No, 3, 4, raz, 2. Good morning, ladies and gentlemen. My name is Teresa, and on behalf of Leadvent Group, let me welcome you to the second annual Wind Turbine Blade Materials and Recycling Forum. Thank you everyone for coming, and I hope you had a nice rest. You managed to get a little bit of coffee, and let me now share a little bit of the organizational things with you. From my colleagues, you have received conference materials. Inside you will find an agenda, delegate list, and evaluation form. Also the speaker's bio. So you have a lot of reading to do. And please, I would like to remind you also for the evaluation form throughout the conference, please evaluate the speakers, their presentation skills, the content, and the general impression of the presentation. As you can see in the agenda, everything will be included for you. So there will be 2 coffee breaks, one in the morning, second one in the afternoon, and 1 lunch. For the lunch, we will go for the restaurant, basically the same one as for the breakfast, but don't worry, we will always navigate you. In the evening, we have scheduled an evening reception for you for more networking events. So there'll be 1 hour of the drinks and some finger food for you to enjoy. For other logistic details, the restrooms are located just on the right side of the meeting room, and all the coffee breaks will take place in the lobby in front of the meeting room as well. For our speakers, they will be presenting from the stage, as me now. Please always use the microphone because our conference is web streamed, so we need to have a way how to transmit the sound. You can also use the hand microphone here, or should you wish to use a headset, please reach out to my colleagues in the AV in the backside of the room. In the conference material, in the agenda, and on your badges, you have also 2 QR codes. One black and one is for accessing our online platform. You should have all received the login details via your email. If this is not the case, just reach out to me and we will reset it. The second one, the colorful QR code, is for the photos. As you have noticed, we have our photographer Mika here, so she will be regularly taking pictures of you, and everything will be uploaded on the shared drive on the album. For other organizational stuff, all the presentations will be shared. Usually it's gonna be within 2 or 3 weeks time because we want to allow our speakers to make any changes, and it will be always shared in the PDF. And also you will receive the recording of the conference. So if you don't manage to follow up on all the presentation, you can do so after the conference. I think that was enough from me. Let me now introduce the chairman of the conference, Mr. David Morgan. Thank you very much. The stage is yours.
Good morning, everyone. I hope everyone had a pleasant rest last night and is prepared for some stimulating and some very intellectual conversation on how we can basically solve this industry problem. So my name is David Morgan, as Teresa said. So I live in the US, but I'm here a lot for conferences and working with different industry partners for what we all want to achieve is the recycling of wind turbine blades. And so I'm just going to say a couple of comments this morning, and then we'll start off with our first speaker. But it's very exciting because we have industry here, we have government representatives, we have nonprofit and organizations, we also have, of course, academic institutions. And you've all heard the phrase that it takes a village to raise a child. Well, it takes a village to recycle a wind blade as well. And so we should be very happy, we should be very encouraged and stimulated with the type of individuals who are here and the groups that they represent, because if it's any indication of what we've been able to accomplish in the last 2 or 3 years with respect to advancing polymer composite circularity, then we should be highly optimistic over the next few years, especially the rest of this decade of what we will be able to achieve. So one of the things I wanted to point out this morning is something that has just been really announced in the last couple of days, and that is House Resolution Bill 9676. Accelerating a Circular Economy for Plastics and Recycling Innovation Act of 2024. So this is a bill that's going into subcommittee in the United States Congress right now, but I think this is indicative, as you all know, in the United States, we're a little bit farther behind in terms of wanting to have these types of initiatives in place, what we're already here doing in the EU. But this is encouraging. This is the definition of what's coming now out of the other side of the pond. The term recycled plastic means products that are produced from mechanical recycling of pre-consumer recovered feedstocks or plastics, and post-consumer plastics, or from the advanced recycling of pre-consumer recovered feedstocks or plastics, and post-consumer plastics via mass balance attribution under a third-party certification system. The terms recycled content and certified recycled shall have the same meaning as recycled plastic. So what we're seeing right now with legislation coming from different government bodies is this move to see circular economy standardized, one, which is fantastic, but number two, seeing that once material has been recovered through a chemical or a thermal or a mechanical type of event and process, that material is no longer a waste stream. It is a recycled product to raw material supply. So that's very, very encouraging. And we can see the same thing maybe taking place in other parts of the world as well in the very near future. So all of us, I think, will have a lot to contribute to. Please take advantage of conversations while you're here. Realize that the order, so to speak, is looking at some of the technologies that we have all been able to contribute to in this room and to advance the circularity of polymer composites specific to wind. And then we're also looking at some of the sustainability aspects for what circular economy entails. And then even what is next, so to speak, on the horizon? What does circular economy and sustainability really mean? What are the effects and the implications thereof, not just for this region, but for the rest of the world? And again, be encouraged, because the conversations that we're having over the next couple of days are not going to be just indicative of what's taking place here in this region, but it's going to be indicative of what takes place globally. So without further ado, I would like to introduce Professor Marcello Colledani, Professor Mechanical Engineering Department of DEREM, Co-Project Coordinator at the Politecnico di Milano. So, Professor.
Thank you. Thank you very much, Chairman. And good morning from my side. Well, big responsibility to be the first in the program opening technical speeches. So I hope I will be able presenting effectively the ongoing activities of our project DEREMCO that follows up on the previous project FiberUse that you may have heard in other events in the past few years. I'm a professor in mechanical engineering department, and I'm coordinating DEREMCO and FiberUse as well, that was finished in 2021. So I will directly jump into the main reason why we are here, and I will first learn how to switch slides, and then, okay, good, it works. I don't think I have to go in details of these charts. I mean, if we are here, it means that we are well aware of the complexity and needs for taking care of finding suitable and sustainable solutions for recycling the currently installed and old and arriving to the end of life blades in the wider applications in Europe. There are many studies about data on the volumes of expected wind blades in the next few years. I took this chart, but there might be other charts in the literature showing that this problem is important. 70,000 tons of blades by 2025, it's what this study reports. Other studies report slightly different numbers, but reality is that the problem is there because 2025 is next year. So we are getting to the point where the amount of post-use blades is increasing, and this creates a massive flow of post-use GFRP and CFRP on the market that needs to find a destination, needs to find a solution that should be economically viable and environmentally sustainable. These 2 days, we will hear strategies to make future blades more sustainable, which is a super important problem and actually very interesting as well from the technical point of view. But we don't have to forget that we have a population of already installed blades that was done without this criteria that we are trying to follow now of reversible resins and sustainable resins and sustainable composite formulations that still need to be treated. And today, there are no actually solutions that can make this blade recyclable and recycled with good performance and with good economic and environmental sustainability. This is a matter of fact. So both problems should be taken together if we want to bring sustainability to the entire wind energy industry, I think. And what our chairman told us just before this presentation goes in exactly the same direction, I think. We have a specific aspect of these GFRP and CFRP composites is that they are not only used for blades, but again, trying to be more effective in switching, they are used in many other sectors. Again, different statistics give us different shares of the market for construction and for energy system with respect to the other sectors. Roughly 1/3 of the GFRP consumption goes in these sectors, but there are other sectors as well that absorb quite a lot of these materials. And this is a challenge, of course, but it's also an opportunity. Opportunity because the technical requirements for these materials in the different sectors are not actually the same. And wow, this is really kind of difficult to deal with. Okay, it's getting there. And if we compare the technical characteristics of this material typically used in these sectors, we see that these charts offer us a degree of freedom for reusing materials from one sector into other sectors while preserving the technical characteristics that are actually needed by that sector. So without compromising on the technical performance of the products that are reused in these secondary fractions. This is what we call cross-sectorial circular economy options that we are trying to grasp in all our projects, trying to find high-added value solutions, if not in the same sector, in other sectors that will require the residual properties of the material. And this is, of course, beneficial both for the input sector, blades in this case, while because we can achieve higher sustainability along the entire life cycle of the blade, but also for the target sector, because the target sector can replace virgin material with secondary materials, hopefully at lower cost. This is what we try to achieve in the first project I will be talking about very briefly today. That's Fiberuse. Fiberuse was launched in 2017 and was finished in 2021. You may have heard already about this project because I presented in many other events around Europe, Wind Europe events, for example. And there's also a book published. Where should I point? Yeah, this is the challenges of being the first presenter in the agenda. Well, you may have heard about this project because we delivered 3 years ago that book that you see over there. Thanks. That's actually presenting in a unique volume the entire set of technological innovations that we achieved in Fiberuse, as well as a presentation of the first set of products we produced and we brought to the market, integrating considerable fractions of secondary glass fibers obtained from treating wind blades. Now I don't know how to switch anymore because I don't have the switcher. Thanks. We also brought some of these products to a high visibility event in Milan. That's the Design Week. I don't know how many of you are familiar with this event, but it collects and it brings together more than 100,000 of visitors every year. And we gave the feeling of the quality of these materials by organizing this high visibility installation. Was 300 square meters, where we presented in these settings all the different products, both design products, but also technical products, to the wide set of stakeholders, citizens, but also industries. Now, after Fiber Use, we had two let's say, follow-ups. The first one was creating a company. Fiber Use Tech is the company today on the market, is a startup that received also some funding for bringing to the market some of the technologies we'll be talking about today. And the second is to launch another project to allow more stakeholders in Europe to experiment with this material and to produce prototypes of products embedding these materials in their product families. Nice installation, right? So there was this effect of retro-enlightened glass fiber reinforced plastics construction material that was very nice also from the design perspective. So we tried also to, let's say, bring visibility to the quality of the material and to the aesthetical appearance of the material that you can obtain. Which is a very important leverage for achieving a bigger market. Now, this is Erenco. So the new project we launched 2 years ago, and we are now 1 year to the end of the project. I'm coordinating this project as well. It's bringing together 30 partners from 7 countries and regions in Europe, and with a high footprint, as you see over there, of companies from Lombardy region. But also from Slovenia, Spain, from Finland, and Portugal. What we are trying to achieve here is simply to open the market. So to have more companies embedding these fractions in their products, trying to demonstrate that the technical performance of this material are comparable with the technical performance of the raw materials, the primary raw materials, and trying to adapt their manufacturing processes in order to steadily absorb in input recycled materials from glass fibers. So that's very, very synthetically what's our objective. Target TRL is high, TRL 8, even 9 in some cases. So you will see very market mature products out of this project. Can I get the, thank you. In order to do this, on top of the cross-sectorial things a lot, cross-sectorial principle approach that I showed before, we added another approach that I think is even more important to make this transition stable and systematic. What we call the demand-driven specification compliant circular economy approach. What does this mean? Well, typically in recycling, you may know because you are in the sector as well, companies, not only for blades, but for all materials, they apply some processes they usually have in their plant. I'm talking about recycling company. They look at the material, they characterize the properties of material, and then, only then, they try to find a market, trying to find off-takers. So the recycling market today is intrinsically push, right? This is good because we achieved some results in Europe, as it was said before, but it doesn't make the approach mature enough to steadily reach off-takers on the market. We are trying to reverse this approach. So we start from the specifications coming from the different application uses of the material, from different application scenarios, and we pull these specifications in order to adapt the recycling process and making the material steadily in specification through this controllable recycling process. So we think that this approach is very important to make recycling at the same level of maturity of primary material production and achieving the specification compliance of the recycled and secondary material streams. I don't want to make the story too long. I want to give you some examples as well. So here we are following two main strategies. Strategy one, and you see all the demo cases or pilots or companies that are experimenting on this strategy, is to mechanically treat the blades, obtain different fractions at different granulometry depending on the specifications that the user holds, and then reprocess this material together with other either secondary streams, typically industrial waste of composites, or primary materials in order to obtain in-specification products in all these sectors. So these are the output sectors that we are tackling with our products in these 10 different use cases or pilots in strategy one. I will give you some example later on, but we also have a second strategy that is dealing with the thermochemical recycling of the blades in order to obtain clean fibers and resins or resins byproducts that can then be reprocessed through resizing and reprocessing to obtain other new secondary material for new composites, preserving a little bit higher mechanical performance of the fibers. Now, a few more details about the process chains of strategy one and two. Very important, blades are inhomogeneous. We know that. So the quantity of glass fibers along the blade length varies a lot. So what we do at the beginning is to obtain a smaller portion from the entire blade, trying to sort the different portions with respect to homogeneity in the quantity of fibers of the specific parts of the blade. We have developed a technology for high volume treatment of this blade that obtain very controlled classes of input samples, input materials to be then sent to the second set of processes, which is 2 or 3 stages mechanical recycling. Typically, we apply a first gentle stage, a gentle shredding stage, a low RPM, so in order to avoid dust. And then, depending on the specification, we can apply 2 further or 1 further stage of shredding, meeting different target granulometries of the specific application. Now, I have a video showing a little bit more in details what we do. I hope it starts. I don't know if we will have time to see the entire video because I think I lost quite a lot of time with this issue, but I hope it gives, oh, whoa, no, yeah, should be started. Well, we save 2 minutes if it doesn't start. No problem. No problem. The video will be available in the final presentation, which is a PDF, so you won't be able to see the video, but upon request is available. So according to the second strategy, the thermochemical recycling, what we are doing is, thanks to the partnership between Fibergis Tech and the Corec, we are using this control environment pyrolysis process that is an innovative technology that we already experimented in fiber use and is able, with a pretty reasonable low cost, to treat and separate fibers from the resin, and the byproduct can also be used to make more economically viable the entire process. And of course, the fibers themselves usually lose part of the mechanical performance, but not as much as the traditional pyrolysis process. Then by resizing, so by a process that brings back the compatibility of the fibers with the resin and gives some more advanced mechanical performance, we can then obtain new composite material for the target application. Now, in the remaining 4 minutes, I will give you a hint of the applications. Now, the video didn't work, but I have some samples with me of all the phases of the process. So if you are interested, just I'm seated there. Come and I will show you a little bit of what we can do with this process chain. So one of our companies, NTS, is using these fractions coming from strategy one, mechanical recycling, for obtaining parts that are basically targeting the automotive sector. Now, you know how demanding is the automotive sector in terms of certification, in terms of performance, in terms of stability of the performance. So if this company succeeds in integrating more than 50%, usually the composition is 65% of recycled GFRP in their BMC, well, it's a big achievement. And it opens the way for massive introduction of this material, because the volume is what makes a difference in this approach, right? We need to be sure that there is stability between the input volume of post-use blades and the output demand of these materials. Well, this use case, in my view, is very important for the volume side. It can ensure reasonable volume of wind blade streams to be reused in a high-end application. You see some of the products that this company is producing, and the mechanical techs are very promising for a massive introduction of this material in this sector. Another company that we are working with in this project is Caracol. Caracol is a company producing technology for 3D printing of massive size. And in this case, the specification on the material is totally different from the BMC application. So it's very fine, usually 0.1 millimeter granulometry of the material that we can achieve through 3 stages of shredding. And once this material is achieved, the company has developed a solution for producing new parts. In this case, is mold is a tool for, again, producing other components from small wind blades. Another case is from Slovenia. This company is producing these fences for outdoor applications, and usually produced only by virgin materials. Now they are integrating a considerable fraction of recycled material, again, a market with a high volume potentially. Concerning strategy 2, and I have 1 minute left, we are fostering a very interesting solution by our partner Centrocoat from Lombardy. It's a textile company. They are using the liberated fibers in conjunction with other fibers, typically coming from recycled polymers, and applying a process that is able to obtain a hybrid yarn that can be then used for new textile production. Here you see one example of this hybrid yarn. So it's a very interesting material that can be used in high-end applications due to the residual performance of the yarn. And last, another application I want to show you is the reuse of both mechanical recycled and thermal recycled fibers for producing mat for construction. Here we are cooperating with another company of Lombardy for obtaining this mat at very high quantities. And this mat preserves pretty significant residual properties for different uses in construction. And this demo case is in the end at this moment of Fiber Use Tech. Now, you've seen some of the applications. There are more because we have 14 cases. So I don't want to be exhaustive with this presentation, but I want to give you a sort of hint about the fact that with this cross-sectorial approach plus the demand-driven approach, we can even absorb quite a significant fraction of these materials in different applications. What's next? So, as I said at the beginning, opening the market is the key word for us. So trying to find more and more applications with companies that produce composite-made parts, demonstrating that we can meet steadily the required specifications, and we can help them substituting virgin materials with the secondary materials with the high performance. So in view of reaching this goal, we are trying to implement different strategies. First of all, in Derenco, we have open calls. The first open call cascade funding mechanism was closed last month, but there will be another open call launched in November, funding experiments to small, medium enterprises for trying to insert this material in their in conjunction with their primary streams. If you're interested, go to the website of Derenco and see all the details of this open call 2 that will be launched in November. And then we are cooperating with different institutions, trying to find a systematic way to support companies in our regions to do experiments and to achieve a market with their products. Here you see the visit of Mr. Sheffer that came to Polyme, president of EIC, trying to find synergies between this project that is funded under the I3 mechanism, Interregional Innovation Investment Mechanism, and the EIC mechanisms. I hope I gave you a sort of a hint on what we are doing in Derenco. Again, samples are there. Sorry for the technical problems that didn't allow me to show you the video. But again, if you are interested, please send me an email. I will distribute the video. And you will see anyway some videos available already on YouTube if you select fiber use. Thanks for the attention. Open for questions.
Any questions from the audience?
Thank you, Professor. My name is Derek Berry from the National Renewable Energy Laboratory in the United States. Really interesting. Thank you so much. One of your slides mentioned that in addition to the fiber and the resin system, that other materials involved were gel coat and bonder, which I'm assuming is adhesive for bonding the blades together. What wasn't on that list was core material, that at least that list, balsa or foam core. Is that something that is recycled along with the resin and fiber, or do you have to remove that or not use those sections that have core material? And maybe it's just that one slide.
Yeah, very important question. Thanks a lot. It's actually a good example on the effectiveness of the demand-driven approach. There are some applications that are robust to the introduction of impurities. And if the target application is robust to the production of impurities, we avoid sorting out the impurities before the shredding. There are other applications that are very sensitive to the presence of impurities. In that case, the pre-shredding cutting technology that we are developing, and today we applied a low volume, is able to sort out impurities that can be cut from the blade, but is not always necessary.
Thank you so much.
You're welcome.
Hello, my name is Nina from Vestas. In these different applications of the reused fibers or recycled fibers, what is the potential for another life cycle after that?
What do you mean by another life cycle?
So if they are put into these applications, can they then be recycled when they reach end of life?
Sorry, I thought another life cycle within the blade in the wind blade industry. No, you're talking about multiple life cycles. There is potential. I mean, those products obtained by integrated mechanical recycle fraction is obvious that there is potential. But for those applications integrating textile or fibers obtained by the second route, there's still potential. We have done some tests on the construction material. I have to say we have not done massive tests, so I cannot really ensure about the residual mechanical properties. But it depends very much on how you reformulate the resizing process.
Thank you.
Last question.
Thank you, Professor. I'm Meta Wang from Japan, and related with the first question about the purity of the material, and it depends on the purity of the material within the balsa or not. So there must be the big difference of the tensile strength and the twist strength. And so application for next the item can be different, just your panel or some industrial the material which require the strength. And so is there any data or some result or cost model for that the items, each item? So.
Yeah, so we have all calculations, of course, behind the business cases. And clearly, the mechanical performance are not the only two requirements for finding the right application for the right streams. There are other requirements for different applications. For example, the thermal, the resistance to fire, it's one of the critical aspects for reusing this material in some applications. I didn't list all of them. We have a platform, digital platform, a software that we have been developing in fiber use and also in Derenco, enhanced in Derenco, to grasp all the technical specifications of each application and trying to find the right application for the right input stream. I didn't talk about this because there was not enough time, but if you're interested, we can comment about this. All these business cases have calculated economical feasibility, right? So behind there is a calculation of the economic value of the material compared with the virgin material, and all of them are feasible from the economic point of view.
Thank you.
Of course, assuming some target volumes that are not there yet.
Marcelo, thank you very much.
Thank you.
For your time.
Thank you.
So now for our next presentation, we have Nina Wittig, Material Specialist in Innovation and Concepts at Vestas. Thank you.
Thank you, and good morning, everyone. I think in this room we can all agree that environmentally speaking, wind turbines do more good than they do harm. They produce green energy for the world, and because of their very long lifetime, they also have a big payback, both environmentally and economically. Moreover, more than 80% of the materials going into the wind turbines can already be recycled. But of course, it's the last fraction, including the composites going into the blades, that are the difficult part and the one we must focus on now. As a materials chemist, I cannot be satisfied that the energy and materials going into these blades are going to waste, when in fact we should view them as valuable resources, which they were when they were introduced to the blades. And I'm sure that many of you will agree that looking at the many pictures of blades in landfill can only be considered the opposite of out of sight, out of mind. And this is, of course, a challenge that is very much on our minds in Vestas. And my name is Nina Køllen-Vitti. I am a material specialist in Vestas R&D and a new face in this circle. And today I will take you along with me on our journey towards blade circularity. Let's see if I can figure this out. Yes. So who is Vestas? We like to call ourselves a global leader in wind energy with more than 30,000 employees around the world, all contributing to a better world through design, manufacture, installation, development, and service of wind energy projects. We have more than 57,000 turbines under service, which is the largest fleet in the world. And with more than 177 gigawatts of installed wind turbine capacity spanning 88 countries worldwide, we help the world avoid more than 230 million tons of CO2 equivalents annually. And this global reach is to a very large extent possible because of our local presence. We have sales, service, production, and research facilities located all over the world, as you can see on this map. And our portfolio includes both onshore and offshore solutions, as well as service and development contracts underlying these solutions. And if we go a bit more into the sustainability part of it, our turbines are energy neutral in only 4.8 to 7.6 months of operation. So if we assume a 20-year life cycle, this means that our turbines will generate around 30 to 50 times more energy than it uses in its entire life cycle. This is way outperforming traditional energy sources like gas and coal, and also nuclear power. And these numbers are actually quite conservative. In Denmark, we know that the life cycle is closer to 29 years than 20 years, and this is excluding refurbishment, which is also very widespread of our turbines. And looking at the carbon footprints, they are also very low, only about 4 to 7 kilograms of CO2 equivalents per megawatt hour generated, which is orders of magnitude lower than what we see for coal, gas, oil, and even solar power as well, which is around 10 times higher. And this means that since 1981, Vestas has helped the world avoid more than 2 billion tons of CO2 equivalents being emitted into the air. And the turbines produced and shipped in 2023 alone, we expect them to avoid 396 million tons of CO2 equivalents over their lifetime. And this is actually equivalent to the fueling of 88 million passenger vehicles, or the electricity use of 77 million homes, or the carbon sequestering of more than 1.9 square kilometers of forest. I don't know if I said that. Good. Anyways, as I also said in the beginning, we need to do more. We need to live up to our principle of sustainability in everything we do in Vestas. And this was announced with our sustainability strategy in 2020, which relies on 4 pillars. First of all, we want to reach carbon neutrality by 2030 without using carbon offsets. We also want to reach zero waste wind turbines by 2040, which is the focus of my talk today. But other than that, we also want to be the safest and most inclusive and socially responsible company in our industry and lead the transition towards renewable energies. But let's keep focus on zero waste. Yeah, there we go. Good. So having zero waste wind turbines means that all of the materials we put in there over the entire life cycle, so also during production and manufacturing and at end of life, should be able to stay in the value. Should keep value. And this also means that we need to know exactly what materials we put into our turbines. And in Vestas, this is detailed in our life cycle assessments, here shown for 2 different turbine types of our 4 megawatt platform with slightly different weights and material compositions. And depending on the turbine type, around 80 to 90% of the turbine can already be recycled. But as I also said in the beginning, it's the remaining fraction that's the hard part. This also includes finishing materials, paint, electronics, and so on, but definitely also the composites going into the blades. These are built to last, not to be disassembled, and therefore they represent a challenge that must be tackled with new means. Therefore, in 2021, where do I need to point? There we go. In 2021, Vestas announced a circularity roadmap, which has 3 main areas of focus. There's, of course, design, operation, and material recovery. We need to design materials and turbines that can last for a long time, ensuring a long operational lifetime, but also that can be disassembled both in parts and into materials, so that we can put them through these loops of increased size, assuming that increased loop size means increased energy input or other input of resources. So first of all, we would like to be able to service our turbines, maintain them, but also reuse, repair, and remanufacture only parts, refurbish whole turbines for reinstallation, and finally, decommissioning and recycling all of the materials going into the blades. And this design for circularity, which we can call the top level of this roadmap, is where we are focusing right now. These loops also indicate that we should make sure to involve all the stakeholders of the value chain. We need to be involved, investors and other OEMs as the manufacturers, but we also need our customers, the developers and wind turbine owners, to actually put the end-of-life turbines back to waste handlers, which need to be involved in scaling new technologies so that materials can go back to our suppliers, and they need to be able to take them back and give them back to us or others that can actually reuse the materials. So we all need to be involved in this. And moreover, we need brilliant researchers, like we just saw also from the talk before, to actually be involved in the development of these new technologies. So when Vestas first started our design for circularity path in 2016, it was together with researchers from Aarhus University in Denmark and Danish Technological Institute. And the aim here was to identify modifications to the epoxy resin, which would allow for programmed disassembly of the composites so that they could be reused. And a proof of concept was already found in this project. And the next step was then to scale up such a solution. And moreover, it was also identified that the difficult fraction for actually recycling at high quality was the epoxy fraction or the resin fraction coming out of the disassembly process. And this, we needed a route for it to be converted back to its monomers in a chemical recycling process, which we call ChemCycling. And therefore, another important stakeholder in the value chain was brought in, represented by Olin, which is one of the leading epoxy suppliers globally. And again, we have this circular loop indicating that we need all parties to be involved. But we started with focus on this fraction, the resin fraction. And actually, we ended up finding a solution that was even better than we had hoped for. So the aim was first to find a chemical modification to the epoxy resin, which would allow for programmed disassembly. But we actually found a disassembly process that could work for the epoxy that we are using in Vestas now and have been using for several years. And also a ChemCycling process for this. And this means that we can cut 20 to 30 years of the actual implementation of the solution, since we can start recycling end-of-life blades already today. This, of course, puts a very big task immediately ahead of us, since we need to be able to bring this solution to scale as soon as possible. So we have shown that there is a way for the resin, but of course, during the disassembly process, many more fractions are coming out. And we are now partnering with Stena Recycling, that are able to industrialize this separation process. And I think we will hear more about that later today. But together, we're looking into to all of the different fractions coming out, qualifying them, and finding out what their actual value is. We are building up a business case. And it does turn out that even though this is a big problem in our industry and probably our Achilles heel, so to say, the volumes of end-of-life blades are not that big right now. They will be in the future, but right now they are not that big. And when we divide them into fractions, the volumes become even smaller, but the investment is really big in these technologies. So we need to be able to carry this investment, all of us, not only the developers or the waste handlers or manufacturers, but all of us. And we need to be able to put a value on increased sustainability and include this into our business cases. And I think this is really one of the main challenges that we're facing in scaling up these solutions. Anyways, we have shown that it is possible. We have shown that the design we have today is actually already designed for circularity. And in Vestas, we have service department, which makes sure that our long lifetimes are maintained. We also repair and remanufacture parts. We have a department for refurbishment that buys back end-of-life turbines and converts them back to technically new conditions so that they can be sold with a new warranty and service contract. And finally, at end of life, we now also have a recycling solution which can allow for the materials to go back into the loops. So with this, and also a bit of time left, I can see, I would like to thank you for your time, and I welcome any questions or discussion points. Thank you.
Any questions from the audience?
Nina, thank you. Derek Berry from NREL. What was unique about your previously used or being used for several year resin system that allowed you then to go back and recycle that without developing a new sort of reversible resin system? What was the, maybe it's getting too deep chemically here, but how is that possible without developing a new resin system, I guess is my question.
I think it is a lot to do with luck. So the researchers involved from Aarhus University, they found a chemical way to disassemble what we were already using. So it turned out that that wasn't as impossible as we thought initially.
And that what you were already using was a standard epoxy resin system.
It's an infused epoxy system, yes.
Okay. All right. Thank you very much.
Hello, my name is Niklas. I come from Siemens Gamesa. I want to ask about the core materials, because I didn't see any of that in the fractions.
Yes, I think it wasn't my newest presentation that was up there. I had put also core, because of course this is also an important fraction coming out. And actually already the core material we use, it's PET and can be recycled quite easily.
Thank you.
Hi, Nina. Thanks for your presentation. My name is Declan and I work for DNV. You made an interesting comment at the end there about refurbishing turbines and then selling second-hand turbines. Where is the market for that for Vestas?
I think it is a market with more demand than we are actually using right now. So the department in Vestas is still quite small. So they are taking in as much as they can, and I expect that this will grow.
Thanks.
Any others? Very good. Nina, thank you very much for your talk.
Thank you too.
So our next conversation today is by Julio Vidal, Head of R&D Department, IDI at Moses Productos.
First of all, I will try to work this out. No, okay. Yeah, thank you very much. Thank you very much for the organization, for inviting Moses, for inviting me here to speak about the different projects that we are developing. Moses is a spin-off from a technology center, so we don't have the numbers of Vestas. We are just around 30, 40 people. So what brings us here? We are in Spain, as you can see. For those that you that don't know, well, Zaragoza is there, Barcelona is there, Madrid over there. So in the middle of a really core point in Spain, which is we have a river by the side in a valley, so plenty of wind power at our disposal. We started in 2008, but we didn't start with the mission of wind blades by itself. We started with different products that we have that are based on thermoplastic materials. Sorry. Now, so we started with rotomolding thermoplastic materials. We started with this kind of products, thinking about hydrogen, fuel tanks, containers, and so on. We also develop other products, also in thermoplastics, in which we are starting to recover glass fibers. So any glass fiber that can be provided from wind turbine blades, we are eager to test it in these blade keepers, okay? To protect during the harvest season, we use thermoplastic and glass fiber to avoid any sparks so that we will have any fire during the season. What brings us as a technology tech center and a spin-off focus on thermoplastics into this sector? Specifically, what I have mentioned to you, the potential of our region. Sorry. No, not now. The potential of our region with the wind turbine blades. This is a picture of a map taken in 2021, so 3 years from now, but you can see all the different parks or farms that we had in the moment, everything that was planned and everything that is being planning ahead. We have plenty of wind turbine blades in our region. We will have more. There is still more developments in this sense. And as a company based in the center of the region, we want to be prepared to dismantle all of this material and provide to our industry a new solution. So we started a new project, which is Eolo Hubs. It's a European project based on circularity in the circularity concept. You can see partners all around Europe, mainly coming from manufacturers to dismantlers such as ourselves or Mitsubishi, and plenty of technology centers and different universities and partners that can collaborate with us in order to provide us a solution that will enable us to go into the end of life of all these wind farms in the region and provide a solution for the problem and provide a new income and new resources to be used in different products such as the one that we already have, or different products that can be used or that we can take over. As has been mentioned also in different in previous speeches, we are also talking with automotive sector. We are also working with construction sector and many other sectors, trying to see if they can take in all of these glass fiber and carbon fibers that will be in the future wind turbine blades in order to provide a solution. Because it was mentioned now that today we don't have plenty of blades to be decommissioned, but in the future we will have plenty of them. And I can tell you, just with the parts that we have, we will not be able to take over all these glass fibers. So we are looking at different strategies, different industries in order to achieve that. But first of all, we have to look at the wind turbine itself. I will not go in depth, but because in here, I think all of you have seen a picture such as this one. We have many different materials, many different parts of the wind turbine blade, and an heterogeneity in the materials that are used in this manufacture. So we need to take this into account if we want a proper end-of-life cycle. What we did in that sense is to put all of that consortium that I have already mentioned together and develop this scheme. This scheme is based in two different lines, okay? First line focus on this in the south of Europe, okay? More in Spain, Italy, and the second line more focused on the north of Europe, Denmark, the Netherlands. Of course, all technologies that are being developed in one or the other can be changed and we can mix them up. But I will focus on the decommission and the green chemical solvolysis. Okay, the decommissioning is focused in the northern part, a low carbon pyrolysis is focused by Mitsubishi, in which they are trying to bring up or make more optimal the pyrolysis process in order to make it industrializable and make profitable the reuse of glass fiber. So first of all, we have to decommission these parts. And sorry. Now, okay. And this is the blade. What we did is to work with water jet cutting pieces in order to separate the different parts of the blade. We know the structure is pretty complex and we cannot put all those different parts in a single recycling system all together. So what we need to do is to cut them. Even if we want to go everything into pyrolysis, we cannot have a reactor that is taking the full blade itself. So we need to cut it. We need to chop it in order to adapt it for the different technologies that we will use afterwards. And we need to cut it in order to separate the different materials. So this is what we did. Sorry, I always point to the other part. The idea with this, we have two different ideas. One, that is to remanufacture all these parts. There should be a video starting. If we can start the video from. Okay, to cut the parts in order to have a proper or different perspective of the use of these composite materials, and also to cut them in order to chop them into the different parts. As you can see here, my colleague, he is with a geometrical form designed to capture all of its movements, and he will be moving in order to define the strategy that we want to cut. Imagine that we have the map or the plans of how the wind blade of the blade is made. We can separate the carbon fiber from the glass fiber. We can separate where we have a core, where we don't have the core, which parts is more interesting for us, and so on. So this is what we are doing. We afterwards take all this data and put it into the computer. And this is the track that the robot will take in order to make the water jet cutting. If we can maybe move to the middle, because it's an 8-minute video, so it will eat my whole presentation, just in the middle, for example, there. Here you can see the robot has gone to the place, and now it will start the cutting. It's positioning itself. Yeah, and here it's fine. No, if we can play it. No, okay. So, well, I can send you, those of you that are interested, I can send you the video. What we will see is that the robot is miming the movements of my colleagues so that one person can design, make a really complex cut, and then the robot with the water jet will be cutting it with this exact form. So we can separate all the different parts. What we did from that point is to go for solvolysis process. We have already cut the parts. We have already separated the different resin from the core and so on. And what we did is take several standard resins and put it into the solvolysis process. This is an acid oxidant process. And as you can see in here, we can dissolve the resin. Okay, we just apply some heat, nothing really extreme, about 80 degrees. So it's not something really energy consuming. We tried some other resins coming from the project and some other resins also coming from the different manufacturers. Most of them were dissolved. I can tell you, we have to try every resin in order to define which are the parameters that we need to dissolve it and which are the parameters or which are the resins that we cannot dissolve or we can dissolve partially. So every resin has its own systems. We have already heard about epoxy resins are really complex resins, and therefore we don't have one solution for all the different systems. Afterwards, we went into the composite. Our process does affect the fiber or no? What we observe is if it doesn't affect the fiber and that we can recover the fibers after the solvolysis process without any damage. So we started the scale up process, or we started to understand how we can scale up this process, how we can make this process faster. In here, you can see that it takes around 24 hours to be completely rid of the resin, but we can make it faster now. We can optimize these parameters. This was done in the first trials. We can increase the temperature, increase the percentage of acids, oxidants. We play with all those points, and we can make our system work faster in this sense. This is not only at lab scale. We have also done it at first pilot scale with reactors of 20 liters. As you can see in here, our main problem was not the dissolution of the resin, was the mess that we had around the rotor blade with all these fibers. We are working with long fibers in order to recover the fibers with the highest value possible. So the fibers are just wandering about the reactor as we have the rotor, and they entangled all around. This is a problem if we want to industrialize all of this, because afterwards we have to take the rotor out, we have to start pulling all the fibers, and this is a really big problem. So what we thought is about making a basket or a kind of basket. Now, we put half, okay, this is the thickness of a real wind blade turbine. We cut it in half, okay? We didn't put it as a whole. We put it inside the basket and put our system. What we obtain from this side is that we have the fabrics itself. We don't have a mess, so we can recover not only the fiber, but we can recover the fabric. This, we can scale it up to different sizes, to different geometries, in order to adapt to the geometry that we want to use. Next steps for us is to understand if these fibers are really useful in a composite, as a fabric, or if we have to keep chopping them as fiber in order to make another textile. This is something that we will have to see and we will have to study. But first of all, which are the quality of these fibers? What do we damage the fiber? In case if it's glass, in case it's carbon, what's happening to each of the fibers? In here, you can see some values of the average tensile strength, modulus, and also you can see a Raman spectroscopy of carbon fiber. You can see that it's mainly not damaged. It's more damaged mechanically than chemically, although of course we have an acid and an oxidant agents in reaction, so we are affecting a little bit the carbon fiber. In the case of the glass fiber, it seems that we are not affecting at all the glass, which makes sense because our reactor is made of glass. So it's pretty good for us, so we will be able to use the same reactor. With this, we have found a solution that will enable us to bring the commissioning of the wind turbine blades, to cut them or to chop them into the geometries that we want in order to keep the value as high as possible, and also the same possibility with the solvolysis process. Once we have chopped them, we can put them into the reactor and recover resin and fiber. I have not focused on the resin because it's something that we are still working on, but once the resin is in this liquid, we can recover all those monomers and oligomers from the liquid and try to use them again as a new source of epoxy resin system. With this, I want to mention to you that in ITIP and in MOSES ourselves, we are developing several technologies because we do not believe one technology will be able to enhance all of this. We have this idea that we will be able to come up with a synergetic system that will enable us to provide a solution for all these problems. In fact, we are also working in the project that I will mention right now with enzymes in order to degrade the epoxy system so that we will have the specific monomers that will enhance us to use, or that we will enable us to use them into new epoxy systems, commercial systems. So this is the strategies that we are following. I'm presenting those because I can tell you right now, enzymes, let's say at that really low TRL, we are working with milligrams, so maybe it's not ready to go into the market, but this is the perspective that we have and what we want to build. In this other project I have mentioned to you, which, okay, it's a smaller project, it's really R&D focus. We are focusing on making 100% bio-based wind turbine blade with bio-based carbon fiber, bio-based epoxy, using Bitrumer-like technology for the adhesives in the core, and also using self-healing coatings. So we are putting all of these technologies together in order to define the blade of the future, and also to combine it with all the different technologies that we are developing and that are currently at more market scale, because we don't want to generate a new technology for the wind turbine blade sector and ask them to change completely all the recycling technologies that they are using. So all these technologies will be suitable for all these recycling methodologies. In here you have the scheme of the project, but in synthesis is what I have just mentioned to you. We are using bio-based, or are developing bio-based carbon fiber. We are developing bio-based epoxy resins, bio-based coatings, bio-based adhesives between the core and between the framework inside and the skin of the blade. Everything bio, everything recyclable, and we are also implementing an enzymatic approach to recycle all these materials. So from Moses, just as an idea of the whole work that we are developing, we are focusing on the end of life of wind turbine blades. We are focusing on how we can decommission these blades, how we can transport them, because to cut, it means that we can reduce the cost of transport from the field where the blade is installed to the decommissioning point. And we are also working on a greener future, trying to develop new systems that will enable us to have a full, completely green wind blade sector. With this, just to thank you all for your attention, and if you have any question.
Thank you, Julio. Any questions? It's coming. Microphone.
Hi, hello. Hello. Hello, Julio. Marta from Renocycle. I have a question regarding the water jet that you presented. How efficient is in terms of water consumption?
We are adapting the parameters because the part that I just saw, that was shown in the video, is from an aircraft. So they are using really thick carbon fiber parts. Okay, even in some cases, 2 different layers. Okay, with some air in the middle, but it's quite consuming. I don't have the number right now. I can check it for you and later tell you during the coffee break. But it's quite consuming. The good thing is that we can recover that water and reduce the gain. So if you have a fully closed system, it will be like 0 consumption. But if it's open, it will be quite tens of liters per minute.
Okay, thank you.
Julio, thanks for your talk. Carl England from Washington State University. You mentioned at the very beginning you had a food contact coffee.
Yeah, it's one of the products.
In the States, we have to go through EDA or FDA and get approval for any recycled material going. Is that the same in Spain and Europe?
Think about this capsule these capsules have like kind of 2 layers. Okay, one layer is in contact with the food, yeah. And this is more the aesthetical part that we are producing. So we don't have to care about this because it's not really the layer in contact with the coffee grains.
Thank you, Eric Dalis from Owens Corning. So very interested. I think at the end, you said that you are working on how you will repurpose, reuse the glass fiber that you are taking, but can you provide us a bit of idea on which area you are working on?
Well, we have different industries in the sector. One is the construction sector. Okay, we are thinking about the insulation material used in buildings, which is mainly glass fiber. So the idea would be to use this glass fiber in there. In our parts, for example, we are using glass fiber to reinforce thermoplastic components. So it will be just as reinforcement. And in the automotive, it's similar to that as reinforcement in several plastics, interior or exterior, depending on the kind of car. One thing that we have to work and that we have not checked yet is the sizing of the compatibility that we have between the fiber that we have recycled and the different matrices that we can use. This is something that we will have to look at depending on each of the different sectors. But we are open to everything. In fact, anything that we can put carbon or the glass, it's welcome. And we have just these examples in order to test that really all these tons of material will be afterwards implemented in something. I don't know if I have answered or it's really vague.
No, but yeah, thank you. At least you are exploring many.
Yeah.
Last question.
Thank you, Julio. The question that I typically pose to you in these meetings is, do you have an estimate, at least range? I know that calculation in precise way are difficult at this level of development, but of the cost of the technology.
Which technology?
The
Solvolysis?
solvolysis, yes, I'm talking about the solvolysis.
No, well, I don't have the numbers, but it's I don't think it's ready for the market yet. In terms of use of acids and oxidants that we have, in terms of time, what we are trying to look at in this sense is, do we obtain better values than pyrolysis or than any other? Because in terms of rate, it seems we will be far away, but maybe in terms of quality, we achieve higher quality than in pyrolysis and so on. So we will look for the market that is looking for really high properties, or also that is looking for the fabric itself, that we don't have to. That's why we avoided the fibers alone or strangled, and we try to recover the full fabric in order to elevate the value and be able to afford the whole solvolysis system.
Thank you.
Julio, thank you very much. Our next presentation this morning is Declan McGinley, Head of Operations at Rewind DNV. Declan.
Morning, everyone. Let me see if I can. I'm delighted to be presenting this morning on Rewind, which is an end-of-life planning tool for the wind industry. Today, I'm going to be talking a little bit what our software does, who it's for, who our customers are, and what they're interested in learning about from experts such as yourself in the blade recycling sector. I'm not a blade expert. I'm not a materials expert either. So the insights I share are from our partnerships with our customers over the last 18 months or so. Okay, let's see. So Rewind is part of DNV. It's a project within DNV, which is an independent and global risk advisory and assurance management company. We are in over 100 countries worldwide, but headquartered in Norway. We're fully independent, which means that we can invest quite a lot of our revenue annually back into R&D. And that's where Rewind's funding actually comes from. Our two main sectors are the maritime industry and the energy industry. Some of you may have met my colleagues in energy certification who work with original engineering manufacturers on ensuring hardware is up to technical standards, and we're also involved in writing those standards. And our advisory background, or as my background, sorry, that business works with developers, on ensuring that energy infrastructure is financed and actually built from design to realization. And we also work with investors in financing the energy transition. So the next slide, when I get there, is a little bit of background about how Rewind came to fruition. Rewind's a team of 9, and we came together and secured funding to investigate the problem area that end-of-life planning of wind farms in the wind sector is a growing challenge for the wind industry. The first wind farms were installed in 1982 in California and in Greece, and the sort of major commercial build-out of the wind sector was in the early 2000s. I think many of you will know that wind turbines tend to have a design life of 25 years. So we're at a point in time, where a large volume of turbines are coming offline, and many operators and asset owners are facing challenges of how to handle the sustainable decommissioning of these assets and handling materials within these assets now at end of life. The analysis on my left-hand side, I think it's also your left-hand side, published by Wind Europe last year, shows that many of these wind farms today, the 24,000 in Europe, are estimated over 15 years old. And they're near us in the Benelux region, in Germany, Denmark, France, Spain, and the United Kingdom. And there's a point that there's over 52,000 of these sort of older wind turbines right now worldwide. So a growing problem for the sector. In the same publication, Wind Europe estimated that by 2030, in Europe alone, 13 gigawatts of capacity will be decommissioned and 9 gigawatts will be repowered, which is when an older asset is replaced with a new capacity turbine. So that's a net negative loss, which is not ideal for our energy transition ambitions across the sector. The market's continually growing. As I think many of you will be aware, I won't need to dwell on that long. We publish an energy transition outlook annually, which is our sort of forecast of the different vectors of the energy sector and what it will look like by 2050. So the headline for the wind sector is by 2050, we estimate a 630% increase in capacity globally, worldwide. So there's 1 terawatt of capacity installed today. We expect 1.8 terawatts to be installed by 2030 and 6.3 in 2050. So that's a little bit of the context of why Rewind was born. And Rewind's an end-of-life planning software, as I mentioned, for customers who are asset owners and developers of wind farms. And we help optimize and try to de-risk the decisions required at end of life for wind farms. And we do this in a few ways. One of which is we provide an estimate of the bill of materials of your site within the turbine and the balance of plant. We can calculate the overall circularity of your assets depending on the decisions you take at end of life. We can estimate the dismantling costs at decommissioning. And we also have a sort of first of its kind database with many industry partners in the supply chain who can handle materials. So I also have a video and we will see if it plays. It generally moves faster than I can talk, but it does loop. But this is just a sort of demo of the software and a modeling profile within Rewind. So here we can see our material breakdown estimate for a turbine. This is based on a proprietary loads model within DNV, which is validated against some OEM data, which we are permitted to use, and from DNV's own work in actual design of turbines. And the material breakdown is useful for a number of reasons. It's important to know the volume of and bill of materials when making decisions at end of life. But it's also useful for development projects going forward, where developers are required to submit these bill of materials that are expected at end of life in order to win a tender. The second main value proposition for our customers is our cost calculator. And sure enough, the video's gone ahead of me. But here a customer can enter site-specific details on their turbines, their foundations, their crane pads, roads. For offshore, they can also define inputs on scour protection, that sort of thing. And you can tailor the scope to your specific decommissioning scenario. A report is able to be generated instantly and exported to any stakeholders that you wish to share with. And lastly, we have our supply chain database, which is maybe of interest to some people in the room, which is, we think, a first of its kind database. If I can get to the next slide, with over 800 providers. Bear with me. Over 800 providers globally listed, and it allows asset owners of wind turbines to source companies which can handle materials such as blades at end of life. The screen shows Europe. We also have providers listed in the US as well, Australia and some parts of Asia. And so a customer can filter on what type of materials handled at end of life, what services are offered. Decommissioning contractors are also present, ports are present, second-hand wind turbine vendors are also present. And so if this is of interest to anyone in the room on being featured in our database, please come find me in the networking sessions and drop me your details. This is a view of what the customer sees when they do find you in the database. They can see where you are in the world, what materials you handle, some context about your facility, contact details, and if you are open to sharing as a company, you can share your gate fees, the capacity that you can take each day. So this is a company who are global, EMR, and this is a facility in Scotland that opened this year. Come on. So our customers, as I said, are primarily asset owners and developers of wind farms. Rewind launched in 2023 in the summer, and we launched a pilot of our software with 7 early adopters. Many of them are still with us today. SSE is one of them, a developer based in the United Kingdom, headquartered in Scotland. And they're using Rewind across their offshore and onshore fleet to understand decommissioning costs at end of life. End of life, of course, involves more than just decommissioning, and where we want to go next in Rewind is be a sort of full end of life planning toolbox. There's many challenges facing the wind industry as a wind farm approaches its end of life. So we're wanting to sort of add more value on top of our decommissioning models. If someone can help me go to the next slide. Through sort of conversations with our customers, we found that wind farm owners do not only just wish to decommission, they wish to see if they can either life extend the current assets or in fact repower, which is again when an older turbine is replaced with a new capacity turbine. So we're in an area of sort of discovery right now about how we can actually help our customers here. There's many facets to repowering and adding new turbines. And so we've not landed on where the software might go next, but we are looking for partnerships from asset owners and developers. So if you are a developer in the room and you also share these pain points, please reach out if this is a partnership you might be interested in taking part in. We've got experience in building models and delivering software, but we maybe don't have the insights that you have. So hopefully there's some collaboration opportunities there. Okay, so that's a little bit about Rewind. I thought I'd share what our customers have been asking about blade recycling as a large part of decommissioning a wind turbine. And one of the main considerations that I found quite interesting was that many operators wish for decommissioning as the wind farm as a whole, the blades included, to be ideally carbon zero or carbon negative. My assumption, which is maybe incorrect for most customers, was that they would solely be interested in the gate fee and what price they must pay to actually recycle their blades. But in fact, there is a lot of sustainability interest as well. And so operators wish to understand the true cost of offsetting carbon in the decommissioning process. And this unlocks value in a number of ways. A customer told me last week that they are looking to understand a benchmark for offsetting carbon or an accepted value. And this will feed into many strategic planning across their organization. from a sustainability perspective. So the first of which is identifying decarbonisation opportunities within a project or a portfolio, or in fact the organisation. I think this can be applied wider than decommissioning. So once the cost of offsetting that carbon is understood, how can carbon reductions be made at decommissioning? The data also feeds into sustainability reporting and mandatory reporting requirements. Here in the EU, we have the CSRD. I think many of you will be familiar with Scope 1, 2, and 3 reporting. So that data is useful there. And then there's a feedback loop of understanding the cost of offsetting carbon back into new designs. We heard from Vestas this morning on how that's happening at an OEM perspective, but developers are also taking those same principles there. Non-price auction criteria is when a developer is tendering to build a new wind farm. They are required to compete for the right to build that wind farm. And so having this sustainability data gives them a competitive edge in auctions where that is a requirement to report. And understanding this data allows them to select partners which meets their sustainability goals in the procurement process, and also monitoring this data through the lifetime and operations of a project allows an operator to continually improve. So at decommissioning, this factors in a number of ways. Mainly it's understanding the carbon output during the dismantling of a wind farm, also the transportation of materials from the decommissioning of the wind farm to its end facility, and then also understanding the carbon output of the actual material recycling or recovery process. So on transportation, for example, I've been told by customers of Rewind that they will not send blades overseas, for example. Well, that was a UK customer in particular, as the sea and land freight carbon expenditure will completely offset any opportunities to be carbon zero, in their opinion. And so operators will prioritize markets local to them. And I think there's a constant search for where are the opportunities and companies that can help recycle blades. Knowing where those markets are is a sort of constant hunt for developers. And then on understanding the carbon output of the recovery process, I think if a company can actually provide a life cycle assessment or sharing that data of the carbon output during the recycling process, that will give them a competitive edge when winning work from a developer. In fact, some developers are selecting recycling processes based on that criteria. Some are ruling out energy from waste considerations of incineration based on the carbon expenditure there, and also a PR expenditure or a PR point of view, sorry. In general, I think there's a knowledge gap. Come on, slides. In operators within the wind industry, and they're looking for partners to help inform their strategy going forward. And discover best practice. And so customers of Rewind are constantly looking for commercially ready partners or partners who are near commercial readiness. And so if you are one of those and you can process at least one blade for trial purposes and are willing to share data, I think my customers are definitely interested in talking to you. Other major sort of concerns is operators are unsure what blade recycling techniques are actually appropriate for their blades. And they're also trying to identify if there is any actual reuse opportunities for recycled or recovered material in their own organization. And I think we've heard some of those opportunities this morning, which was of interest to me. So again, I think I'm just going to plug this supply chain database one more time. If you are of interest in being in our database and are open to sharing data with us and our customers, I think that would be really valuable. We see the sort of transparent sharing of aggregated data as being beneficial for the sector. Thank you very much. I think I'm a little bit ahead of time, but I know we have a break next. So yeah, delighted to take any questions from the audience.
Thanks, Declan. Thanks, Declan. That was very informative. And Ben Lester from EMR Group in the UK. So yeah, thank you very much for throwing our site up on site there. But I think you've encapsulated everything that we're trying to achieve, and we're trying to react to what we expect the industry needs will be, certainly in the UK and Europe, in terms of responding to repowering on scale. So, you know, and also the sustainable aspirations. So, you know, from our perspective, we are looking for all solutions for blades, from repurposing right through to recycling and recovery, but also trying to facilitate the scale of that as well. So 10 turbines, 30 blades, 50 to 60, 100-meter long blades, plus the nacelles and the towers. And also overlaying that is the sustainable solutions for those. So re-rolling steel for the towers, so lower carbon technology. So on your tool, I was glad to see about the carbon side, but also in terms of the locations that can deal with these turbines, is there a facility on the tool to show the permits and the environmental compliance side?
No, there's not at present. I'd be actually really interested to talk to you and sort of learn a bit more about that, and yeah, what that means for you as a sort of supply chain partner, and what our customers maybe we need to know and search for.
Yeah, because we're just pulling a slide together. We've got 8 deep sea ports around the UK. Each is permitted to take the nacelles, the towers, and the blades, so can deal with offshore and onshore at scale. So again, it's that kind of acknowledgement that is a scale issue here as well as a technology issue. So yeah, we'll talk.
Yeah, that's a great point. Thanks.
Thank you, Declan. Very interesting presentation. I think this platform can provide really transparency on the market. My name is Joachim Karthäuser from Wingbeam in Scandinavia. My question relates to the true costs per ton, which you were indicating. I know it depends on the process, but can you give some numbers to it? Basically, my question is, what would be a true and fair gate fee in euro per ton? Can you give some numbers?
Yeah, okay, so you're asking about the gate fee, not the carbon. Yeah.
Well, basically, I think a fair gate fee relates to the true costs, really.
Yeah, I think it's a good question. On gate fees, I think we are certainly uncertain, and our customers are definitely uncertain. I think many of you will probably have had emails from developers in the industry requesting quotes for a gate fee. I don't know what's fair, but the assumption that we tell customers right now is 500 euros per ton for a recycled blade, and I'd be very open to hearing feedback on that assumption from those in the room, whether that's too low, too high, whether it's unfair. But from talking to some select partners in the industry, that's the sort of ballpark we've come to, and that's our default assumption within the product right now.
Thank you.
I have a question, Declan, from my side.
Okay.
So you mentioned that it seems like there could be maybe like a modular enhancement to your platform whereby you can have LCA, incentives, credits, EPDs, things like that, certifications and permits and whatnot applied, which is excellent to hear. What you're trying to provide is certainly a major gap in the industry, so hats off to you. So my question is, downstream to the actors that are involved in recycling, next life cycle groups in the tier supply chain would need this material back in certain form factors, with certain mechanical properties, going into a variety of different intermediates for a new blade, a new boat, a new car, basically, right? So what is the engagement with your team for downstream to the recycling groups, and what type of, if there is engagement, what do they need to see in your platform in order to prove out this full circular economy on like a digital product platform type of initiative?
Yeah, great question. I think, to be honest, we need more engagement with supply chain. I think we are maybe guilty of speaking to our customers who are blade owners, but we do need to engage with the likes of yourself and Ben in the processing sector. Right now, we have an assumption in the tool that blades are cut on site for transport, and then we sort of think of it probably incorrectly as a black box that the vendor or the blade recycler will then sort of figure out the exact size and shapes required for their recycling processes. But I'd be very open to hearing feedback on what's required from different parts of the industry and how we can incorporate that into the tool.
Anybody else? Declan, thank you very much.
Thank you.
Appreciate it. Well, now, similar to wind turbine blades, us as human beings will be decommissioned if we don't have a good intake of food and drink every day. So we're going to have a short coffee break, and please network. Please get contact information for people you would like to speak with, and we'll see you back in just a few minutes. So at 10:50, we'll be prompt and start with the next selection.
Yes, I. No, I have Yes, I don't think, well, I honestly think I should work either my point anywhere. The key is the distance, not the. Yes, it is here, the residue. I will leave you with this, or I will compare it there, yes.
If everyone could come and have a seat.
Did we vote in the?
Now that we've finished our break, if everyone could come and have a seat, please. We will have 3 more presentations before lunch. The first is with Irene and Justine. So looking forward to seeing what they have to say. I think in all these conferences, probably the most popular person might be Irene. Everyone knows who you are, and you've been excellent at demonstrating what Makeen is doing these days. So we're excited to have an opportunity to listen to them share, and looking forward to some very stimulating questions.
Thank you. So this is going to be a shared presentation between myself and Justine, and we are going to talk about the glass fiber remelting proof of concept that we did in the common Decomplace, and also a coming project, II45, that Justine will be telling you about. So Makeen Energy is an old, well-established company being a technology and equipment provider within refurbishing and filling LPG gas cylinders worldwide. And we are more than 3,600 employees. Since 2017, we had a division called Makeen Envirotech. So we're now also a technology and equipment provider within pyrolysis equipment. And that is where we are working with pyrolysis. We started out with pyrolysis on plastic, on household sorted plastic that we produce into pyrolysis oil that then can go back to new plastic. This is also where we have the Decomplace project that I'm going to talk about today. So the Decomplace is both the name of a consortium of 10 organizations that collaborated in the project, also called Decomplace. The aim of the project was to establish value chains. The specific task for McKean was given, and that was investigate pyrolysis as technology to recycle end-of-life wind turbine blades. So the technology was defined, and we had to look into that. We had the focus in the project on the oldest wind turbine blades, the one we expect to see first, and that is glass fiber reinforced thermoset plastic wind turbine blades with a lot of different materials for the core materials, the coating, the sealing, etc. And one of the big results coming out of Decon Blades was what is called the Blade Material Passport. It was invented by our partners Siemens Gamesa, LM Wind Power, and Vestas, and is giving information about which materials you can expect to find in the wind turbine blade, the approximate amount, and also the approximate location in the blade for the materials. Based on the numbers on the composite materials from these blade material passports, one thing is obvious, and that is that the main ingredients in the wind turbine blades are the glass fibers. So our considerations was that separation and use of a small fraction, whatever we could figure out in the process, is not enough to claim that you have found a solution to recycle the wind turbine blades. We believe that we need to find a sustainable solution for the main ingredient, the glass fibers. Also, very soon in the project, we established our first reactor, and I did the first pyrolysis processes and learned that doing the pyrolysis was quite easy. But we had a very reduced tensile strength. We lost the sizing, and it was difficult to find offtake of the amount of glass fiber we could foresee in the coming years that could use the material, and we could have an income for it. Therefore, we decided very early in the project that we wanted to try something else, something that was not tried in previous projects. We wanted to look into recycling or remelting. So my presentation will be about the pyrolysis value chain for decommissioned wind turbine blades, where we did the large-scale trial that we called glass fiber remelting proof of concept. It was done together with the partners in the consortium, and it was partly funded by Innovation Fund Denmark. It was also done with a huge contribution, and we couldn't have done it without them, 3B Fiberglass. What was the trial about, and what was the scale? The idea in the trial is to recover glass fibers from old wind turbine blades and to process the material into a quality so that it can substitute raw material, then add the raw material to a certain percentage in the production of new glass fibers and produce new glass fibers with a remelted content, and demonstrate that the performance of these fibers have the same performance as from 100% virgin materials, so that they can be used in new wind turbine blades, and actually also use the produced glass fibers in new wind turbine blades. The fibers would be assessed by both 3B and DTU for that. So why is this value chain important? First of all, it is a sustainable solution. And we see no degradation at all in the produced glass fibers. So therefore, we are actually opening the possibility for a blade-to-blade circularity for the glass fibers. Also, this value chain can offtake the coming quantities. The issue that we had at the beginning, we couldn't find offtake for the quantities coming. Now we all of a sudden have a solution that can find offtake for all the quantities coming. I'll come back to that. So the scale of the trial is that we have two 37-meter long wind turbine blades that was processed in real process equipment into 9.9 tons of shredded material. Some of that is still in storage. A lot of it, or some of it, was used, and we obtained 1.5 tons of clean glass fibers. And that was then introduced in the production of new glass fibers with remelted content, and 76 tons of bobbin with remelted content was produced in the real production facilities at 3B. As you can see, we did use a lot of material, and that was a lot of the composite material was used to parameter setting in the new established continuous process, large-scale pyrolysis process that we installed at McKean. Looking into the aim of creating the value chain, in reality, we decided from the beginning that we need a continuous operation, large-scale process equipment for pyrolysis, and that's what we introduced when we were ready to produce this material. Also, in the process steps that we had to prepare the material. I'll come back to what that is. We used the material to process setting, and we used it to clean the equipment from remaining materials in there. So the amount of used material versus the cleaned fibers is not at all representative to a commercial process. So what would we like to have as outcome of the trial? First of all, we would like to prove that it is possible to remelt. A lot of people was busy telling us that's not possible. Well, we wanted to prove that it is possible. We wanted to establish a technical and process-wise baseline to develop from, so that from the learning we could design this commercial process setup. We wanted specific to answer these questions. Can we process the recovered glass fibers to meet the defined requirements expected to be necessary to a successful remelting? Can 3B fiberglass homogenize fibers with the raw materials, and can they have an efficient production and same level of breakage during fiberization? And what about the quality of the output fibers? Will the produced glass fibers have the same performance as glass fibers from virgin materials? That's important to answer, both to evaluate the process, but also the quality coming out of there. We also wanted to look into the environmental impact of such a value chain if that was implemented in a commercial process. Pyrolysis is often biased by pyrolysis is using a lot of energy, so that's a bad idea. Or pyrolysis is a waste bin, or pyrolysis is incineration. And that's not true. Let me say, you should never, ever, ever do pyrolysis unless you can obtain good products coming out of it from which you can do high quality products. Then otherwise you should not do it. But that is actually what pyrolysis can. It can separate the materials to products coming out of it, so you can have high quality products. Coming back to the environmental assessment that is being done by our partners. So here, high level, I'll describe what you have to take into consideration. The environmental costs are the resources putting into recovering glass fibers and process them into a quality so that it can enter into the furnace for production of new glass fibers with remelted content that can be used in new blades. So that's a cost. The savings are what you're avoiding. So you're avoiding digging out more new raw materials. So that will be the mining resources, that will be the transport and the processing. And very important is noticing the avoided decarbonization of the limestone and the dolomite. Taking that into account, you also have to look into pyrolysis. We are having two byproducts, if you can say so. We are having the pyrolysis liquid and the pyrolysis gas. And into the calculations, you have to take into the considerations their further processing and also what they're being used for and substituted in the market. So it's quite complicated. We are still awaiting the publications from SDU to come out about details, so what's out for them later this year. But from the internal reporting we are having, we know that we have a positive environmental impact from this value chain. Also, just to tell you about the output products we are having, since this is concentrating about the fibers, but for the liquid, we agree with the petrochemical industry that the main important part of this liquid is to be used as building bricks in the chemical industry. Also, we have a gas fraction that is non-condensable gas, and legislation very much in Denmark is determining what to be used for, but it can be used back in the process. It can be used for central heating, etc. And then we have an ash fraction that can be used as a concrete additive. So going back to the remelting of the glass fibers, what was the approach and what were the process steps? So 3B Fiberglass suggested us to aim high. They suggested that we aim for production of their highest quality product, which is Hypertex material. They also set up the requirements for us to meet for the recovered and processed glass fibers so that it would be able to go into the process. And the definition was regarding a safe remelt and also a high probability of having a performance of the fibers similar to virgin materials. It was their best guess because it was the first time. The requirements we were told to meet was for metals, no aluminum at all, not acceptable. And also for the magnetic particles, the amount must be low. for contamination, we have to remove the coating, the resin, the core material, and we also have to protect it from contamination during the transport and process steps that we are giving. The carbon level must be low, so we need to process them well. And then since the material has to be homogenized with the raw materials, the particle size matters. Knowing these requirements, we then started to design which process steps do we believe is necessary to recover the fibers and end up with a quality of recovered fibers that will be accepted to go into the furnace. Knowing that this process value chain do not exist, we had to look into process equipment that is not designed for this material. You'll see that is a challenge, but also process equipment being used to produce or to process other materials, and that gave us a very high risk for contamination. We had to live with that because that was what we could do. Our starting point for the process was the 2 wind turbine blades and the blade material passport I told you about. Then we had to prepare for the shredding process, and here we cut the wind turbine blades into panels. We knew that aluminum was not accepted, and therefore the aluminum band along the wind turbine blades was removed, together with a big steel bushing and electronics and wires. And that was all recycled with the already existing metal recycling value chains. Then for the shredding process, we originally had a one-step process available, and we were challenged. We were very challenged, and actually we couldn't do it. So we ended up with a 2-step process, and we were still in deep trouble. I'll show you in a moment. During this process, we also had a magnet installed, and we realized that at the production of this, there was used a lot of staplers. Then the shredded material went to the pyrolysis process, and that is actually a 2-step process. In the first step, we are through pyrolysis, removing the resin, the coating, the core material, etc. And we are having what we consider clean glass fibers, but with a thin carbonaceous layer. The thin carbonaceous layer is then removed in the second process, in the post-process. And what we are obtaining is what I call Santa Claus's beard, very white, shiny glass fibers. Then we sent this material to the milling operation because we needed to transfer it into powder so that it could be homogenized with the raw materials. And that was unexpectedly easy peasy. That was the easiest part of it all. Now, this was the original scheduled process steps to go through. And we, back then, when we planned the trial, had agreed on a go-no-go gate in order to evaluate if the material could enter into the furnace for remelting, and we had a no-go. We had a way too high content of magnetic metals, and we had copper in there. Investigating, we found out that the copper came from electrical wires in the shredder that was previously being shredded in the shredder and was hiding during inspection. Even though we processed composite material and put that aside to clean the equipment, it was still in there. And for the magnetic materials, we believe that came from wear and tear during the process steps that we had. So, we have been spending a lot of months and money and energy and resources on this. We were very frustrated. So we reached out to our networks, and we were lucky finally to find a company down in Munich that would give it a try to sort it. Now we were having a glass fiber powder, and that was one of the issues that was creating difficulties when we went to sorting. But they air table sorted this material, and they did it so well, it was working so well that we, at the next go-no-go gate, had a clear go, and it was even considered a low risk to do the remelting. Then the material was sent to 3B, and there was a batch correction so that they analyzed what is the composition of recovered glass fibers, and then taking that into the account when they did the mixing of the raw material with the recovered glass fibers. Then this material entered the furnace, and the production of glass fibers with remelted content started. That was produced with 2 different sizings, one for LM Wind Power and one for Siemens Gamesa, since they are going to use the glass fibers in production of new wind turbine blades in real life. The fibers was then assessed by 3D DTU and compared, and it was both single fiber testing and composite evaluation. But Justine will tell you more about that in a moment. Then the fibers went to AVEVA and will then be used in production of new wind turbine blades. So now I'm going to show you what actually happened in this process, but be aware that equipment is not designed for this material, and also we see contamination.
Today we are threading our wind turbine blades. All the threaded material will come to McKean in Randers, and here we will process it and separate it in oil, gas, and fibers. And then the fibers will be milled and then sent back to a fiber factory.
Right now, we arrived at the 3B facility in Birkeland in Norway, and the reason that we're here is that we did all the process steps that we, in the partnership with 3B, have agreed to do to recover the glass fibers from the old wind turbine blades. A few minutes ago, we loaded in the recovered glass in the process in Birkeland. So right now the remelting is being performed. And it's very exciting to see what is going on and gain the learning from the remelting as well.
So 3B, we were approached by the McKean and the Complete partners to prove, that this recovered glass from the McKean process could be recycled through our furnaces. And we were very interested because we believe that's the future way of recycling those large amount of used glass fiber. The quantities of blades to be recycled will grow in the future. And so this will be, a problem to recycle those blades and especially the glass fiber. So the potential of this project is really to prove that with 25 years old material or 30 years old material, you can really produce virgin material with, let's say, the original properties or even better properties, the properties of the actual fiber, which is going into the blades.
it was with challenges and a lot of learning gained. So no matter what is going to happen with the quality of the outcome of the fibers, we learned a lot. We're quite sure and confident that it is going to be a high quality fiber, but still a lot of learning has been obtained from this project. Afterwards, the fibers will be assessed by both 3B and DTU Wind Energy to make sure that we did obtain this high quality glass fiber that we are aiming for in this project.
Yes, and that's where DTU participated in the glass fiber remelting proof of concept in testing the fibers. So we got several samples from 3B fiberglass. So all the dots you can see on the curve here are 25 kilos glass fiber bobbins. They were produced at different times during the production of these fibers, and they all include a different amount of recycled recovered glass concentration. So we tested 4 samples, but today I'm going to present number 1 and 2, which are probably the most interesting ones. That's the one with the highest amount of recovered glass and the one without any. We did a single fiber tensile test, but we also used the fibers to produce new composites that we then tested in the fiber direction and transverse to the fiber direction. This is the equipment we use for single fiber testing. It's a semi-automated machine, and what is very nice about it is that you can test hundreds of fibers, and you can also get the actual cross-sectional area of your fibers. And that's very important because that gives you a very accurate value for the stiffness, the Young's modulus of the fibers. And those are the results. So as you can see, we tested at least 100 fibers for the 2 samples that I just mentioned. So the orange sample is the, you could say, the reference fiber. That's the fiber that does not contain any recovered glass. And the green sample is the one with the highest amount of recovered glass. So the highest amount recovered glass was around 1.96%. And as you can see, the Young's modulus, the max stress, the strain to failure, and the density, they lie very nicely on top of each other. There is virtually no difference between the 2 samples. So with this very high performance glass fibers, we decided to continue the experiment and prepare some composites. So we wanted to have some unidirectional fiber composites. We used filament winding techniques for that, and vacuum infusion using an epoxy resin. And here are the composite properties. And as you can see, the properties are identical or almost identical. So we cannot see any difference in the fibers with or without the recovered glass inside the fibers. The performance are the same, and they also correspond to what 3B fiberglass is advertising for their Hypertex product. So that's great news.
Yeah, so coming back to the questions at the beginning, we wanted to answer is that the answers are that yes, we can recover glass fibers and process them into a quality so that they can substitute raw materials. And yes, 3B fiberglass can homogenize with the raw materials, and yes, it can have an efficient production. And yes, the fibers do have the same performance as from 100% virgin material. So you could say that we showed in a low substitution rate, and you're right. We had a time constraint, meaning that we did not have time to process more recovered glass fibers. But with the, we did not see any indications at all telling us that we should not be able to go much higher in the substitution rate. Looking into the composition of this recovered glass fibers versus the composition of the glass fibers we were going to produce, the Hypertex, we would, with only twisting and looking into the ingredients, been able to go to a 15% substitution rate. In order to evaluate what is the necessary substitution rate, I have looked into numbers only for all of them from Wind Europe, and I have looked at the build out of wind energy versus the decommissioning of blade weight and calculated into amount of glass fibers, and comparing those will give us the maximum necessary substitution rate. That's in Europe, and that's between 6 to 15% in the years to come. And that is if all material come this way, no second-hand market, no spare parts storage, no reuse, no other recycling solutions will take some of it. If all come this way, this is the maximum substitution rate that is needed. And that is actually preferable because producing glass fibers is a sensitive process. So having a low substitution rate as necessary is giving a lower risk. And also we have time to learn and to upscale for a higher substitution rate in case that is needed. So the conclusions from the trial was that we see no degradation, and actually it's opening the possibility for blade-to-blade circularity if that is what legislation wants. We can also be on our way to 100% recyclable wind turbine blades, so remelting is possible. LCA results, we're still waiting for the publication from our partner SDU, and this value chain can offtake the quantities in the coming years. But as I also said in this introduction, the aim of the decom blades was to establish value chains. So what does it take to establish value chains, in our opinion? Well, first of all, there are other projects than decom blades. There are other technologies, there are other solutions. We heard about it today, we will hear more these days. And I think we are all interested in hearing about that and watching the results on, and especially the environmental and economical assessment of those. But no matter which choice of technology or solution you're looking into, to be an investor, to be a realistic, should I invest in this? Should I continue my work in this? I believe we can agree there are two things that we all are lacking. One is a thorough study on the quantities of input material divided into what, where, and when. We know from decom blades that postponing the installation year by 25 years is not a good estimate for end-of-life wind turbine blades. There is a large second-hand market. We also heard from Vestas. We know that some wind turbine blades get much older than what we expect from here. And also some markets suggest to repower earlier than the 25 years. And then also production waste is mentioned as a high contribution to the input waste. But looking into the details, it shows that foils, packaging material, and tubes and molds is what is most of in there, and that requires another recycling process. And then also the cut-out glass with recycling. Please put that in a group by itself because that requires a minor process. And then also include studies for similar materials and industries in there. The other thing I think we are lacking, or at least we are lacking, and I think we agree, I think we all expect that the legislation will change from allowing landfill to something else. But what will the aim be? What will the aim be, especially on circularity, but very specifically on it will be a requirement on sustainability, but what about circularity? Will it be accepted to degrade the material? Will it be accepted not to keep the performance, but having a bunch of material? Or will it be a requirement that we should keep the quality of the material out there? Will the requirement come country by country? Will it be the same in EU? And what will the tender requirements be? We saw very strict tender requirements aiming for a full circularity solution. But no matter what, whoever we are, I think all of us need a study of the quantity, and we need something about legislation in order to do a realistic business case assessment. And a realistic business case assessment, at least seeing a business out in the horizon, is what is needed for people to invest and continue putting resources and energy into this, is my opinion. But once getting there and you are believing in one of the solutions, I'm also quite sure that the pre-processing is going to be involved in whatever process is going to happen. So that really needs to be an efficient process handling the dust issue, and that will be applicable for everything. If the pyrolysis value chain will come, we will also have to look into the sorting process and also reach out to the off-takers of the glass fibers and the liquids, asking them to prepare their production to take in the materials. So the conclusion from my side is that to make this happen, we need knowledge about the waste streams, input material, we need something about legislation, and then we need to collaborate. So.
And collaboration is the next topic, because I'm going to talk about a network that is called the IEA Wind Task 45. So this is a network, this is not a research project. And the topics that we are discussing in this network, well, the network is about enabling the recycling of wind turbine blades. Irene, you just listed some of the topics that we are actively discussing in this group. There are waste quantities, there are economics and planning at end of use, there are policy and regulation, and there are value chain perspective. So the idea is really to discuss how we can join forces to solve these issues that are actually common to all of us in order to enable the recycling of wind turbine blades. Because no matter what technology you are using, you will face this discussion: how much waste do I have next year? How do I plan for the next year knowing that I don't have the waste? And what about policy and regulation? How does it look like in a couple of years? So we see a lot of common issues, and therefore we believe it's a good idea to collaborate on those. So that's the purpose of the IEA Wind Task 45, is to identify all of these barriers, find levers and mitigation strategies for the implementation of large-scale recycling solutions for blade. And we believe that the solution or the enablers needed to enable the recycling of wind turbine blades, they are not only technical solution. You need many other perspective, life cycle perspective, a value chain perspective. You need to look into the legislations that play a huge role in this discussion. Environmental impact, of course, for example, and economic feasibility. So the network has existed since 2021, and we just ended first phase, so where we were roughly 76 participants from 44 different organizations, spread over 9 countries and also including Wind Europe. It's not a European network, it's an international network. So we also have people from the United States joining this network, and the network is also open to Asian participants if they are interested. So the objective for the network was to, based on the learning that we can get on how to plan for the next year, how to estimate waste, can we establish best practices on how you should manage your end-of-life blades? And we are on the way, so we are not finished yet. We don't have those best practices yet, and that's why we have a second phase starting end of November. But we do have some key results so far that you can find on our website. I think the QR code, unfortunately, doesn't work. I see some people raising the phone that I will present now. So the key result number 1 is a list of action to transform recycling technologies into functional value chain. As we were speaking with all the experts around the table and involved in the network, we realized that recycling wind turbine blade is not just a one-stop shop. You really have to take into consideration all the pre-processing you have before and maybe also after your recycling technology. So we reviewed the state of the art, considering this, the dimension of the blades. That helped us understanding, uncovering the pre-processing step needed for some of the solution. If you're aiming to build a bridge, then maybe you don't need to go down to fraction in order to do that. But for some other applications, you need that. Then we did a workshop facilitated by the University of Leeds and Anne Wellentorf. an expert in circular economy, where we together analyze the drivers and barriers in order to shape those recycling technologies. And they could be very different. They could be legislation-based, but they could also be data-driven. A lot of the discussions we also have is what is in the blade and what do we need to know and what can we get from the blade OEMs. And based on that, we defined a list of actions, political actions, technical actions, social actions, that in order to enable the recycling of wind turbine blades, taking into consideration this value chain perspective. Okay, I'm going to skip that for time reasons. The key results number 2 was to establish strategies for future wind turbine blades, taking into consideration the recycling needs. So really understanding the needs from the recyclers and try to recommend strategies for future blades. So we have all the experts in the network from recyclers, but also blade manufacturers. So we reviewed together the current blade materials and innovation. Then we went on by discussing and interviewing the recycling experts, understanding what their needs was, and then together during a workshop again, we recommended or established strategies for future blades. So you can see here a list of 8 needs that you can consider during the design phase. We try to get inspired from those in order to formulate new strategies. And we came up with 2 concepts. The first one is design for recycling concept, and the second one is a design for repurposing. And this content is available open access on Zenodo. And the last key results for the first phase of the IEA Wind Task 45 is looking into policies. And here the result is a proposal promoting recycling of blades through policies. So we first reviewed what was existing and tried to discuss proposals, how to push for blade recycling from this side. So we formulated several proposals as well. But as I mentioned, the work started by reviewing what was existing out there. We separated into hard law measures, soft law measures, and tender requirements, trying to have the whole word into the image. This is also available. And as I mentioned, we are moving on to phase 2 very soon, kicking off end of November. Where we will have a list of topics that you can see here on the screen in the focus. I would say the one that we are expecting at the end of the task is really this best practices. So that would be number 6, shared vision on blade recycling, how to perform blade recycling if you're using this or that technology, what you should take into consideration, what you should be careful of, and so on. So that in order to get there, we'll work on better waste predictions. We'll work on data to support the recycling, harmonize policies, economic viability, and we'll also work out a technology roadmap. And this is how the team looks like for the phase 2. So Derek Berry, that is also present today, and I will be coordinating this network. And then we have a crew, a European American crew to lead the work packages and the subtasks. I'm not going to name everyone, you can read for yourself. Yes, and also just mentioning, we are kicking off end of November, but we are having a small conference as well on the sustainable wind turbine blades, discussing recycling, but not only, also integrating, for example, policy perspectives, also having in mind this multidisciplinary approach. Thank you.
Thank you both for a very stimulating conversation on this, and well done. Hats off to you for what you've been able to accomplish. So I'm sure there's quite a few questions in the audience.
Yes, hello. My name is Reinhard Kessing, Kescon Engineering. First of all, I'd like to just clarify, when you did the comparison of the fibers, you know, the virgin glass fibers versus the one with the content, you mentioned, and maybe I misunderstood, that the composition was 1.96% of recycled in the test comparison. Is that correct?
Inside the fiber.
Inside, yeah.
Inside the fiber.
Yeah, so 1.96 was only the recycled content. Okay, that was question number one. So it was 98% virgin still, even in the one that you call recycled.
Correct.
How can you, with all these steps that you're talking about, with pre-cleaning, cutting, and everything else, how can you be profitable in making these fibers? Aren't you losing so much energy, time, effort, and money that this will never make a business case?
It requires some quantities, but still, this was the first time, and we had to transport and use process equipment. Of course, to make this a viable business case, you will have to have a one-line process only doing this and with the capacity made for the quantity that the process is designed for. So since this was the first trial and we need to protect the material, we see no solution other than having a process set up specifically made for this.
Okay.
Of course, the gate fee will be higher than it is for landfill, but not surprisingly, not tremendously higher.
Okay, all right. So it's basically still a trial stage. It's not
Yeah.
industrial ready.
It's not a commercial process yet. No.
All right. All right. Thank you.
A question from my side on your resin recovery. Where is that in development currently? And do you have some other partners in industry that you're working with, or even with DTU on the resin recovery side? And how's that going?
During the project, we actually work with the 5 different petrochemical industries, actually them reaching out to us, learning that we were working with this. They were very interested in having samples and learning about it. And all of them came back and said this should not be considered a pyrolysis oil for incineration. It should be used as a chemical building brick for the chemical industry. However, that will require them to put resources in to develop their process. And that's where the story ended, because every time they requested this thorough study on the input material waste stream for them to see the business case out there. So for the glass fiber industry, we had a lot of collaboration, actually a lot of others looking into the fibers and the resin. But for the petrochemical industry, that was a barrier, that not knowing those quantities. So everybody agreed that that was a route, but also they agreed that they need to do something to implement it into their process. And since the project stopped, ended by the year, then we are not there yet.
Over in the front.
Thank you. You mentioned that the pre-treatment or the mechanical recycling part process chain was not optimized for your requirements, which I understand. I mean, you use the commercial technologies, but after you run the process, after you test the material, after you calculated the costs throughout the process chain, what would be the step of the process that is more critical from your point of view, and what would be the step that you would improve, and in which direction potentially? So what are your improvement suggestions on the overall process chain?
Yeah. We are a technology and equipment provider within pyrolysis. So of course our focus is on pyrolysis, whereas we would like the ones knowing about pre-processing to work on that. So we are not looking into the pre-processing process because others should do that. But we can see what we did was not working. So we will, I was interested in what you are doing in other projects, because you came very far on your process steps, inventing different solutions to do that. So we'll put that there. For the pyrolysis part of it, that will be, you know, the pyrolysis was very easy. Transporting the huge amount of solid material, having a different weight coming in with the resin, then being a little sticky during the process, and then at the the end, as I say, I think gravity does not exist because it cannot fall anywhere. That's where we have to work on that. And then, of course, transfer the heat to the material. So development and upscaling of the pyrolysis process is where we will put our effort. But my message is also we need the whole value chain to be efficient. Otherwise, this is not a good solution.
Thank
you. Yeah.
Thank you.
Julian, Struck team. Just to follow on the gentleman question, what volume of feedstock do you need to make your line with a viable business case? Is it 10 kilotons, 50 kilotons, 100 kilotons?
Yeah, we looked at calculations similar to what we know from our plastic pyrolysis process in order to have some numbers to compare with. And we looked into numbers of 16,000 tons per year for a plant, give and take. Yeah.
Thank you both for the nice presentation. My question is to Justine about your network. I was wondering how open or who's the target audience for your network? Is it also young researchers or young?
Yes, we have researchers and industries joining. And I think if we want to make guidelines that are useful for everyone, we need to have both. We also have state organization and associations. Yeah, so we welcome everyone.
Thank you, thank you.
Time for one more.
Thanks both for the presentations. Eric Dalis, Owens Corning again. So very exciting indeed to see that recycling composite glass fiber through remelting is an option that we do at Owens Corning as well, that we are pursuing. So very exciting. Now my question is very specific on the blade that you have taken. Were there blade at end of use or were there blade that were built on purpose for Decom blade?
That was blades in the fuse. It was old blades.
So meaning that the glass that was not put in for the purpose of the blade?
No, it was old end of life wind turbine blades. Yes, real case. Yes.
And maybe we can say that 3B analyzed the glass and they could say it was probably e-glass fibers, but that's very broad.
So with the project with 3B that was successful at that stage of development, that having a continuous recycled fiber is quite novel. Are other industries like marine, automotive, groups like this, aerospace, looking at this as well? Or is this mostly just wind focused at this stage?
To our knowledge, it's wind focused at the stage. And of course, 3B fiberglass are supplying to other the other industries as well. So that could be interesting there. I know the focus is within the automotive industry as well, but we have not been working on that. We have, and I think the main reason is that we have been focusing on the thermoset plastic, whereas thermoplastic is what is being used in there. And that's not an issue. It's just a matter of the reactor we use for the pyrolysis process. So it's a similar process. Yeah.
Thank you both very much. So our next talk now is by Sandro, Senior WTG Engineer with RWE, and Marta, Chief Technology Officer with Renner Cycle.
Hi, hello, good morning. We are going to make a together presentation. My name is Marta. I'm coming from Renner Cycle, and I have been working in the wind industry for almost 18 years, mainly in the design part. I was designing wind turbines, and now I am in the end of life solution. So I'm kind of an example of circularity as well.
Good day to everyone. My name is Sandro Di Noi. I see a lot of faces I know already, but also new faces. So congratulations to the organizer, which attracted new people. And I work actually in RWE since 2 years. And I joined the wind industry back in 2008 as a young aerospace engineer. And as Marta said, so we are closing the circle here. Hopefully we will have still a long time to go before to finish our experience. So today this is a very quick preliminary agenda. We will speak about who we are, divided in two parts, and what are the challenges for us as operators. And we will introduce a Renner cycle as well as a waste to fiber solution. Very quickly, RWE started in 1998, a very well-known German company based in North Rhine-Westphalia, not that far from the border with the Netherlands. And we basically deliver electricity to the countries where we are located at. Last year, we celebrated 125 years with a very nice party. And and today we are divided in 5 main core business. So the first one is offshore wind. The second one is onshore wind and solar. That's where I belong to, which means usually it's called OBEA, which means onshore photovoltaic Europe and Australia. Then we have the flexible generation, supply and trading, coal and nuclear. Let me say that for the first 4, we do cooperate together. So flexible generation work with us in onshore wind and solar to develop hydrogen projects, producing hydrogen directly from the wind turbines. And that's something that it's happening here in the Netherlands as well, in Eemshaven. That's the pilot project we are running there. At the moment, we have more than 35 gigawatt installed in green capacity all over the world. Here, very quickly, it's a build-out plans until 2030 for onshore wind and solar. So we have a very challenge time in front of us. And we aim to reach 14 gigawatt pro rata of onshore wind turbines in Europe and Australia. As you can see, we have already 8.6 installed capacity in 2023. Now it's already close to 12 at the end of 2024. And we still have to grow a lot up to 2030. Same for solar. And that's why, let's say, when we go back to what we have already, there are many turbines out there which are reaching the end of lifetime. Mostly due to the challenges in having new projects up and running. You know how the situation is in Europe right now. There are many projects in many countries who are basically stopping the development in renewables, or not stopping, just reducing the push on the acceleration of the renewable energy, and that is affecting us and our plan. But at the same time, we have so many turbines which we need to replace with new one, and that's why we decided in RWE to invest in green energy technology from 24 to 2030, roughly 55 billion euro. And that's why because we will have at the end of 2030 the green capacity of 65 gigawatt combined with offshore, onshore, and solar. Then in these slides, what we would like to express is that we are committed to reduce the 1.5 degrees Celsius in emission. And that's why we already define a path to reach net zero target already in 2040. That's very complicated, I have to admit, because all the turbines which we buy already today are demanding a lot of CO2. Just imagine, as per today, we are building sites in south of Italy as an example, but the blades are coming from Shanghai. And that's no way that the OEM will change this mindset. For us, it doesn't change our life because we pay the turbine the same. Either they're produced in Europe or in China. That's something which is not good for the environment because those blades have to travel at least 6 to 8 weeks to reach the final destination. And we are talking about mainly, if we are really lucky, only 27 blades per project, but can go up to 40, 50 blades. And we are talking about 80-meter blade length. So So we do our best, but we would like to have a joint venture mindset also with the manufacturer to say it's not only our call to reach 1.5 to keep the 1.5 degree emission. And that's why we keep working on it, and the blade recyclability is one of the main targets. Here, what we would like to show to you is that our circular economy policy is public. You can go on the link or on our website, rwe.com, typing circular economy policy in the search, and you will get the document available for you. What we know already is that Wind Europe will call for continent-wide landfill ban on turbine blades. That's why I have to admit we already started. So all the blades which are going to be decommissioned or the broken blades, they are already banned internally to go on the landfill. What is happening today, they're just, cut in pieces and burned. That's what is happening to the blades actually. And I have to be honest, we are quite lucky because the old blades, they have mostly no carbon inside. So we are talking about balsa, glass, and resin. The new one, I see it a little bit challenging also to cut them in pieces because of the pultruded planks inside. That's why the circular economy policy plays a role because we make it public for a reason. We want also the OEM, all the stakeholders in the wind industry to be aware of what is the demand we need to fulfill, in particular from the EU, but also in other countries. Even in US, things seems that they are changing. Here is the challenges we have as operators. As you can imagine, we have a lot of blades. This is an example of a dismantled wind park. And we also try to reduce the impact on CO2 emission to have a lifetime extension of our project. That's not always easy. That's not always possible, mainly because many of these sites, which are already more than 25 years old, they already achieved the design lifetime of the turbines. What is the most affected part of the turbines, in particular in sites where 25 years ago no one was thinking about turbulences and they were only thinking about, okay, we can install the turbines, the process was easy, the money were there, so we just installed the turbines. Today, what we are checking is that after 25 years, we see into the blade in particular very, very elevated signs of fatigue on the blades, which makes them breaking in pieces. And that's why for safety, we decide to shut down the site and anticipate the repowering of those sites. Of course, that means we will have a lot of blades available already for recycling, hopefully, but we are not there yet. That's why we are analyzing the possible option, and Marta is here with us today to show what our ideas are and how we are cooperating together. And then we are also assessing all the possible application of the blades. The example in the picture, it's something which has been done in Germany, where part of the blades will be used as a noise barrier on the highway. And then, we also would like to build know-how and establish industrial partnership to support the end of lifetime projects. At the moment, just for you to have an idea, we didn't reach the level where the 40-meter blades are reaching the end of lifetime. We are still at 25, 30, 35. But that's coming. It's just 2-3 years in front of us, maybe 5 maximum. I have to admit that the OEM are moving in such a way like the blade material passport, which was really helpful for us, but they are only there to deliver this document for the old blades. So if we will have a brand new turbine, 2-3 years old, collapsing, we will still not have that document because of the intellectual properties. Of course, you can imagine, we don't need to know how the fibers are positioned, how the fibers are, I don't know, H glass, E glass. We just need to know the amounts in mass, because that's what our partners recycling blades would like to know. At the moment, we only know the blade mass totally, the set, and that's it. And then we need, thanks to the support also of DNV, we are able to estimate sometimes what the level are. But, without a good cooperation, without breaking barriers, it will be difficult for us to support companies like Marta to move forward with this technology. And with these slides, we would like to share with you, we invested, so RWE Obea, the company where I belongs to, invested into Renercycle and Waste2Fibers for full circularity of wind blades. In particular, these are projects for us, as also has been said in the last presentation, which it's becoming mandatory for us. We all know what is coming, what will come from the European Union in Europe. Maybe in other countries, it's a little bit less, but we already, even in offshore, we have Kaskasi, where we have the Siemens Gamesa blades made up with the recyclable resin up and running. We've been the first one installing those blades. But again, if one of those blades should be dismantled tomorrow, we don't know where and how to recycle that blade. So we got the blade, but there is not the possibility to recycle the blade actually, and not even in 5 years. Even if we try to do it, there is no way. So we would like to switch from a fancy exercise to reality. And for sure, that's where we all need to work together. And we hope we can really reach a point where also the OEM together can reach an agreement. So for us, as I said, the blade passport will be already a very good starting point. Thank you. And with this one, I give the remote controller to Marta.
Okay, well, first of all, I would like to introduce Renercycle, my company, that is a startup. It's a small company, but with a big mission. Our mission is to close the loop in the wind industry by providing sustainable solutions that reduce waste and promote the recovery and reuse of the raw materials, keeping them in use and out of the landfills. In short, at Renercycle, we are not just in the business of wind energy, we are in the business of creating a sustainable future for the wind energy. Today, we are focused in 3 key business lines. The first one, wind turbine decommissioning and transportation of turbines that have reached the end of their life cycle. The second one is reconditioning, repairing, refurbishing wind turbine parts to give them a second life. And finally, the third one is to recover and recycle valuable materials. While recycling materials like steel or copper are quite straightforward, recycling wind turbine blades pose a significant challenge, not only for the wind industry, but for the composite material sectors in general. And that's why we have partnered with Acciona Energía to cover the gap on the right, and just to scale up a dedicated solution for blade recycling at our Waste2Fiber plant that I will explain in detail in the further slides. So let's take a closer look at the Waste2Fiber solution developed to tackle challenges of blade recycling. Waste2Fiber is a continuous thermal recycling process that separates the resin from the fibers, but heating the material at low temperatures, with the distinction that it involves an additional oxidizing step to remove carbon residues and to obtain a more efficient fiber recovery and higher fiber quality than those achieved with the traditional standard pyrolysis at high temperatures. The thermal degradation facility for the composite materials, as well as the associated recycling process, has been patented by Acciona, and you can see on the screen the application number, and you can find it in the internet as well. And here is how it works. The solution is built around 2 hermetically sealed reactors that carefully control atmosphere and temperature conditions. The process itself is carried out in 3 stages. Stage 1 begins in a sealed rotary cylindrical furnace where the materials are gradually degraded at low temperatures and in a low oxygen environment. In stage 2, another different rotatory furnace maintains a controlled oxygen atmosphere, enabling further thermal treatment. And finally, step 3 is focused on fiber separation and sizing to optimize fiber use in subsequent manufacturing processes. And where are we now? The important thing is that waste-to-fiber solution has reached technology readiness level of 7, meaning that we have successfully carried out control tests in our pilot plant and achieved all the critical milestones. The technology is currently in a pre-commercial phase, but we are advancing quickly towards a full commercial deployment. The next step will be scaling up at a facility in Navarra, in Spain, in the north of Spain, that we are already building. As you can see in the render, to recover the composite materials from the blades, the main warehouse will be divided in 3 different areas. A first area for initial preparation of the materials, screening and material segregation. A second is an area where the thermal process itself will take place. And finally, an area for byproduct recovery. Looking ahead and looking at the numbers, we can see that 2026 is the number for us, is the year where the facility will be fully operational, and it is expected to process 10,000 tons of composite materials per year. The facility will be powered mainly by renewable energy, reducing its carbon footprint. And environmental-wise, recycling with this technology will cut emissions by 66% when we talk about glass fiber and up to 95% when we talk about carbon fibers, compared to producing new materials. But of course, as all the solutions that we have been seeing today, this has as well pros and cons. So here in this slide, you can see a table that we have prepared to compare it with the mechanical solution and for recycling the wind turbine blades. We have chosen the mechanical recycling for the comparison because it is the most mature and cost-effective method that we have in the market today. It involves breaking down blades into smaller pieces through shredding, crushing, or milling. And this is practical and accessible, this methodology, but it mostly produces lower quality materials suited for downcycle application like fillers in concrete or asphalt, placing them lower in the waste hierarchy pyramid. On the contrary, the thermal process preserves the original properties of the fibers, producing high-quality fibers, high-quality outputs, such as oils, non-woven materials, and high-quality glass and carbon fibers that can be reused in multiple applications in different industries. On the other hand, the mechanical method has a very big advantage that it requires less energy and fewer specialized resources, making it accessible and straightforward for many facilities. And this is not the case for the thermal process because this is more energy intensive and requires a specialized equipment that can drive up the cost. And this is a disadvantage, of course, of the methodology. But however, recent optimization in the process and the use of a low temperature process can reduce these energy requirements, making it more viable. Although mechanical recycling remains the go-to method in the market today due to the cost and simplicity, the increasing focus on sustainability is pushing us to look beyond just cost and consider other methods that are higher in the pyramid. And well, I will pass very quickly through these slides because we are talking about business opportunities that have been already commented by Marcelo very well this morning. So, well, the business opportunities are clear and we have already discussed about them. We expect a big market for the commissioning of onshore wind farms over the next years in Europe. And this comes with a big opportunity. And one of the reasons for the current immature business case for recycling composites is the lack of sufficient market demand for the final recycled fibers. However, with increased use of composite materials in different industries, such as the wind energy, the marine, aerospace, there is now an urgent need for sustainable solutions, as we can see this morning. So with the waste-to-fiber solution, we can repurpose recycled fibers coming from the commissioned wind turbine blades and then produce strong, lightweight, and non-structural components suitable for use in vehicles, aircraft, and ships. And finally, despite all the opportunities commented before, the reality is that up to now, the place has been most landfill or incinerated. However, landfilling is becoming something unacceptable in Europe, mainly due to the lack of space. And there are different initiatives European directives and regulations that support this idea. For example, when Europe has called for a Europe-wide landfill ban for blades by 2025. So therefore, we see that regulation and also the public opinion underscore the urgency towards sustainable solutions, and they are pushing the industry towards to adopt a more cleaner and greener solutions just to recycle the blades. Any questions?
Thank you. Nicholas from Siemens Gamesa. I would just like to ask if you could comment or elaborate why you would need to, in the short term, recycle a blade from Kaskasi when it's a completely new wind farm.
No, wait. I touch wood, so I hope we don't have to recycle them, but that's something that theoretically can happen, right? So that's why if it should happen, we don't know how to recycle them, even if they are recyclable. That was the point.
Okay, sorry. Thank you.
You're welcome.
Can I go from here? Here in the middle.
Oh, yes.
Nice to meet you. I'm Gianmarco Gioffre from Wind Europe, Sustainability Advisor. I have a question. I mean, maybe you can elaborate a little bit more about the point on the prices of Chinese wind turbines, if I understood correctly, because you said that the prices are almost equal. And I mean, the narrative that we've been hearing quite a lot in Europe, at least at Wind Europe, and that's what we've been advocating for, is the fact that wind turbines produced in China, due to multiple reasons that you probably also are quite aware of, are costing 50% less than what we pay here in Europe. So I wanted to know whether where these numbers were coming from. I mean, the Commission will be starting an investigation on this. So I wanted to know where these numbers were coming from. Thank you.
Yeah. Let me clarify. I know what you're talking about. Let me say that I was referring to the fact that we buy turbines from European manufacturers only today. And for us, the price is not that much affected from where the turbines are coming. So we sign a contract in Europe, but the components of those turbines are coming from China. So the potential difference with the Chinese manufacturer, that's another story. So that's what I guess we all know where this could lead to. But at the moment, RWE has only one wind farm in Italy with Chinese onshore turbines. It was really a rare case. And they are only, if I remember properly, there are just 7 turbines we have from a Chinese manufacturer, which are 5 years old now. So the prices I was referring to, that we pay the cost as if the wind turbines is manufactured in Europe, but in reality, the components are coming from China. That's what I meant.
Okay.
But that's good for you also to investigate, because, you know, we need some regulations here, and at the moment there are not. You know, we have the first offshore wind farm in Italy with Chinese turbines. You know that Belleolico is the name.
I'm Italian, so I'm particularly aware of the
That's
stories.
why.
Okay, many thanks.
Thank you.
Hi guys, over on your thanks very much for your presentations. I've got a question for each of you. Marta, maybe first of all, congrats on raising funding for your startup and securing those partnerships. What markets do you see your blades coming from for your sort of quoted capacity going forward in 2026? And then I'll maybe get the question out first, sorry. And then Sandro, on RWE's investment, are you looking at investments in other sort of blade recycling facilities globally around the world?
Okay, regarding the first question, we are expecting to receive blades from the Commission wind farms, mainly from the south of Europe. And we are focused on Spain, firstly, because they are the average age of the wind farms in Spain are really high compared to other European countries, and we are going to be located there. But we are open also to receive blades from other countries in Europe, but right now we are focused on the south of Europe.
So answering to your question, as I presented, we are basically funding only two main projects, and that's for a particular reason. As Marta said, we actually have many sites reaching the end of lifetime. The old turbines, we are talking about more than 400 blades reaching the end of lifetime. And that's why we decided to join the partnership with the company that Marta represents. It's a matter of business. You know, we have one in the south, one in Spain, one in Germany. We are also in the IEA task 46, if I remember the number properly. And we are looking to all the possible solutions.
Hi, Nina from Vestas over here. I have a question to you, Marta. In the comparison to mechanical recycling, you also listed a number of byproducts. Are you also looking into routes for these, or are you only focusing on the fibers?
Sorry, focus on the last part of the question.
Are you also looking into routes for the byproducts, or are you only focusing on the fibers?
We are only focused on the byproducts. We are focused not on the fibers, as commented our colleagues before. We are not focused on using them in new wind turbine blades because after the mechanical test has passed successfully, but we have our concerns about fatigue. So in this sense, we propose the use of these fibers for the byproducts only in non-structural components.
Thank you. Marta, one question from my side. Thanks for the very interesting presentation of your technology. Are you already working with potential off-takers of your material in output? And if yes, can you give us a hint on the main application scenarios? You said no structural parts, but in what sector? And yeah, what scenarios? Thanks.
Well, the project is led by Acciona. And I know that just to invest in this project, they prepare a business case. I don't have the numbers, sorry, but I know that they have in contact with at least the aerospace industry, Airbus, and also with the automotive industry, with different brands. When we are talking about the components, we are talking about the interior panels, the floor in the aircraft, for example, and this kind of components that are not part of the structural of the vehicles or of the aircrafts, but still they have a big portion of composites that could be used there. And as well, I know that, well, I didn't explain because of the time, but there is an European directive for the automotive sector that they were gonna be it's compulsory just to use 25% of recycled plastic in the vehicles. So in this sense, for the bumpers and these kind of components, they are talking about with these different industries. As far as I know, Airbus and different brands of the vehicle and the automotive industry, just to give this second life to the composites.
Thank you.
Thank you both very much for your presentation. We appreciate it. So our last presentation before lunch is Professor Vasilios Koutsos, Deputy Head of Research Institute for Materials and Processes, School of Engineering, the University of Edinburgh. And this will be virtual.
Many thanks. Can you hear me and see my presentation?
We can hear you.
Can you see me now?
We don't see you yet, but we can hear you clearly.
I have the video on. I start my video again. Can you see my presentation at least?
Yes.
Yes, it's okay. So I think I can proceed. Thank you for the invitation. I'm sorry that I couldn't make it to Amsterdam. and to the Netherlands. I have done my PhD in the Netherlands, so I'm very much fond of the country. It's really pity that I couldn't make it up, but thank you for the opportunity to present our work virtually. So I'm going to try to connect two big problems in the renewable energy industry, the wind turbine industry, the recycling of wind turbines with leading edge erosion, a very big problem of wind turbines. I will start with that. So leading edge erosion of wind turbines, a very big problem of wind turbines. The erosion that happens with time, there is usually, let me try, I'm sorry. Let me try to, I'm sorry again. No. I'm trying to get the pointer. Here it is. Okay, there is an initial incubation period where the leading edge erosion starts to form, and then there is an acceleration period and a steady period. And we're very much interested in this incubation period, how long it takes, because the leading edge erosion can reduce the turbine's annual energy production because it changes completely the aerodynamic characteristics, and has therefore important consequences for the profitability of the wind farms. We have done a study with Sedvion. I think now it is belongs to Siemens. We have done a study where we have connected the leading edge erosion with meteorological conditions. So you can see here the erosion grade 0, almost no erosion. You can see erosion grade 1, erosion grade 2, the erosion has progressed even more, and erosion grade 3. And we have found that, as you can see here in these graphs, to summarize them, if you look at the triangles, are locations that in the UK that there was a lot of rain. The diamonds are where there was a lot of hail, and as you can see, actually there was not a lot of erosion after 2 years of operations. So it is just 2 years of operation. But however, when we had quarries, when the wind farms were near quarries, or where it was near the sea. So we're talking about wind farms in land. So these were near the sea. So I guess that this will be very important for the offshore wind farm industry. We have seen quite substantial rates of degradation due to the leading edge erosion, even only after 2 years of operations, which is kind of concerning. So this kind of study has generated a lot of interest, and people and various groups and various asset owners have contacted me, and we are continuing this work, and we're trying to understand this effect. We have we're in the process of publishing this modeling in order to predict the leading edge erosion initiation. We have used different models, and under some conditions, making some assumptions about what's happening near quarries. We're concentrating near quarries. It will be another study when we will concentrate on assets near the sea or for offshore industry. We have found that we have models that they can actually predict the order of magnitude of about few years for the initiation of the leading edge erosion. So what do you do about the leading edge erosion? This is from the literature. There are a lot of different propositions for protective coatings, can be all sorts of coatings. Some people have introduced nanocomposites, polymer films that can be sprayed or can be applied by a brush, a little bit like painting by rolling brush to the wind turbine leading edge in order to protect it from the leading edge erosion. And it was our idea that we thought that we can create such coatings by actually using the mechanical recycling route, which has its disadvantages, of course, but it has also its advantages, the easiness of making, of milling and grinding the blade parts. This is just a proof of principle study, very low scale, lab scale, more academic study at this stage. So we have used some milling equipment that you can see here, and we have optimized at this small scale the milling process, and we have managed to have some very good final powders for both carbon fiber epoxy composites and glass fiber epoxy composites. We have done a quite detailed study, which is usually missing from the commercial endeavors of the parts. We have used standard material science engineering characterization tools. Here is with a laser diffractometer in order to see the size of particles that we're producing. You can see that it is in the tens of micrometer range. This is our initial results. You can see some SEM images. You can see the fibers. You can see here in the magnification the fibers. So we have some short fibers now, and you can see the epoxy resin particles that they are in the micrometer and sub-micrometer scale. We have optimized this more, some more laser diffractometry results. So you can see now that we have for the carbon fiber epoxy powder particle size distribution, it's a bimodal distribution. The fibers are of this size, but we have now managed to make the particles of the epoxy much smaller, even more optimization. You can see now the fibers are in the couple of micrometers range, while the epoxy particles are clearly in the nanometer range. For the glass fibers, these are some initial grinding results. You can see the bimodal distribution. For the glass fibers, when we optimize even further, we have only one distribution. There is a peak. There is not a second peak about the epoxy particles, so we might have a little bit larger epoxy particles in this case. And then what we did is we created a process, a very simple process of distributing these particles into a polymer matrix. You have used different polymer matrices. Cannot go too much into detail because of the of some commercial sensitivity of some of our formulations. You can see the films that we have done at the lab scale, and you can see here that this is an example of SEM images of glass fiber epoxy powder particle dispersed in a polymer. And you can see that from the images that the particles are relatively, we might see some clustering, but relatively well-distributed particles. This is carbon fiber epoxy powder in another polymer, where we see quite good distribution as well. This is the glass fiber epoxy powder in the second polymer. Again, we see good distributions. Of course, not. We have done a lot of trials. We have used different polymers. Some polymers have worked better than others. So I'm a little bit choosing what I'm going to, what I'm showing to you, or on our more successful results of the dispersion. Certainly, there is more work to be done in order to optimize the dispersion process for all sorts of polymers. And just to stress that we have not used any dispersant, so this is just a very simple process without any dispersant. We expect and we are now working with dispersant expert companies in order to introduce proper dispersant in our systems that we can use that can generate even better results. We have done a lot of mechanical testing. I don't have time to go so much on the mechanical testing. We have done also ice adhesion. And what it is very important is wear testing, because the application has to do with abrasion, with wear. We have not done any studies in more realistic conditions where we have particle hitting our films. We have used at the lab scale just for the proof of concept a wear testing device that's called Tabor abrasion tester, and usually for elastomers. This is the abrasion testing that is recommended in the standards about wear testing of elastomers. And we have seen in some cases some very good Tabor wear index results. The smaller is this index, the better it is, because it is the amount of mass that is lost after 1,000 cycles. So you can see a case where we have very good result and improvement after the dispersion of the composite epoxy powder. And we have done also ice adhesion test results. You can see a little bit more varied distribution. We would like our films to have good de-icing properties as well. You can see that actually the glass fibers have less adhesion, much more interesting adhesion than the carbon fiber epoxy powder. This is an interesting result. Of course, again, we have not used any kind of ice for these results for any other substance that they can improve the ice adhesion test results. We work on ice adhesion with all sorts of other types of materials in other projects, and we can introduce some of our successful results there in order to improve these results. So this is just out of the mechanical grinding without any other additives. So in our opinion, these are very promising results. We've done also a lot of, apart from mechanical testing, abrasion testing, we've done also water adhesion testing, contact angle analysis. We have seen some cases where the hydrophobicity increases, some cases where the hydrophilicity increases. The water adhesion testing is also quite important because this affects the erosion of the blades. And we are working on optimizing, and as you can see that in some cases for some polymers the maximum adhesive force has diminished. So to conclude, we have demonstrated that the composites at the lab scale can be successfully ground into fine powders. And in some cases, we have seen that we have gone to the nanometer scale with quite narrow particle size distributions. We have successfully dispersed the powders into elastomeric resins. And the samples were successfully cast and cured. Examination of the dispersion via SEM and particle analysis with laser diffractometry have showed very good dispersion in most cases, I would say. Mechanical testing and surface characterization of the films have shown promising results, again, in most cases. And generally, I think the impression that we get from this proof of concept study that our process of turning the composites into powder and using them as reinforcement in elastomeric resins is a promising recycling route. We are still working on this project, and we're still trying to improve our formulations. So stay tuned. We might have better and more interesting results next year. Certainly, we're talking about the project at the lab scale. We would like to improve and optimize our process before we move to any scaling up. We are very keen to have partners in this in our endeavor. Here are my contact details, and many thanks for your attention.
Do we have any questions? Vasileios, this is David. Just to kick things off, are you working with any industry developers on onshore, offshore testing in the near future for your elastomer?
Currently, as you can see, I have Green Code Renewables there. This has been funded by the Green Code Renewables. Yes, we're not working directly, but we're talking to many partners. There are many partners. I think there are many stakeholders here. One is materials people, companies that make dispersants, for example. We're talking to them in order to optimize our formulation. Composites people, asset owners who own the wind farms, but also would like to work more with companies that make the wind turbines, because I think there could be a very good exchange of views there in order that will help us to optimize their process and perhaps in the future fulfill their needs, and also to connect it more with application. I think in this project we have both push and pull. That has been mentioned before. I mean, there is the push from the recycling sector, but also the pull from the point of view that we have a specific application in mind, that we think that we have an opportunity to make a good and useful product, so that the wind turbine materials are recycled within the sector and used as protective coatings for the leading edge erosion, which is a big problem for the asset owners.
Very good. One more question from my side, if anyone else has anything. And my second question is, are you looking at other material matrices for deployment of carbon or glass going into a compound, like say films or coatings, or is it mostly an elastomer-based system?
I have used the word elastomer a little bit loosely here. I have talked about the elastomers. I have a lot of experience with elastomers. I have worked a lot with tire rubbers. I mean, in tire rubbers, you have styrene butadiene rubber mainly, and also natural rubber. This is not the rubber that we use. We use other type of polymers that they are more fine-tuned for the protective coatings for leading edge erosion products. So even there are commercial products right now, and we know what kind of matrices that they use, and we use this type of matrix. So they are elastomeric. They are tough. They are not. It's not for a structural element. It's for a protective film. So they don't have to be super hard. The important thing is to be very much wear resistant.
Very good. Marcelo.
Thank you. I've seen that you use, according to the graphs you have reported, the Fritsch ball milling technology. So for your powder production, did you adapt the machine, or is simply using the commercial system? You see what I mean, right?
A little bit of both. A little bit of both. We're using the commercial machine, but we had to optimize the conditions. I cannot go too much into the detail, but what we're doing is not. It's relatively simple. Let's put it this way. I mean, we have optimized it. I mean, you could say that we use the commercial machine. We use it the way that it is prescribed to work, and we are having good results. But it would be a lie if I said that we got it one day and the next day we were able to do that. We spent several weeks and months of optimizing the conditions.
Clear. Thanks.
Especially for the carbon fiber, which is much more challenging. Glass fibers has worked pretty well, it was easier for the glass fibers. Which is interesting because I think there is more glass fiber out there than carbon fiber. And of course, I want to add that, I mean, this system, if we prove the concept, it can work for other epoxy based thermoset polymer composites in other applications. And we're talking to people, to companies that they make yachts in the marine industry, also aerospace application, automotive applications, wherever you use carbon or glass fiber reinforced epoxy. This might be a method. This was mentioned before. I'm not the only one that says that. This can be a good recycling methods for this type of composites applications as well.
Very good. Vasilios, thank you very much for your talk. And hope everything is going well in Edinburgh.
Many thanks. Many thanks. The sun is shining, strangely enough, right now.
Excellent. We will be adjourning for lunch in just a moment. After lunch, we'll have a panel discussion to talk about the state of affairs with the various technologies. And then we have obviously a really nice afternoon full of a variety of different topics. So we'll do lunch until 2 o'clock. Thank you very much. Hello, everybody. We are now starting the afternoon session after lunch. That was fast. Now, this will be a very robust conversation. We have some excellent individuals on this panel. So I would like to introduce them. They can come up if they would, except for two who will be virtual. Julio Vidal. Matt Corey will be virtual. He's with Oak Ridge National Lab. Mitch Renchek is with EPRI. He's also virtual. Ignacio Julian. Sandro. And Marta, por favor. It looks like Mitch is in space. I can maybe stand up and give you space, right? That would be fine. So welcome everybody back from lunch. Today for this panel, we will be speaking about wind turbine recycling, of course, but something more specific about what are some of the various TRL technologies that are in place and being developed for further commercialization. So again, we've got 4 panelists here, and we've also got 2 that are virtual here in the US. So we'll do just very quick introductions, and then we'll get to the slides and talk about various questions that many of us will have on this particular topic. So first, what I could do is I could ask each person to introduce themselves here on the panel, and then I'll go to the 2 virtuals. Just quickly, the initial question is, with your particular company, organization, research group, what is your ideal to achieve with this particular topic? What is the contribution that you want to have for circularity of wind blades?
Okay, so first of all, I'm Julio Vidal. I'm working with Moses, the Technology Center. We are working on 2 different technologies, the cutting and for the commissioning and the solvolysis. In both cases, the idea is to bring those into the market. Okay, the idea is to, if we are not able to produce it because we are a small company, to have a large company that can take over the technology and provide that technology for that entity. In both cases, in the case of the cutting, we let's say at TRL 7, TRL 8, as you have seen in the video, we have already cut large parts. So we are quite close. And in the case of the solvolysis, it's still ongoing and it will take more time to go. But the idea is the same, to have a company that can really take over and use these technologies and these processes for its own benefit.
Very good. Sandro?
Yeah. I already introduced myself before, but for the 2 online, I'm Sandro Di Noi from RWE onshore, and our target is to reduce the CO2 footprint. And at the same time, you know, the idea is to have the wind turbines fully recyclable. At the moment, the blades are the only components of the turbine, which is really difficult to recycle, while the other components are still easy to recyclable. So that's the target.
Very good. Ignacio.
Hi, good afternoon, everyone. My name is Ignacio Julián. I work as Technology Project Manager at CIRSE Technology Center in Spain. And our idea is similar to that of Julio and his company. So we are developing technology and specifically microwave-assisted thermochemical processes. And our purpose is to demonstrate and assess the viability and the energy efficiency of microwaves as heating source for the decarbonization and electrification of waste recycling. And in this particular case, the wind turbine blades recycling.
Marta.
Okay, my name is Marta Barreras. I came from Renault Cycle. My company, we are dedicated to the commission, the wind farms that are at the end of their lifetime. And our purpose is just to make the wind energy sector truly circular. We estimate that right now we are able to recycle almost 90% of the components providing from a wind turbine, and our ideal scenario will be just to recycle the 10% of the components. And for that, we are working with the most critical ones that are, for example, the focus of this talk, of this conference, that is the blades that are really challenging, but also the oils that we use in the gearboxes. We have an R&D project as well, just to be able to recycle these oils and using again in the wind energy sector.
Very good. Thank you. Mitch, would you share your position at EPRI and EPRI's contribution to this discussion?
Yeah, absolutely. Hi, everyone. My name is Mitchell Renchek. I work at the Electric Power Research Institute. EPRI is a nonprofit research organization. We are primarily funded through asset owners or utility owners from around the world. I think the statistics, like roughly 90% of the utility companies in the United States fund EPRI in one way or another, and we do research across the energy sector. I specifically work and lead research on the end-of-life management for wind energy technologies. So a lot of what we do at EPRI is very asset owner focused and utility owner focused. So to them, that is looking at best practices for decommissioning, evaluating recycling technologies, for asset owners in terms of wind turbine blades. That has been the primary focus from their perspective over the past couple of years as they push to have more sustainable operations within their individual organizations. So that's how we interact with this whole topic. Thanks, David.
Thank you, Mitch. Matt Corey, would you share a little bit about your role at Department of Energy and your contribution?
Yeah. Hi, everybody. My name is Matthew Corey. I'm a staff scientist at Oak Ridge National Laboratory in Knoxville, Tennessee, in the United States. So I'm not sure if Steve Nolet is in the room today, but Steve Nolet has a very famous saying. He's from TPI Composites, who says that we're looking for the killer app for recycled wind turbine blades, the killer application that's going to pull the material into the next life. And so that's what really motivates me and my team at Oak Ridge National Lab. We're really focused on the killer app. So for us, we don't compete with the market. We're one of several national labs. Derek Berry may be in the audience today as well. So Derek Berry is a scientist at our sister laboratory, the National Renewable Energy Lab. We all work very similar to the Fraunhofer Institute. We don't compete on the market. And so for that, with that in mind, we're really focused on the preparation technologies for recycling. So we don't compete. So we're not looking for competing technologies for what's available industrially at Oak Ridge. We're really focused on how do we make the materials recyclable using these technologies, and in particular, how do we maximize the value of the material in the blade when it's recovered? So that may look like steps that happen before it goes to a pyrolysis technology at Carbon Rivers, for example. It may look like technologies that occur after in order to separate out mixed hybrid fiber systems that are recycled. That's really our role. We're really focused on the next generation technologies in this. And my role, I'm really hands-on with the recycling. So a lot of the recycling work that comes for blades specifically at Oak Ridge is coming from me and my team. But there's a number of us working a host of different materials throughout the turbine. So I'll stop there.
Thank you very much, Matt. I appreciate it. So we have a couple of slides that we prepared and put together to give context here. So if the first slide can go up, here it goes. So higher TRL end of life wind turbine blade strategies utilized today. So a lot of the individuals in this room at a research level, lab level, or more for the commercialization perspective are looking at these particular technology applications and platforms. So what I want to do is just talk through a little bit about these and in an objective way, in the sense of what is the current state of affairs with each of these, what needs to take place next level for these to be more applicable for commercialization. And I want to start that with the context. So if I could, I'm going to stay with our virtual guests just for a moment, and if you could keep the slide up. But Mitch, from your perspective and how you're working with different owner operators, as you say, that are your customers, so to speak, with your organization with EPRI, what are some of the things that they're looking at with respect to these, say, options that are currently being developed? What are their levels of interest? What do they want to see from your perspective take place?
Yeah, this is a great question, David. And the way I like to think about it is all of the asset owners that EPRI engages with are all in different parts of their end of life management journey with wind turbine blades, as I like to put it. So some of them are very new to owning wind and very new to owning or very new to understanding and figuring out how to manage. And then you have everything in between, all the way to the other side of the spectrum, which is they've done this before. They kind of know what recycling technologies they want, and they want to know what they would like to get out of each individual recycling technologies. So I think on the left side of the spectrum, when they're like, I don't know really how to decommission, or I don't know how to handle these at end of life, I think they're just looking for a recycling technology. They're looking to get a certificate of recycling saying these were not landfilled. And then as the progression continues over time, I've seen asset owners keep asking for more and more value from products made with their recycled blades. And they would like to know where those materials are going into the secondary market, how they're being used. They're wanting a higher value product to be made out of their material. So less just being used for like cement filler or asphalt filler, and more used in the second market, whether that be liberation of the fiber from the epoxy and used in another composite material, or maybe it's used as a reinforcement in another product instead of just a filler. So any application that can add value is what the asset owner has been asking for more and more of lately, as we have, monthly and weekly discussions with a lot of asset owners. So that's kind of the state of it from many asset owners' perspective.
Very good. Matt, along the same lines, but maybe dialing in a little bit more, I do have a question that would be maybe provocative. And that is, say we're talking about cement kiln co-processing, and we have some owner operators represented here. The idea of taking a recovered glass fiber and putting it into a cement admix to decrease the emissions intensity that is dedicated to the production of virgin glass fiber, as an example, and also lowering cement in a mixed design when you're pouring pads for an owner operator, as an example. Have you had any conversations with the wind space in terms of that? Is that something of interest when it comes to, say, glass fiber going into reduction of cement and emissions, or displacing virgin fibers going into cement? Is that a conversation you've had at all with the wind group?
Yeah, so it is an ongoing conversation we've had for quite a while, actually, because as I'm sure many in the room know, at least in the United States, which is the market that I'm most familiar with because that's where I'm based. And I will acknowledge, it's very ironic for a US scientist to come to Europe and talk about blade recycling, because you guys are definitely way far ahead of us, in our opinion. The National Composite Center in the UK, as well as several national labs in the US, including NREL, Oak Ridge National Lab and Sandia National Lab, recently did a large comparative analysis project where we looked at all of these recycling technologies on this screen, plus several others. And we did a comparative life cycle analysis and techno-economic analysis. And to our surprise, the cement kiln technology actually does come in at carbon negative. And the reason why the analysis is showing that, and I will also indicate that NCC in the UK, their analysis was consistent with that result. The big reason why that technology is so quote unquote decarbonized is because you're able to skip a step in the cement kiln production. The carbonization step you can skip if you use a wind turbine blade as the feedstock, as opposed to traditional materials. And so that technology is actually surprisingly more sustainable than we had anticipated, at least in the US. And I will just indicate one last time that this is multiple sources of analyses are confirming this is behavior. Now, I'm not necessarily the biggest fan personally of us burning wind turbine blades as a fuel, and then using that fuel to produce one of the most commonly used materials in the world. It's, arguably not one of the most sustainable technologies when you consider just the blade material itself. If you look at the carbon in the blade alone, we may not want to burn that and emit it. We may want to use it in new products. So there's a lot of pull for the next generation technologies, but there is a case to be made about iterative technologies that can get us slowly decarbonized and help achieve those Biden administration goals of 50% and then 100% decarbonized manufacturing by 2050.
Very good. Thank you for that. So Marta, looking at these slides and kind of the different processes, obviously your team is more involved in maybe the last two. And so if you could comment a little bit on what you are trying to achieve, and maybe do you have any gaps that you would say, like, if we can do X, Y, and Z in the next 5 years, we will be at this position? Where do you see this going with what your team is trying to specifically implement in this area?
Well, as I see now, the most important thing is regarding costs, because for the operators and owners of the wind farms, it's much cheaper to dispose of the blades in the landfill than going through a recycling process. The numbers that I saw is that, for example, a thermal process costs 4 times more than the taxes that you need to pay for landfilling. And then in this case, I think that we need to work in order just to reduce the cost of the current strategies that we are using just to recycling the blades. For example, we talk about the energy consumption of this kind of facilities that is huge, because at the end of the day, we are working with high temperatures or medium temperatures or low temperatures, but at the end you are consuming energy, and maybe the costs are coming from that. Also, the costs are coming from the complex equipments that you need just to process all these materials. So in this end, I think that we are working around the process just to try to reduce this energy consumption, these energy requirements, but we need also to try to make simple the equipment if possible. I'm talking about the challenge for the future, because now we need to stabilize what we are doing now. But I think that regarding the cost, I think this is the most important. At the end, money is something that moves all of us, and I think that the effort needs to be put there in trying to reduce the cost of the process of recycling to make it competitive. Maybe not only with the landfill, because I think that landfill is going to be dismissed in the future because of the lack of space, as we commented in Europe, for example, but because of the public concerns as well of having huge tons of blades in the field. But maybe with other kind of cheaper options just to dispose of these blades, for example, incineration, that are not environmental friendly. So we need to compete against that, and the cost reduction is something that we need to be focused on.
Yep. No, absolutely. And adding to that a little bit, Ignacio, but also kind of the LCA component here on the slide. Hopefully everyone can see a little bit of those numbers, and these slides can be provided, I imagine. But, you know, a lot of individuals in the various kind of customer supply chains, they need an environmental product declaration, and they need LCA, and they need to make sure that these are processes that obviously we want to be commercial, but beyond that, they have to be environmentally friendly. So can you share a little bit about your process, what it looks like with respect to the conversations you have on either the lowering emission side of things, or looking at EPDs and LCAs and those types of asks by the market?
All right, yes. Well, at CIRCE, our main target is also to reduce the cost of the process somehow. And in our case, using microwave heating, we try to reduce the energy consumption at least by 3 times with respect to conventional heating. But also regarding environmental impact, we are considering also the valorization of the oils apart from the glass fibers. And this is something I want to bring on the table today, because I've heard many talks and everyone seems to be very worried about getting the best out of glass fibers, but there are oils out of thermolysis processes, both solvolysis and pyrolysis. And using microwaves, we have a better control of the thermal environment within the process, so we can provide the range of oil products that we want. So we avoid throwing them as gases in the atmosphere. So we are tackling both energy efficiency and a reduction of environmental impact, but by taking advantage of the controlled oil productions. So this is what we do. So currently, we are looking for end users for these oils. They can end up as fuels for the petrochemical industry, but more especially, they should end as building blocks for the chemical industry. Most blades are made by epoxy or polyester. Oils coming out of epoxy resins are mainly phenols. So many phenol producers can benefit from these oils. On the contrary, polyester resins lead to phthalic anhydrides or phthalic derivatives that have also a lot of end-use options. So our purpose is to produce both glass fibers, carbon fibers, plus oils in order not to have a penalty on the environment. This is our approach.
Very good. So Sandro, yes, go ahead.
Is it okay if I ask a follow-up question to that?
Yeah, absolutely.
I was just going to ask, as you can see for the left side of the slide here, microwave pyrolysis, especially when it comes to carbon fiber composites in the spar cap of wind turbine blade, is arguably one of the more sustainable technologies, and for the exact reason that the panelists mentioned, which is, of course, the energy savings from the microwave process itself. I just wanted to ask, in terms of the reutilization of the oils, a lot of the chemical companies have very, very stringent standards for what those oils look like when they go into their reactors, because they're just feeding them in at a certain volume into this larger reactor. Any amount of halogen contamination from a PVC foam, for example, any amount of nitrogen in that oil can contaminate the entire batch and result in it not being utilized. I was just curious if the panelists had any studies looking at the quality of that oil coming from the microwave pyrolysis. And David, you may be able to speak to this as well with your technologies as well. Are you finding that the pyrolysis technology of the blade itself is enabling to that technology? Because other processes, for example, automotive plastic waste and several different municipal solid waste streams simply cannot be utilized once they are pyrolyzed. So I'm just curious if there's if there's opportunities there, if you think that there's technologies that are still needed to enable the use of that oil after pyrolysis.
Ignacio?
Yeah, thank you. Good question. Regarding PVC contamination, of course, it can occur. And then one of our products would be chlorine or hydrochloric acid. In both cases, this will be released as gas and will not remain on the oil itself. So our oils are always chlorine-free. Regarding nitrogen, of course, it exists mainly on epoxy resins, not on polyester ones. And we will need an upgrade, a catalytic upgrade, most probably, to remove the nitrogen content, especially if we want to use the oils as fuels. Otherwise, perhaps amines or amides, it can be in the final formulation of the oil, and this could be building blocks for the chemical industry.
Yeah, thank you for the answer. I just wanted to highlight for you panelists as well as others in the audience, the Oak Ridge team is really, we acknowledge that this is a technological barrier. And so one of the ways that companies will work with us is looking at these kinds of technological barriers. So feel free to reach out if there's our technologies of interest to those on the call.
Thank you.
I'll give you Matt's home number when if anyone wants. So
don't forget the country code, David.
Yes. The next question, but in a similar manner, Sandro, as the face of RWE, speaking for the CEO and the board members, there's obviously internal desire and there's external desire with RWE to move along these technologies. So as an owner-operator being, highlighted and showcased here, what do you want to see with respect to, or what needs to be demonstrated with some of these commercial technologies for RWE to say, yes, this is something of interest that we need to have in place to look at intensely?
Yeah, we don't have wish list, let me say. So every single technology we look at the potential output, right? So for me, this graph is real. We are all watching. So yes, it's really interesting because if I look at the all glass fiber blade, the pyrolysis, it's not let's say the net total. It's not negative. It's positive. It's 6 point something. Sorry, I cannot really read it. And I know that for ages we spoke about pyrolysis as one of the solution for the existing blades, right? And it's good that here we can see the complete overview, including the carbon fiber blade option and the rest of the blade. For us, the point is, we know that already the turbines in the lifetime, they do, let's say, they are green energy, they are producing electricity from the wind. So they already have a positive balance as far as we know. So all the CO2 emissions for producing the turbines, installing, transportation, they are covered, or let's say, we are able to compensate them in 20 years in operation, right? So that's already positive for the environment. What is not positive, it's exactly what I told you before. We can recycle everything except the blades. And these are the point which people see the most. If you ask to a kid to draw a wind turbine, they will do the blade, basically. So all the people knows the wind turbines only for the blades. So it's more a cultural point. So we need to solve this problem. I know there are several options out there. We are testing a lot of them, but in every technology, there is a positive and a negative part. For us as end users, if the fiber can be reused or not, that doesn't change our life, because we know we will pay the new turbines always the same. So we hope that the fibers can be reused in order to reduce the cost of buying a new turbine. But this is a wish. The reality, I guess, will never be that close.
So you do have a wish list.
Yeah. But the reality is different.
Yep. At least for today, maybe.
Yeah, because the raw material manufacturer, I don't think they're happy to use recycled fibers. And when we talk about glass fibers, we know where the glass fibers are coming from. So they are relatively cheap. I hope that the use of the carbon fiber, which is a little bit more expensive to produce, will open the door to say, hey guys, we need to reuse those carbon fibers more than producing brand new one.
Yep. No, very good. Before I come over here to Julio, I have one question for Matt and for Mitch. Your labs were behind a lot of this data. Could you share just briefly with everyone here the assumptions put forward for this LCA model? I know that's more than a 2-minute conversation.
Yeah, no problem. I'll take it, Dr. Renchek, because Mitch started working on this project, and then he got an amazing offer to work at EPRI. So he unfortunately left our team, but we're so happy for him. So this, again, was a collaborative effort between Sandia National Lab, the National Renewable Energy Lab, and Oak Ridge National Laboratory in the States. And so one of the things I really want to put into context, so on the slide, David, that you shared, I just wanted to highlight that there are 2 graphs on that slide. One of those slides, the functional unit is the kilogram of CO2 per kilogram of recycled material. And then on the other figure, it was per blade. It was, kilogram CO2 per blade recycled. So it's really important if we're looking at these slides, just to make sure that we're keeping that context kind of in our mind. So the big thing is the carbon fiber versus rest of the blade recycling information. So that was actually very much inspired by the analysis that the National Composites Center did, because they did something very similar, where they basically had assumed if you could get the carbon out, how would that affect the recycling technology's carbon footprint? So we did something very similar using technologies that are available at scale in the States. The other thing I wanted to highlight is because of the way that this analysis was performed, which was led by a Sandia National Laboratory team, and we all collaborated on it, of course. The pyrolysis companies have an undue burden because some pyrolysis technologies will actually recover the syngas from their process, and they will reuse that rather than natural gas. So at Carbon Rivers, the best way to think about this, as you're burning the blade in a controlled way, you're recovering an oil product, you're recovering a syngas product, and you're recovering a solids product, which is a char. All three of those materials have a next generation. So it's not just an oil, it's not just a glass, it's not just a syngas. That syngas is captured, and you actually basically turn off the natural gas line and you turn on the syngas line at the same time, and you're basically eliminating your need for natural gas. So you get a credit for not burning the natural gas, but you get penalized at the pyrolysis company for burning the syngas. Now, whether or not we all agree with that in the room, that's unfortunately how this analysis was done and agreed to. So with that in mind, the pyrolysis companies, they don't, if they sell that syngas, for example, as part of their business model to a Next Life who then burns it there, they get just the credit and not the burden. And so there are certain limitations to the analysis as it was performed in this particular work. It is consistent with other analyses that are out there, but these, you know, it's complex. But if we do have the technologies to recover the carbon from within the blade, all of the recycling technologies, almost all of them, are undoubtedly better than landfilling overall. And that's not only a carbon footprint savings, that those technologies could generate the carbon fiber in a low-cost way, as the other panelists mentioned. Cost is super important. If you're able to get that carbon fiber out, there is so much demand, at least in the US market. That's the only market that I know. There's a ton of demand for that carbon fiber, and there's a ton of applications that are at the right volume to use the carbon fiber too. And so there are tremendous benefits to all of the different recycling technologies. It's tough to compare them side by side, but you know, we have to do the best that we can, of course. But even the products are different that are coming out of them, right? The pyrolysis products do not look anything like the mechanical recycling products. So it's really challenging to compare those two technologies side by side. I don't think one is necessarily better than the other, but I think once you get that carbon out, it's undoubted all of them are better than landfill.
I will add to that, David, a lot of the data used for the LCA was not specific to one commercial technology, because that would be kind of, if the analysis targeted one data set from a commercial line, then that would be biased, and it was trying to look at the technology as a whole. So the data inputs used for that pyrolysis LCA study were all from publicly available literature and not modeling any one specific commercially available process. So everything could change depending on how that process is ran and performed, much as what Matt was saying. Just want to also add that bit in there as well.
Now, gentlemen,
if anybody in the audience is asking, how do I get access to these figures? How do I get access to this data? How can I leverage this as part of my business model? The person that you need to ask is Derek Barry. In the audience today, he'll raise his hand. That data should hopefully be published in 2 reports somewhat shortly. And they will be coming out of the National Renewable Energy Lab. So I know Derek is in the room laughing right now. Please talk to him and ask him when that publication is coming out. And then hopefully he'll be able to give you a good answer for that.
Thank you, gentlemen. I just wanted everyone to hear kind of the assumptions and caveats as you put together this model. That was just helpful. So one final question before we move on to our next section, starting with Marta again. And the technology that you are developing, where do you see this in 10 years? What type of reach, what type of commercialization do you expect, say, we'll say by the end of the decade, by 2030? A lot of the companies here, of course, have their 2030, 2040, 2050 benchmarks for lowering emissions, you know, for LCA, et cetera, going carbon neutral, carbon negative. With your company and what you're trying to accomplish, by 2030, where do you want to be?
Well, I would like to have the facility fully operating, not only with the 10,000 tons that I commented before, but with a more important volume, because the expectations of the commissioning blades are going to be high. And I would like to have more facilities, not only in Spain, the place where I'm going to locate it the first, but all across Europe. So I would like to be able to process more tons of blades coming from the commission.
Very good. Ignacio?
Well, as a technology development company, our aim is to demonstrate the robustness of the technology and find the suitable investor to industrialize the solution. Yeah.
Let me say, we really hope this solution will be available, all of them. So we will have the possibility to differentiate, because the blades will be there. That's out of the discussion. But we really need to help these companies as much as we can, because the investment which require the movement to a higher TRL level, it's really huge. And I think that many banks, maybe they don't see the potential yet. So we should be the one financing or sponsoring you more than everyone else.
Or helping financial institutions see what that business case could look like.
Exactly.
Yep.
Exactly.
Very good. No, thank you for that. Julio?
For the water jet cutting system, I wish for it to be deployed in several places. I think it's a really good solution for the decommissioning, for transport, and so on. And for the solvolysis process, similar as Ignacio has said, just to provide a solution. And in our case, I hope that we will be able to not only provide one solution that facilitate that this solution in wind blade turbine sector can be applied also to the aeronautics, to the construction, to all those other sectors that are also using composites.
Fantastic. Thank you much to all our panelists, the ones that are here and the ones that are virtual. Give them a hand, please. Well, brilliant. Now we're going to transition over to Claudio Martin, CEO of Yulmine. Is that right? The wind blade recycling.
All right. Yeah. Hi, everyone. So does this work actually? Yeah, I guess so.
Yes, it's on.
Yeah. Well, I learned from the panel that I need to find Derek. I think that was his name, right? So, that's you. All right, good. Because our numbers look very different than, what your colleague showed. So I'm very, very interested in that one. Yes. So, yeah, I'm going to present basically an economically viable solution to produce low carbon hydrogen out of blades. So last time we talked a lot about, on the last conference, we talked a lot about paradoxes, and I will do a little recap, but this time I want to take it a step further and touch also a couple of topics that were already briefly discussed and touched here and there. So what's really basically in our heart is that we really take a look at the full value chain and not just at like a single scope. So very briefly, who we are. Definitely, we want to have like a solution that represents like a full material recovery. So one of our slogans is basically every element matters. So that's our aim. No? We want to recover as many elements as possible. We don't want to accept any emissions or CO2 emissions, and we are renewably powered, and it needs to be scalable and economically viable. So, and the beauty is if you have like a Gen Z writing your vision, then you get the last sentences, no? Anything less is not a solution. So, yeah, we are pretty mixed team, quite young, actually. We were founded in the end of 22 as a spin-off of 2 companies, basically. So we teamed up, and we have been longer working actually on the project. So why is basically the challenges are a little bit paradoxically, and we see this already in all these discussions, no? Because we need to increase on the one side production while reducing the environmental impact. We should grow, yet shrink its footprint. And then we should automate and create jobs. So that obviously requires, some rethinking, because it cannot be solved within the parameters. And if I see sometimes the discussions that we already had also today, you know, if I can say one thing, you know, I'm in the wind industry since 2000, so quite a long time. And we should not do the same mistake again. You know, we kind of postponed that, you know, like in 2000 and 2005. And we said, yeah, we are running a marathon. And then right now, you know, we are almost at the end of the marathon because of the blade recycling. But it's not good enough to say like, oh, the last 500 meters, yeah, I think I'm good. I'm gonna go home now. So I think we should do better and really find a solution. In the beginning of the wind industry, everything was about like functionality, just making it work, getting the blade a little bit longer and extending it another 5 meters and get a bigger rotor size. So it was all about functionality. Nobody really cared about the material inside of the blade. And that is really actually what gives us one of the headaches within the recycling and in terms of material health. So today, I hope you learn a little bit, you know, about that it is possible to have a sustainable yet economical solution where like all elements are recovered, where we close material cycle and the energy cycle and produce hydrogen. Wow, this seems to work quite well now. So and this is actually why I need to talk to Derek, because our numbers look very, very different. So we also did an LCA comparison, and maybe to explain that a little bit is when in our solution, we don't emit anything, right? We capture the CO2. And if we want to capture the CO2, we have two options. We can bring the CO2 back into a refinery and produce olefin. With that, we have a really, really low carbon footprint. And we have done the LCA over scope 1, 2, and 3. So totally comprehensive. So that's actually when we have like the lowest footprint. The other option is to put it into a greenhouse. And, you know, so to increase the production of peppers and tomatoes. And we are having discussions with the certifying body, which are saying like, yeah, but it's not captured, you're breathing it out. So it's sometimes really, you know, crazy discussions we are having. But then we are roughly around 10, 11 grams per CO2 equivalent if we are taking that option for the hydrogen production. So, and on the incineration part, it's really, you know, it will be actually really high. So we are coming up with a carbon equivalent of 156. So, but what we are actually trying to say that, you know, all the gold standards like CO2 neutrality, we need to revisit what do we want to live up to? Because CO2 neutrality is not circularity. You can be 100% CO2 neutral and 0% circular. So if you take incineration, why is it 100% CO2 neutral? You know, companies even get awards for that, especially in Germany. Because you offset, you know, the usage of fossil fuels against, you know, the blades that you are burning. So that is why it's neutral, but in the end, you're still having a lot of emissions. You're not getting rid of the emissions. So this is just a balance sheet thing. It's not real circularity, right? Or it's not real sustainable, at least from our perspective. So, and so we need to find the best solution basically on that side. So we have to kind of take a responsibility in every scope. That is a bit like what we are, at least that motivates us. So when we take a look at it, we take a look, okay, how are the blades transported to us? How many, you know, indirect and direct emissions do we have? But also the scope 3, this is actually the biggest part in every company. And that is also where the biggest potential actually is. So we need to take ownership of the entire life cycle. And so that's also where many opportunities lie. And especially when we take a blade, there is, we find a lot of elements in there that should not be in there and that probably people forget. So, so material health and critical byproducts is like a really, really big issue. So and these are kind of the stuff that my engineering said, okay, this is all right. But we found some really crazy things. We found like radioactive stuff in blades. Strontium doesn't belong there, right? So how did it get in there? So we have to be aware that, you know, we cannot change whatever happens in the past. And it happened for a reason. And we were all proud, you know, when we built the wind industry that we got it done, you know, and did something good for the world. But now we also have to take a look, you know, a hard look and say like, hey, how do we deal actually with what we have put out there? So we find a lot of chlorine in there because of the foams, PVC foams, and that can become a chlorine gas, right? And if you're emitting it, you're emitting it. So what's a big other thing? Halogens. You either have that in the oil or somewhere else. You have boron, you have lead, you have serum, you know, you have a lot of things in there. So you have a lot of harmful substances that come through, you know, flame retardants or, you know, a lot of coatings, gel coats, adhesives. So there's a lot of things in these products, and just emitting it is not an option, at least not for us. So we have to see that they're in there. It's a fact, right? The question is now, how do we deal with those? And that is why we think we have to really take a hard look at what type of products do we produce out of these recycled blades. If we use it as a filler material, it's in the filler material. It's not gone. It's just in hiding. So then we have to take care of that. We have to think about that. It's still, you know, in a few years' time, when those products will, you know, get recycled, we still have to deal with that problem. So sometimes we have byproducts, you know, that form during the process. Okay, that's probably the easiest part to deal with. But if we have products that, you know, harmful byproducts or products by using, or, you know, whether it's in landfilling or by using it in application or due to weathering, then this is not really in our control anymore. And so we have to think, you know, in the full scope, what happens to the parts or the products that we create by recycling, you know, the blades. So we are trying to apply the cradle-to-cradle thinking, but this is not always possible. Definitely not with the current. So this is kind of a, you know, an idea. It's an ideal thought, and we are working with a company together who is actually doing that for parts of the blade, but they can only accept parts of the blades that is not, you know, contaminated. So at least we are trying to do the best out of it. To follow actually the model and find permanent solutions, for especially anything that happens in scope 3. So the product passports is a great initiative, and we need more material transparency so that we can actually take a really so that we can actually really handle the material that's in the blades. It's not just about fiber and epoxy, that's just names, but there's like a lot of, you know, chemicals in it. So what are our unique solution? Okay, I briefly explained that already. We are trying to create a solution where everything matters. The CO2 is captured, closing the both loops, and produce low carbon hydrogen. And we take really the material health and scope 3 to the heart. So having said this, we don't claim perfection. So just to make that clear. But at least we want to strive for the smallest possible compromise when it comes to hazardous substances and environmental impact. So how does our process work? Well, in the end, we also have first a mechanical process where we condition the materials, sort out a lot of things. We can actually recycle PVC. It creates a byproduct that then by another recycler can be turned into a product. So we don't do that at our facility, but we can treat it at least. And then we have like a thermochemical process in a reactor where we create actually a syngas. Yeah, it's a high temperature process. And in that way, we are creating a syngas, and we can also take care of the so-called forever chemicals that are not so much in blades. They're used in the blade production process, but they're not in the blades itself. But we can also treat other polymers, production waste, cross-linked polyethylene. So we are operating at a temperature where all the carbon chains are broken up. Yes, so our products basically are low carbon hydrogen. After the reactor, obviously we are conditioning the syngas. We have carbon as a material, because why do we get fossil fuels out of, why do we dig it out of the earth kind of, or pump it up? It's because we want to have the C in it. It's a carbon. It's an everyday product. It's in this product, in every product. It's in the sneakers. So we should use it and keep it as long as in the circle as possible and in as virgin form as possible. And then obviously we also have the glass. So the glass can be used in different applications from, I think Makin proved it in a really nice way how to actually remelt it. That would take, in our process, some preconditioning, but it's possible. And yeah, but otherwise there's plenty of products you can produce out of it, even if it has a little bit of carbon sticking to it. So that's definitely an option. And in terms of like low carbon hydrogen, we are actually outperforming green hydrogen. That's more a part of for the regulations. We can't call ourselves green because we are not. Green comes only from an electrolyzer, but yeah, but we are meeting the requirements. No, you could say so. Yes. So when we are thinking about rotor blade recycling, I think it's about taking a shared responsibility. So within the total value chain. So I think to create a recyclable blade is the first step, right? But it's then also our responsibility then first of all, it's the asset owners they will decide, what is it worth, what's recycling worth to them, like in a sustainable way. That's a decision, and decisions drive the market in terms of investments. So that is a responsibility. So, and then we as companies who are actually treating the blades, we have to also take our share for transparency and having HSE as a big issue, not just in our facility itself, but also in where our products are used. And it is a tricky product. So, our message is perfection isn't the goal here. The goal is progress, basically. And to find a solution, together, where in the total value chain, everybody takes their responsibility. We have heard already, there's a couple of options out there. So it's not about the one solution, right? This is not about it. It's just about there's many options out there. but we have to take responsibility for like every step and every scope. So as long as that is met, then, we are okay. So just a brief overview of the project itself. We are going to invest into a site in the northern part of Germany. So we are targeting maybe mainly the northern part of Europe. And it's a capacity of 44,000 tons per year, annual capacity. And depending on the feedstock. So if it's blades, then it's obviously a little bit less. But if it's also other feedstock materials, we can produce up to 3,000 tons of hydrogen. And save a big amount of CO2. So the products are going either into a refinery or into other applications. And we are currently applying for the building permit. So keep the fingers crossed, then we will commission end of 26. So yes, I think our QR code works, by the way. So yeah, thank you very much.
Any questions? A couple here.
Thank you very much, Claudia. Interesting presentation. My question is on hydrogen production. You say you want to receive 44,000 ton blades and you can produce 3,000 tons of hydrogen. This is
up to.
Well, up to. Yeah, I'm just trying to make up my mind. I mean, there's silicium, carbon, and then hydrogen in the organic molecules. So I would guess there's like 1% hydrogen atoms by weight in a blade. So am I totally wrong? I mean,
no, I think
glass fiber is heavy. It's heavy molecular weight. So that's one question. And the other one is you have a spectacular low carbon footprint for the hydrogen production. I'm building hydrogen stations myself, so I'm a little bit in the business. I'm wondering, you have to heat up a lot of materials with green energy.
Yeah, green energy, yes.
I suppose. So how do you have a number of co-products? How do you arrive at below 10 grams CO2 per megajoule? These are my questions.
Yeah, so we have that. I've not personally done it, but one of our team members has done we did a product carbon footprint calculation together with the TÜV in Germany. And it's about like scope 1 to 3, basically. So the biggest impact is actually the transportation to us. Within our process, we are almost carbon negative, or it's like very little. And then to be basically, at least according to the TÜV, they require that carbon is stored for 25 years, then it's only counts as being captured. So the rules are very different in terms of like, this is not about like offsetting any credits or anything. They're just looking at, do you emit anything? How long is it captured? So it's really black and white in the regulations. So we have taken that into account, and that's why we have these two options. So when we go the olefin route, we look actually better because new plastics or new epoxy can be produced out of it, and assuming it goes into a new blade, and then we will have, it'll run there for another 20-25 years. So if we go into the greenhouse route, we are between like 10 or 11-ish, something like that, CO2 equivalent. Then we have, it goes into the peppers and the tomatoes, but then you also have the green part of the plant, and that will be turned into biogas. And that's when the TÜV says basically, yeah, but that's then not captured. So that is why in that scenario, so these are the different scenarios, and that scenarios, because a fuel, it's not even our customer, it's the customer of our customer right? Who's actually, taking that decision. But in a total life cycle analysis, this should be part of it. You cannot just stop at the end of your at your door, at your gate. You ship it out. This is not it. So that is what we are faced actually here in at least in Germany, we are faced with that we have to look at what does your customer and the customer of your customer do with the products, and then you have to account for that. Yeah, but that is a total. Yeah, we are big. Yeah, so that is a total calculation, but it includes really the full scope. Yes. Yeah. But yeah, we do have a lot of energy going in it, but we also have a lot of energy coming out of it. And for your first part of the questions, we do also use cross-linked polymers. So we have the 44,000 tons is more the capacity for on the mechanical side. So we can feed the reactors. It's basically a multi-feed reactor. So we can feed different types of polymers. So obviously, yes, you are right. If we only feed blades, the output of hydrogen will be much lower. So we get a syngas out of it, and then we also optimize it with like a water gas shift reaction and so on. But if we have more, for example, production waste or PEX or other polymers in there in the process that will fit our recycling specification, then we can increase the output or the yield of the hydrogen. So that's why we're saying like up to.
Okay.
Yes.
Derek.
Yeah, thank you. I am Derek.
Yes,
so
we need to talk.
And we will. So to make two quick comments. One about those reports, just anybody in the room that would like to eventually get a copy of those reports, just give me your contact information here. The first report is two. It will be published sometime soon. It might be delayed a little bit. We have a small election coming up in our country soon, and we're Department of Energy, so it's going to be after that. And then part two of the report is going to be probably in the spring, which covers some different things from that project. So, but I'd be happy to get your contact information and or talk to you here as well. Also, I'll be presenting the results of that project, some of the results of that project at Justine and DTU's second international conference on sustainable wind turbine blades. And so that's also a forum that would be a place you can also see that. One other, Claudia, thank you. And I really took an interest in a lot of your slides and what you talked about. One of the things that struck me is you had the slide of all the potentially dangerous substances in a blade, which I have no doubt, I'm not an expert at all, but I have no doubt that they're in there, and we need to do everything we can to mitigate any negative consequences from having those in the blade or to capture them somehow. But also I want to we have to make sure that we understand the context as well. Fossil fuel industry and others are trying to kill wind by talking about microplastics getting into everything out there. It is an environment that is not a level playing field, and we have to make sure that when we talk about these things, and it's important to talk about it, but it is within, we're not held to a different standard of everything else that's out there in the world, and we understand the nefarious approach to these chemicals in there as well.
I fully agree. This is just maybe like how do we call it, voice of, I don't know, voice of something, but it's more like a reminder that we didn't want to put the reason why we said this is what we find in analysis. Everybody finds this in their analysis, right? And it's not gone. It's somewhere in the oil. It's somewhere in the syngas. If you don't clean it, it's in the filter cake, right? So or in a product. And yes, and yeah, we should measure everything to the same standard. I'm in for 25 years in the wind industry. So, yes, I do believe that's what we are doing is still okay. And Now it's just the last meters in the marathon that we need. So we need to finish, you know,
Yeah.
on good terms.
Yep.
But we also have to take the responsibility for it. It's more about taking the responsibility and what do we create now out of it.
Yeah.
And we need to find a way how to handle it. And somebody also needs to pay for handling it, right?
Right.
You can landfill it. And I said, like, well, fine, you know. So, you know, we had this discussion before, you know, why are so many blades coming out of China? Yeah, nobody wanted to pay for blades coming out of Europe, no? Oops. So, you know, there's market power, there's consequences. So we just need to make sure that because this is in the beginning, and there's definitely more than one solution will establish, right? And that's also good for the market if more than one solution establishes. So because then there's option out there, you know, and there will be progress out there. So we actually do welcome also some competition, you know? So because that means how you progress, right? So yeah, but we, you know, it's also, I'm saying that to like our potential customers.
Yeah.
They're, you know, it's also a responsibility to choose the right, you know, method and be critical about it. And like, yeah.
I think you're approaching it exactly how we have to, and obviously whatever the truth is there, and mitigating and understanding the effects it can have is the right thing to do.
Yeah.
And then that's the best thing to way to approach it. But understanding that there's other agendas out there as well. Yeah.
That's true. Just don't show them my presentation.
Yeah, that slide. They would love the slide. All right. Thank you so much, Claudia. Appreciate it.
Claudia, thank you very much for your presentation. And you're absolutely right that we all carry responsibility. Yes, sir. So our next discussion is by Casper Glenning Buell. He is the project manager, plastic composites for Stena Recycling.
Hello, my name is Casper Glenning Buell, as you just heard. I'm a project leader at Stena Recycling in Denmark, and I work in the plastic and composite department. Today, I will talk to you about some of the steps that we are doing at Stena Recycling to become composite recyclers. And I'll do this based on a project that we have in collaboration with Nina and Vestas as the inspiration. This is my agenda. So first of all, I'll give you a short introduction to Stena and the Stena Sphere. So the overall company, and then going into Stena Recycling, where I'm employed. Then I'll talk about our collaborations, not only with Vestas, but also other companies, our motivation for going in the composite recycling direction, and some of the innovative steps that we are taking as a recycling company. Then I'll talk a little bit about the recycling process that we are currently, or current state of our recycling process. And then last but not least, I'll talk a little bit about risks and safety concerns when you're scaling up a project like this. So first of all, we started in Gothenburg in Sweden as a little scrap dealer. And since then, we have moved towards being a circularity partner, helping companies throughout the different countries that we are situated in. This is how the Stena Sphere is organized. We are a family-owned business. There's a leg that's called Stena Metal. There's a Stena A&B and Stena Cezanne. And these are the different industries that we are working within. We are approximately 19,000 people currently. And one of the things that I'm more proud of is that we are annually recycling more than 6 million tons of waste. In Stena Metal, there is Stena Recycling, then there's the trade and industry, and then we have finance. Stena Recycling is a big part of the 4,200 employees you see here. And we are also responsible for, again, the 6 million tons of waste that is recycled every year. Here you can see where we are situated. So we are very strong in the Nordic countries, but we also have moved down into both Germany, Poland, and Italy. And we are operating within these areas or material fractions. So we are very, very good at metals, both ferrous and non-ferrous. We are good at paper, alternative resources, and also hazardous wastes. Then we also have moved into electronics, and my department, which is the plastic department, looks very small, but we are scaling up. And of course, this is based on weight. Plastic is not that heavy. And we're also moving into composites. Again, here, I'm super proud of what we're doing in terms of CO2 emissions. We have avoided approximately 7,800,000 tons of CO2 annually. This is just a quick overview of how it looks in the different countries that we are in. I think you can look at that at a later point if you're more interested in it. Okay, I can see we have a little bit of a problem. This is the PDF and not the PowerPoint, so there will be a video later where I will just tell you what's happening. It's not going to happen. But yeah, this is the journey that we have been on since 1939 in Gothenburg, where we started as a scrap dealer, moved into recycling material or waste from industry, and then at this point in time, we want to be a circularity partner for the different companies that we have partnerships with. Yeah. Okay. Perfect. Yeah. A few animations here. You'll get the video now. As I've mentioned a few times, we at Stena Recycling think that collaboration is definitely the key to success. It's extremely important for us in all of the collaborations we are doing, especially on the outbound side of things. We need to be in great contact with the recyclers that we are sending material onto, but we also need to be having good collaboration with our inbound customers. Here you see four collaboration cases that we have been working on. I haven't been a part of 3 of them, but I can talk to you about the RACE project. The RACE project is a project where we are trying to recycle plastic from the automotive industry. And this is a project where we have included both academia, we have included recyclers, we have included dismantlers, insurance companies, and so on, to get a broad amount of information, broad amount of knowledge, and to get to the success criteria as fast as possible. This leads me into the project that we have with Vestas, and where this presentation is taking inspiration. So in September 2023, we signed a joint development agreement with Vestas. This project is building on a project that Nina talked about earlier, the CTEC project, where we have further developed on that solution. We are using each other to understand the market better, to reach out to different companies that can help us with recycling when we have separated the different materials, and so on and so forth. When we are going out now, and where we are currently standing in the project, we are trying to get partners to take up some of the materials that we are capable of dismantling or delaminating from the blades. And these are some of the engagement arguments that we can provide to those partners. And this is both regarding the inbound customers, so energy companies like, where are you sitting? Oh, he's not here anymore, but RWE, And here I'm talking about future proof of compliance in terms of when bills and legislations will be saying you can't landfill, you can't incinerate the blades anymore. We will have a solution for that, hopefully. Also reaching sustainability targets. And then if you look at the outbound perspective, if there's a partnership with us, we will of course be tailoring our materials to your recycling capabilities, and therefore there will be a security of supply. We are not only looking at end-of-life blades though. In Stena Recycling, we also want to go to generation 2. As you can see here, that will be production waste. But what is even more important for us is that we can hopefully tailor this solution to also be able to take composites from other industries, as we see a huge potential in that and a huge need for that, as you all know. We have talked a little bit about this in multiple other presentations. There is a huge future installation of wind turbine blades or wind turbine generators. So there will be more blades in the future, but that is quite a bit into the future. So we are also looking at these potential markets for composite or potential composite recycling. And for example, the RACE project that I talked about before in the automotive industry. Again, we have talked about it multiple times during today and probably will as well tomorrow. The current waste solution is either depositing, it's incineration, cement co-processing, and so on and so forth, solvolysis, pyrolysis. And now you can see what we have been doing. This is from the CTEC project though. It's not from our project, but it's the same process. So what you see here is a very, very small part of a wing. It's submerged in our solution, and you see the delamination of the wing. So you have the different layers of glass fiber, and you have an aluminum wire thing. Then you have the foam and a nice separation here. This is from a report that they made for the CTEC project, but it still gives you a good idea of what's going on and the kind of materials that are coming out of the process. This is something that Vestas has created. It's a blade circularity kit which they are bringing to different summits, and I just think it's nicely showing some of the different material fractions that we then at Stena Recycling has the responsibility to then distribute to recyclers. When you look at the recycling hierarchy, we of course want to be on the top spot, right under reuse, but there are also other solutions, as we talked about today. There's recycling into a product that isn't circular. There's recycling with an irreversible loss of properties. Then there's recycling with a reversible loss of properties. And then there's hopefully where we will come in, recycling with full circularity almost, and almost no loss of properties. We have reached this at lab scale, but let's see what we can take it to. This part here is going to be where I'm going to focus all of my attention. So at Stena Recycling, my job will be, among other things, to develop this value stream from receiving the inbound material from different energy companies. So it has been dismantled. Then we are cutting it up and delaminating the different materials into these fractions that you see here. In the project, we won't consider the part that is called others. that will be the coating, glue, and so on. It's a small amount of material, and we don't see any value in pursuing that. Of course, it would be ideal to be able to do it. These are the splits that we have been able to find. This is based on information sharing between us and Vestas, desk research, communication with recyclers on the outbound side. And what is super important for us here as Stena is that we measure or we have two measurements, which is global warming potential and material circularity index. And these are important when we're talking the gate free from the inbound customer, because if we can provide them with a solution where the global warming potential is good and we have a good material circularity index, then we can get a higher fee. If we take carbon fiber, the global warming potential, for example, is there's a positive effect here if we recycle carbon fibers, because as you all know, carbon fibers, virgin carbon fibers, are very energy intensive to produce, whereas recycled carbon fibers don't require anywhere near the same amount of energy. Then if we talk about the material circularity index, that measurement is just about, okay, so you get this amount of material on the inbound side, how much are you capable of recycling? And of course, the more we can recycle, the higher the material index will be. And again, this material hypothesis, you can look more into that at some point. I don't think I have the time to go into depth with all of the different materials. But we have used this material hypothesis in our job at Stena to try and make a maturity level of the market and try to understand what each of these different materials, what the sellability of them are, and when you consider the fact of or the processing of the materials. So if you look at the metals, we have put that to 10. That's because we know exactly how to recycle the metals from the blades. Then you look at the carbon fibers and you look at the foams or the core. As we've also heard today, there are many actors in these markets. It would be possible to find recyclers for these materials, and we are already talking with recyclers. So these we have given a maturity level of 6. Then you look at glass fiber, and we have talked a lot about it today. We see this as being quite a bit lower than, for example, carbon fibers, and this is mostly due to it being a very cheap material. So it will be difficult for us to sell it compared to virgin glass fiber on the outbound market. And then we have the resin or the epoxy, which is a big problem for us right now, and which is something that we are looking into and trying to create partnerships and get a better understanding of how we can recycle the BPA and the epoxy in general. When we look at the different markets and the maturity of the different markets, we look at these 7 steps. It doesn't have to be in this particular order, but we look at these steps to get a better understanding of where we are in the market, if we have any collaboration with any recyclers, and where we need to put in some effort and energy to get a better understanding. So for example, now I won't go through all of them, but considering purity, it's extremely important that we get a better understanding of what our potential recyclers need from our materials and what we can get out of the material fractions from the blades. Again, talking about some of the maturities of entering uncertain markets. for us as a recycler or a material handler, it's very difficult when we don't have, or when we have imprecise pricing of the different materials. We need to put in a big investment to finance the entire processing from inbound to outbound, and therefore prices and being able to sell the material on the outbound market is important for us. Also, unprecise in-feed is a problem. We need to make sure that we will get enough in-feed from the different inbound customers. And again, here it's partnerships and collaboration that is needed. If we talk about, or this is how we view it, at least how to mitigate these risks. Again, it's a collaboration and it's a market study where we need to understand each of these material fractions a little bit better. And that is what I'm supposed to be doing over the next year and a half. And hopefully there will be some push from other places in the industry to mature these markets and put some money into maturing the recyclability of the different materials. Lastly, here I'll quickly run over internal logistics and safety. At Stena Recycling, as I said, we have a lot of experience with hazardous waste. So we have quite meticulous standards for how we do internal logistics and safety at our different branches. First of all, when we are handling new materials or new fractions, we look into are there any volatile elements? So for example, are there any fumes, gases, active compounds, and are there anything that will provide a quick energy release? Then we need to have attention to that, and we need to be able, or we need to have the right machinery, the right ventilation, for example, or buildings to handle these materials. And at Stena Recycling, we are trying to do this by implementing modular design and making sure that when we transport the materials inside our facilities, that we do it in a safe way. You can see an example of it here where we have different zones. And just to make it clear, I'm not a safety expert by any imagination. So if there are any questions towards the safety, ask me and I'll talk to a colleague. Just a quick summary. First of all, we at Stena Recycling think that circularity and partnership, now I've been saying it so many times, but it's really important for us that we have this and that we are capable of using the information from people in the industry and getting that knowledge. So we put a lot of effort into this. Secondly, when we're looking at the market, we think, as well as many of you have said earlier today, that several solutions and several technologies is the best way forward. And then, of course, maybe not all products on the outbound market needs all of this processing. Sometimes you don't necessarily have to go all the way with the processing, and we need to be able to use all of them. And lastly, I'll just say that we at Stena Recycling think that it's so important to keep an attention to health and safety, because if you don't do that, you cannot have a sustainable solution. Thank you so much for listening to me.
Any questions? I have one myself, and that is, as you all are subject matter experts industrially at waste material processing, collecting, sorting, et cetera, and you operate in different regions in the north of Europe, down in Italy and things like that. What do you find as the most challenging bits when you're trying to move material among EU member states? So, for example, some of the materials you work with could effectively be considered recycled materials for raw material supply. going into next life cycle economies. What are you doing with like the commission and policy and things like this to move this material with better ease, say, among different member states?
Yeah, I'm not a lawyer, so I've only talked briefly to our legal department about this. But as far as I know, we cannot classify it as a raw material. It is waste, and therefore there are stringent regulations in terms of moving it across borders.
Hopefully that'll change soon. We'll see.
Hopefully, and we are trying our best at least to be ready for that.
Very good.
Yeah.
I do have a question regarding the fillers. You mentioned that you can recover the fillers. In this case, it was PUR fillers. What do you do with a high percentage of blades that are out there that have actually balsa wood fillers? And this goes to everybody who's, promoting sulfolysis process. What do you do with the balsa wood? How do you recover any of that?
I would say that it would have to be cut out. It cannot be recycled in a sulfolysis. I'm not sure about this because we haven't, or at least while I've been on the project, we haven't considered balsa wood. We have considered plates with primarily PET foam because that's what we see from the materials that we are getting. But of course, there are plates with balsa wood and
high percentage is even high.
Yeah.
And even today, it's still being used again, I should say. Yeah.
Okay.
Since they discovered that you can use the root of the balsa tree, then now they're using more and more again. I think this is something that everybody should be aware of.
Okay, I'll definitely take that back with me. And if you give me your email, I will see if I can come back with an answer for that.
Thank you.
Of course.
Marcel.
Thanks, Casper. I was thinking about your conditions for the off-takers that you are searching for, that you are investigated in. I mean, you have some semi-finished or let's say byproducts or products from your delamination. Suppose I'm a company interested to test your material. What are the conditions that I should agree with you on the use of the material? So is that about reusing the exact same form of the material, or are you providing services for transforming further the material to meet a my specification? So how are you handling this?
We have actually been sending quite a few samples out to different companies already. So for example, carbon fiber and also glass fiber. So we could definitely send some samples to you as well. So yeah, we send it currently because it's not like big parts that we have been sending. I know from your presentation that you're working with fairly big parts. I can go back and talk to my colleagues about whether or not that is a possibility. But I would, at this point in time, not consider that a possibility because we are looking more into recycling each of the different material fractions. So it would be probably layers of glass fiber rather than big pieces of plate, if that answers the question.
One more question and we'll move on.
Hello, Ronan from Suez. So you said you recycle a bit more than 200 wind turbine. That means you have facility to treat blades in all over the country or in each country?
Have I said that we recycle 200 blades? Because that was definitely not true. We are still at lab scale.
Oh, okay.
So we are not capable of taking a full blade, and our pilot project will be for one blade to begin with, and then scaling up further than that. But we are at lab scale with our delamination process currently.
Okay.
Casper, thank you very much.
Thank you.
We have one more talk this afternoon before our next break. So Marcin Rusin, co-owner of GenCraft.
Yes, good afternoon, everyone here in the room, but also our colleagues that are joining us online. We have a small delay, so I will try to be quick, probably cutting already minutes to the coffee break. So if we start up, so my name is Marcin Rusin. As mentioned, I'm co-founder and CEO in the GenCraft, the wind turbine and composite waste recycling technology recycling company and service provider. Today, I will present how GenCraft is advancing the sustainability into the wind turbine recycling and helping energy sector to improve the circularity. So we are addressing in today or in this conference pressing challenge: what to do, how to handle wind turbine waste, and how to turn the waste into the valuable products. And when we established GenCraft, we had a mission to significantly contribute to address this challenge. We have established GenCraft in 2001 in Norway. This is a Norwegian company with a mission to develop sustainable, efficient, scalable, and financially, economically viable solution to address this pressing challenge. We have been committed since the beginning to developing the process focused mainly on the wind turbine composite waste, but we're also looking on the other types of the waste to improve in general the efficiency of the recycling of composite materials. We've been working across the whole value chain with different partners, from the mobilization down to off-takers of the products, that I will say a bit more in a bit later in the presentation. We have already established one plant, fully operational plant, still small scale, but already commercial plant in Norway in 2022, where we've been testing our process on a bit higher scale, on a pilot scale. And once we have proven the concept, improved our technology, we've been working heavily on the market, on the both sides, upstream and downstream, to develop the market and off-takers of products from our process. So you've seen this graph or similar graph already quite a lot today. You have seen different numbers, but I think we can all agree that the European, in general, the energy market is increasing. Our demand for the electricity, for the energy is increasing heavily, and the numbers are very dynamic and changing all the time. But I think we can agree that the amount of energy that we will need in 2050 will be significantly higher what we are seeing now. And this will come with the cost of increased amount of the waste, and especially in wind turbine waste, as the wind energy sector is increasing its share in the power generation. So again, different numbers in the different papers, but based on our research, we are estimating that already by 2050 we will see around 2 million tons of the composite waste coming from wind turbines alone. We've been hearing about the projects and the initiatives of the OEM producers, where they are designing new turbine blades to be fully recyclable. The old generation has not been designed this way, and still we see that a lot of new turbine blades are installed right now. They are still produced based on the old technologies or standard technologies. So the blades we will see coming down in 2050, those will be still the old generation. There will be not too many, probably new generation blades that are possible to be recycled in easy way. So we need to handle this waste stream, and we need to work together to develop different solutions, how to do that in a sustainable and the best way possible. And just a remark, we have already heard about it today. Other presenters also mentioning about that. The wind turbine waste is a small portion of the actual market for the composite waste. So we're talking here about, again, different numbers, but something in the range from 10 to 15%.
So wind turbines stands only for up to 50% of the whole composite markets, and the turbines are actually the one that are having the longest lifespan compared to other type of the composite products. So, for example, the automotive, from the car, construction, aerospace, shipbuilding, and all the other industries, which stands for 85 to 90% of the composite market. Those products has a much shorter lifespan than the blade. So there's a huge amount of the composite that will be on the market to be recycled. And currently we see a high pressure, high push on the wind industry to recycle their composite. We can see the same push on the other industries, but it will come. And the wind turbine sector now is paving the way, is leading the way, how to recycle composite waste in the sustainable manner. So in the future, those markets, other markets, will contribute from the work we are doing right now. So as mentioned, Encraft was and is developing its own technology. We've been crafting technology already in 2020 or even before we actually even were aware of the challenge coming from the wind turbines. Our process is a multi-step process combining both mechanical and thermochemical recycling. One of the steps in our process is already mentioned, pyrolysis. So a lot of projects are using this process mainly because it's ready for the market. So this is the process that allows us to go into the market right now. It's a scalable process and a cost-efficient process for the needs of the market at the current stage. So when we've been investing, when we've been building our technology, working on the development of our technology, we've been looking on the different type of the technologies and the processes, and we've been selecting those which gives us the highest scalability, probability, and possibilities, which was possible to come to the market fairly quickly, and that could from which we could produce the products that will find off-takers of the market. So for us, it was important to work with the process that we can deliver products to the market based on the current demand and based on the market readiness. Of course, we are constantly developing and improving our processes, implementing new innovations to always following the market needs, and to deliver the product quality and grades that are required by the market. So by working or by implementing our technology, we are providing the number of benefits, like reduction of the amount of the waste going to the landfills on incinerations, by reducing the demand for the raw materials, by implementing the materials from our process into the production, by closing the loop for the energy sector, and minimizing carbon footprint both for the waste owners but also for the producer of the composite materials. So the diagram below, you can see the waste stream into the products. From our process, we are recovering glass and carbon fibers in different grades and mechanical and physical properties. We're recovering oils, gases, and the foams that are going into different processes. So if we focus on the fibers for now, based on our fibers, we can produce a number of new products, new materials that then goes to the end product. So we can produce long, short fibers, short fibers, mill fibers. We can produce the mats out of the fibers that in the next step can be implemented into new products, offsetting the need for the new raw materials. And as a proof of this concept, we have executed a number of the test projects. So if we start from the top, for example, as example of high-end product, so to prove that you can use recycled fibers in the high-end products, like for example the skis. We're not a ski producer, but this is just a pair of skis we produce based on the recycled carbon fibers to show that from the recycling products you still can build some valuable products, latex skis that are fully usable, and the properties of those skis are not far away or very similar to the skis that would be produced based on the virgin carbon fiber. There are also other projects we are working with together. For example, with the Refresh from EU, we are working on the new wind turbine that will have
part of the virgin glass fibers replaced with the recycled one. So our goal here is to close the loop and to use fibers recovered from the old turbine and put it back into the new one. Of course, the fibers will not go to the structural elements, but at least they will be in the blade, and they will offset a big amount of the new raw materials. And there are also other products like construction elements, like boards, some tiles, and other composites that can replace the virgin fibers with our fibers. And the low-grade products, for example, where we are remelting the fibers, for example, to new fibers or to other materials which are consuming glass waste in the production. Everything we do requires or we do together with our partners. So for the products that I was presenting, we have partners that are producing those products together with us. And also we have partners on the other end of the process, on the upstream for the materials, where we are working with a lot of operators. We are working with OEM producers, and we are working with the industrial partners. So for example, we are working with the Kingo Wind and Berger Special Transport. Kingo is a Danish company, demobilization company in the construction industry. Bergen Special Transport, the Norwegian transport company. And together we are working to provide comprehensive solution to the operators to allow them to access a similar waste management system as we see, for example, in the plastic industry. So currently the operators doesn't have an access to such system, and in the most of the cases, they need to handle everything themselves, from contacting right partners, collecting offers, and participating in the obtaining all the notifications and other documents and permits, for example, for transportation of the waste, etc., etc. So by creating such a collaboration with the partner, by creating a hub, we are reducing the load on the waste owners and allowing them to transport the waste and treat their waste efficiently, on the low cost, and sustainable way. We are also part of the development project co-financed from EU or Innovation Norway funds, and together with EU partners, we are collaborating under the Refresh project that I will not say much about, because tomorrow my colleague Daniel will have an opportunity to present this project to you. So we'll learn more about it, but I will mention about this project a bit later also in my presentation. So by collaborating with us, our partners contributing on the multiple levels, mainly they are increasing the sustainability, reducing carbon footprint, but also they are aligning with the EU regulations and offsetting some materials, so can reduce some costs by using recycled materials instead of virgin, and offsetting a use of new materials that contributes again in the lower LCA, better LCA analysis, and meeting the regulations and meeting expectation of the public as well. So what is the future for Jähnkraft? And we have a very ambitious plans. We are targeting to have a capacity of 100,000 tons of composite recycling by 2035. We are currently in our pilot plant. Currently, we're processing around 350 tons per year, so there is still a long way in front of us. But we have a very ambitious plan, and that we are implementing every day, successfully implementing every day. And so our next step is that early next year, together with the support from EU, the Refresh project, we will establish, or we will extend our capacity to 1,300 tons annually, and continue with the increase to 10,000 tons already in 2026 and 20 tons in 2028. In parallel, we will establish new locations. So with the mention before Kingo Wind, we have already started working on establishing a new location in Denmark, a new company that will be called Recomp Nordic, with the pretreatment capacity of 5,000 tons already next year, And also this plant will be extended to 20,000 tons in coming years. And in parallel, we are working with other new locations for the third and other plants. So the overall goal is to have 100,000 tons by 2035 in multiple locations across Europe. Yes, so our vision for the wind turbine recycling for the future is to be able to reach the level where we are able to close the circular loop for the circular loop for close the loop for the blades. So we are able at least able to produce the quality of the materials that will allow us to recycle fibers or materials from the wind turbines back to the wind turbines. This will not happen today, it will not happen tomorrow, but eventually in some time when the recycling technologies will improve, will innovate, we will be able to do so. And we in Jähnkraft are committed to that, to achieve that kind of technology level, innovation level, where we will be able to produce the materials that will allow to be used in the wind turbine blades or fully circular from product back to the same product. And we have set up ourselves also ambitious development plan that is tailored to reach that vision. And that would be all from my side. Thank you very much for your attention. I hope that you learn a bit more about Jähnkraft, and if there are any questions, I will be happy to answer.
Marcin, question from my side is, have you been able to work with some of the glass fiber OEMs and look at evaluating the glass production that you've been working on with some of what they have and analyze that with respect to comparison to virgin or their interest in putting this back into production?
We are working with one blade producer from Scotland to run this project for now, to actually produce the new blade based on that fibers. So as mentioned, this will not go directly or it will not go into the core of the blade to the structural part, but we will use it for the shell, for the non-structural parts. And this is the first step to do. The challenge with the use of fibers in the blade, back in the blade, is that for the core materials you need continuous fibers mainly, or at least the design for the current blade is that you need a continuous fiber in the form of the fabrics in most places. And after recycling, the fibers are not the same length anyway, because no one is transporting the full blade to the recyclers. Always, I haven't heard about on any other case, but always the blades are cut into the smaller pieces. So already you are reducing the properties of, at least physical properties of the fibers by cutting the fabric. So our first step is to work with the producer to use the mats into the shell elements, and then we will start progress from there into next possible applications and see where we can go with that.
And one of the reasons why I bring up the glass fiber OEMs is they might have interest not in going from blade into blade, but blade into vehicle or blade into building material or something like that.
Actually, we have one project that we are starting working with the operator of wind turbine, one that is building actually new farm in Denmark. Because of the new requirements that you need to implement a certain percentage of recycled materials into the project. In general, it's not stated where you need to implement those materials, it's just a percentage you need to implement. They're looking into the possibilities to use the fibers from the recycled wind turbines in concrete or in other elements. So we have a project with them where we're looking together with other partners that are producing end products, where we can put some products, either our or their products made based on our fibers, into that construction, so they're able to meet the requirements. So the concrete, some panels, some walls, maybe wall panels for flooring, and different applications. We are working right now to see what are the possibilities to implement recycled materials into the construction of new wind turbine plant, new farm.
Hey, Marcy, thanks for your talk. So my question follows along with David talking about that. And you kind of answered it a little bit there, but you were talking about the fiber market for glass fiber. And so you're looking at going into an already processed weave where they have to be Vartam it or something like that to get resin into it? Or are you talking about establishing a chop fiber for a veil system? Or are you talking about chop fiber for a plastic reinforcement? Where do you see the market going with these things?
We are delivering the products that we see the demand of the market. So we are working with the off-takers to find out actually what will be the products market needs. So we are not like we have a lot of development projects when the off-takers are testing our fibers. So, and we have new products, completely new products, which are only based on our fibers. Like injection molding, for example, and we are having other projects which are in which we are replacing partly or fully virgin material. So based on the fibers that we are getting from our process, we need to do some post-processing, mechanical processing to chop them, mill them, or depending on the requirements of the end user, of the off-taker of our fibers. So this is non-existing market yet, and it's not like we can go to someone and say, okay, this is what those are the fibers we can provide you, because they're usually expecting, okay, I will buy from you 10,000 tons. Can you promise or can you guarantee that I will get 10,000 tons of the fibers of that quality by this date, for example, right? At this stage, we're not able to promise that. So most of the projects we are working with are some kind of also in the development phase. Or the customers that are seeing a benefit for them to produce materials based on the recycled fibers, and they are looking how to apply those fibers in their production. So as an example, maybe I can give you the one of the Norwegian biggest fair production on board producer that we are recycling his carbon composite materials based on the carbon fibers to recover those fibers, and he's looking on in his design in which part he could implement those fibers to offset the virgin fibers, and the properties, the land and the properties to the fibers will be adjusted depending on his need.
And so you have a market for that 100,000 tons per year?
Not for 100,000 tons yet, not yet, but we have a market. We see the market, and
so you're talking niche markets, boutique applications.
Not only niche, because as I said, the market is not there yet, so we're looking different applications. And to use the fibers in the production of the new composite, those are not the big amounts yet. So, for example, we have other markets where we can implement bigger amounts of the fiber, maybe lower grade of the fibers, for example. But there is a huge interest, huge off-takers, which can take significant amount of the fibers. And in the meantime, when the market grows and the new off-takers are interested, the new producers are interested in implementing the fibers, and also when the more significant amount of the composite waste will be available on the market for processing, we can scale up, and then we can provide bigger amounts to other off-takers. So it's a lot of work. We can say that the last 2 years, 50% of our effort was on the development of the technology, and other 50% of our efforts were to develop the market, to find off-takers, to find partners which are willing to test and look into the possibilities to use the fibers in the product. So we are working heavily to actually create this market and create the demand for this fiber, to make all those products, to present. You can use recycled fibers in your product and still produce valuable products that you will have off-takers on the market. So it's heavy work, but I think it's worth all the efforts.
Marcin, thank you very much for your presentation.
Thank you.
Really appreciate it.
Thank you.
So now we'll break and be back at 4:15 for the rest of the afternoon. All right. Hope everyone filled up on liquids and donuts. We're now speaking with Julien Cellier, co-founder and managing director of Structure Team. So he is ready and looking forward to his presentation.
Okay, good afternoon. You all had the coffee, awake, and I think, as you said, 4 presentations away from the beers. So keep focus. I'll try to be interesting. Hopefully, you'll have some fun through the presentation. I don't know how, but we'll try to find it. We'll try to, through that presentation, to take a slightly different angle, which is what should we build the new blade with? We've talked a lot today about existing blades and how to deal with them. There is another side to it, which is blades are still being built at the moment and how they are built today for tomorrow's recycling. I shared with the chairman a small comment. We haven't heard about in-process waste. There is a waste stream today that is not as big as the full blade, but it's probably 2, 3, 5, maybe sometimes 10% of the blade laminate that needs to be recycled. So there is maybe a small immediate application for this. And if we think about a blade manufacturer achieving zero neutral CO2 is mostly about dealing with their in-process waste because they get CO2 in, they get CO2 out when they get the blade out. And in between, you've got the waste. So I think in-process waste is maybe something to think about along those discussions. Quick word about Struct Team. We've got 4 core competencies: material science, design engineering, manufacturing engineering, and supply chain management. And the idea is that combining any of those 4 together, you get to cost-effective composite solutions like blades are. They're extremely cost-effective. That's why nobody is asking whether they're in aluminum or so they're in composite. It's established. We don't have to fight for composites to be in those applications. We're independent and multi-sector composite experts who happen to design a lot of blades. Our competencies, so raw materials, we formulate resins. We help material manufacturers to get their strategy right with their materials. We work on equipment and machinery for intermediates. So for example, pultrusion, filament winding, pre-pregging, strong background of material science, structural design, composite manufacture. Those are big components. You have to design for manufacture. It's not good enough to deliver a set of drawings. You need to be able to replicate and achieve the quality in the workshop. And finally, managing certification in all the market sectors we act in. In that case, there is a DNV stamp for the wind, but wind, marine, construction, you have third-party reviews and the structural report, the structural design need to be audited. And managing certification is a big part of our work. Sustainability in wind energy, it's somewhat of a new requirement over the last few years. All Western blade and turbine OEM have committed to zero waste blade by 2030, net zero. Wind Europe has proposed a ban of blade landfilling in the EU, creating a search for circular blade end-of-life options. The blades that we've got today in the fields were not designed to be recycled. It's a strong statement, but you know, since the beginning of the day, we talk about recycling something that was not intended to be recycled. Today's composites, they effectively reduce the CO2 emissions, but they don't really offer an end-of-life management. There is working with biosourced components. So there are a lot of effort to reduce the blade CO2 footprint, but dealing with end-of-life is still an open topic. The leaders in the industry are started to be active. I've got a personal view that, well, whose responsibility is it to recycle at the end? That's still a big open question. Here we need, we had a discussion at lunchtime here. We need a business case to make things happen. In China, you need leadership from the government to make things happen. Very different paths, different speed of application. Now, the growth of the wind market, together with sustainability road mapping, creates opportunities for alternative chemistries, new design, and that's what we'll look at today. Here you can see for a blade, a glass or a carbon spar cap blade, the breakdown of the bill of material by value. And what we are focusing here on this presentation is about recovering the polymers. So on the left-hand side, with the edge glass infused blade, you can see that, let's say, recovering the polymers will, by value, is represent probably 65% of the bill of material. When you have a carbon blade, recovering the polymers is closer to 35–40%. Well, 35% of the value of the bill of material. So first, to look at really at that case, you need to at the values that you can recover at the end of life with the new resin technologies. You have to see what you start with, you know, what design you start with, and you don't have the same economics. In the rest of the study, we'll focus more on the carbon blades. We've seen this information over different formats since the beginning of the day. So that's our own format to look at, basically we convert gigawatt in kilotons, okay? And here you have an idea using our bill of materials, our engineering, design engineering capabilities. So here you have an idea of the past gigawatts, the past kilotons of FRPs that were produced to make blades year by year in the EU. Onshore and offshore with two different colors. And you can also see on the right-hand side, the forecast with what we can extract on what we know today of the order books, the database that gives you wind farms and let's say wind farm permitting database that helps you to forecast already some of tomorrow's waste. It's interesting to note that in that forecast there is a lot more offshore, because offshore have got a much longer order book typically compared to onshore. The onshore is more 2 to 3 years, whereas the offshore is 5 to 7 years of visibility for the OEMs. A brief summary of the various competing options that we've identified. We class them by blade chemistry change. We see that as a big pain point for the OEMs. Rethinking your manufacturing infrastructure is complicated, it's complex, it's time, it's investment, it's money. And we differentiate between open loop and closed loop. Open loop with a big rate recyclate that needs to find secondary application. Closed loop to where you can, where the value proposition is really to remake blade with what you extract from the past blades. In terms of maturity, on the top left, we have land filling, obviously, that is very mature. No secret about it, but hey, that's a solution. So it deserves to be there. Cement kilns, which is proven and at industrial level, but has some limits. It's not as great as it could be better. You know, it's not the perfect solution. As additives as well, we'll focus on that presentation more on the closed loop solutions, the CTEC, epoxy CTEC to recover the bisphenol A, the UPR pyrolysis, the helium thermoplastic pyrolysis. And also we will look at the recyclamine technology and try to compare those to see what is needed to put them in motion and what does that mean at the end of the day for the recyclate, because it's good to say they are recyclable, but what do you get at the end? So out of those 4 technologies, 3 are closed loop. You can see on the right-hand side the type of recyclate that is expected to be recovered. It's great, thank you to the previous presenters to outline the CTEC hydrogenolysis process, so I don't have to speak too much about it. Helium and the recuperation of styrene, the recuperation of MMAs is a thermolysis stroke pyrolysis process. Whereas there is also the open loop technology promoted by Aditya Biala with the recyclamine, which is a cleavable thermoset where you get thermoplastic pellets as a recyclate, which basically you'll want to compete with polypropylene or this kind of thermoplastic, but it's a new product that needs to find its end market and subsequent qualifications. So the closed loop value proposition is very strong because you know already the application, you don't have to develop a new market. Any open loop technologies, you have new product, new materials to find applications for in big volume. So it's a bit confusing. I come back there. It's a bit confusing for tomorrow. I want to buy to build a blade. Which technology do I choose to for something that will happen in 25 years? Put aside in process waste. So to assess that, we've developed a model where from blade dismantling to recycling, where the output is a recyclate. And for each step of the model, and the different technologies, we've modeled the CapEx, the manpower, the bill of material and utilities needed, the cycle time, the energy balance, and the yield. In terms of output, we get the CapEx and OpEx for each technologies. So that helps to benchmark the investment, how much money, how much capital is needed to deal with one versus the other. We have an estimate of CO2 equivalent for each of the recyclates that are generated. And we also get production cost for the recyclate in terms of euros per kilo for the fiber and for the polymer elements. Okay, we can adapt this to pretty much any geographies. We just need a feedstock in terms of kilotons, and then we see we are able to do a first assessment of size of the recycling units. I'm not a chemist, so I prefer to say that first. But our work started from a review of the patents and chemical reactions, enthalpies, to be able to understand the energies, the thermodynamics of the various reactions that were needed to recover polymers. For people who like molecules, on the top left, you can see what you get from dismantling an epoxy and recuperating the BSA. I believe the BSA is a cross. It's a cross like, let me try to, this one? Okay, no, is that the other one? Okay, so that's the BSA. You see, I'm not a chemist. All right. The middle one is more the helium MMA decomposition, and the right-hand side one is the recyclamine decomposition. Basically, each of those technologies, you can see the flow chart where we start with. Where do we start? We have the virgin material, gets processed by the resin manufacturer, gets to the blade manufacturer, the wheat farm, dismantled, gets to that central recycling unit, and depending if it's a closed loop, it will go externally to a compounder, and it's combined with a virgin thermoplastic, and then ends up in other applications. If it's a closed loop, you have the fiber recyclates, which we hope can go back to the fiber manufacturer somehow, but there is clearly an issue to process glass, and the resin recyclate are intended to go back to the resin manufacturer and create that closed loop recycling element. I presented that presentation once in Boston, and I got a very tricky question about the pyrolysis, so we've completed it a little bit just to explain a little bit more our assumption on the pyrolysis. We see two cases. A case where there is waste combustion, and a case where the waste at the recycling center, the polymer waste, is landfilled. Our model takes into account the case number one, the waste combustion, where from the FRP, okay, I'm trying to point on that one, it will, no, okay. Where the FRP shreds are then depolymerized, and the oil and fiber purification happen at the recycling units, but with self-produced energy. We see the recycling center to be cost-effective, to be a power plant, basically, with a potential energy surplus. you get the recyclates at the end. In the case of dealing with polymer waste to a landfill, you need to purchase energy, and we've outlined here the differences between the various options, and we can see that we have a much favorable, let's say, business case if we work with case one. So we've tried to illustrate the unit CO2 landfill versus combustion on two technologies, on the thermolysis for an helium type product, MMA based, or thermolysis based on UPR. The gray scale on the left-hand side represents the unit CO2. Well, we can see that the unit CO2 is obviously higher when you decide to landfill the process waste from this center. In the case of helium, it remains quite significantly below the virgin material, which is, let's say, a strong point. In the case of UPR, you match more or less the CO2 footprint if your recycling plant is not a power plant as well. In terms of unit cost, it obviously increases the cost to purchase energy from outside, and we believe that well, from our models, the results on the UPR thermolysis to recover styrene becomes quite non-cost effective. Okay. The rest of the presentation is really looking at that combustion case where your recycling center is a power plant. So in that first output, we look at the yearly CapEx and OpEx. The hydrogenolysis is a very difficult work. So the CTEC process is quite intensive in terms of CapEx and OpEx compared to, let's say, the pyrolysis processes, UPR or PMMR. The recycling process is quite also intensive in CapEx and OpEx. So what does that mean? That dealing with today's blade as they are with the CTEC process is likely to, the business case is not straightforward. That's what we could do with our own independent, what we could see with our own independent analysis. That graph is I'm sorry, it's a little bit difficult to read because in the case of the carbon blade, the amounts of carbon are all the same. But I think we should focus really on the green bars, which is polymer recovery. This is intended to be in tonnage, but you can see that two technologies stand out, the helium PMMA pyrolysis, which has a very high yield, and the recyclamine, which has also a very high yield, which means that you have less waste to process. The CTEC process is limited in terms of yield by the amount of bisphenol A in an epoxy formulation, which is limited to 30 to 40% of the formulation. So you can't recover more than the element there is, and there is an efficiency factor. The pyrolysis process for UPR is also the same, limited to the amount of styrene, so 25-30% in a typical UPR formulation. So you still have 70% of your resin contained in your laminate that will go into that process waste and be part of your power plant. In that next graph, again, the amounts of carbon are the same between the different cases because we use the same feedstock to start with. But we can see that in the case of recyclamine and pyrolysis with PMMA pyrolysis, you can see a high value polymer recyclate value, which is coming out of the process. We tend to look at things with an 80-20% rule and focus on the 80%. And in that case, recovering, I'll take the example of helium, the PMMA pyrolysis, you have if within your 80%, you have your carbon fiber and your polymer recycled value. Then maybe the glass value, which we all know is less, can be offsetted. Okay, and that's one of the strong points of those technologies. Finally, we look also at the CO2 footprint of the virgin material versus the recyclate. Again, the CTEC process struggled to be very differentiating, so it needs quite a bit of energy to get through. That's what we found. The pyrolysis process for the helium technology works quite well with a low CO2 recyclate, which obviously once the system, if ever the system gets to be used, then there is long-term benefits for the user of that technology with a continuing return on diminishing CO2. The recyclamine is not extremely competitive, but it was compared against polypropylene, which we believe is the competing material with the epoxy recyclamine technology. So we've tried to summarize this quantitative assessment. We do sell the qualitative assessment. We do sell the quantitative assessment, so it's a bit of a teaser. But we've tried to reflect it in terms of a traffic light system, outlining when it's favorable, green, neutral, in orange, or unfavorable in red, to see the wins that there are between the different technologies. If today you want to build a blade and you've got to choose between those 4 technologies, so first, CTEC, no resin change, you make the assumption, but there are a number of roadblocks: high capex, low yield, no reduction of CO2 equivalent. You'll still use plenty of energy to recover your bisphenol A, and the cost that looks, particularly capex, that looks like a big hurdle at this stage. So it's quite a low TRL technology in our views. The acrylics PMMA pyrolysis, which has demonstrated through the Zebra project a number of, let's say, favorable elements: low capex, low OPEX, very high yield, low CO2 footprint, and a cost where the recyclate seems to be very competitive against virgin. TRL level still needs to be proven with the installation of a recycling plant. The polyester pyrolysis is pretty good overall, but the yield is relatively low just due to the amount of styrene in the polyester formulations to start with. So maybe recovering phthalic acids or MTHPA or whatever other constituent that would add some CO2 production, but maybe there is more to recover there. The problem is that you start with a low value laminate, and recovering low value from a low value material, it starts to be really tricky economically. Finally, the epoxy recyclamine has got a very high yield. The capex is reasonable. The OPEX is high, and we've got a big question. It needs a lot of sodium acetate to recover, and in our assessment, the amounts of sodium acetate to deal with it are quite critical, hence the red spot on the OPEX and on the TRL. We didn't understand how to deal with that waste stream. So in summary, when we look at acrylics by pyrolysis, they look like the better option. There's let's say the technology that did shine through our assessment. However, they remain to be adopted in the wind sector. So there's a big reflection that needs to be had by wind blade manufacturers, but they are not necessarily the one who deal with the end-of-life assets. So it's a little bit when people buy train, you've got somebody buying the feedstock and you've got somebody operating it. So the benefits in operation are not really the problem of the purchaser. So I think that conundrum needs to be kind of solved for helium to really demonstrate industrially its value proposition. With regard to the recycling of epoxies, the hydrogenalysis and CTEC technology is great because if it delivers its value proposition, all the existing blades are recyclable, problem solved. However, the business case remains to be defined, and We look forward to the further development of Vestas and the Aarhus University and Stena, and it was great to have a bit more insight into that. But the potential is to be dealing with past feedstock. With the recycling, the technology is interested. We are limited by the waste stream with sodium acetate, which we don't really get today. And you have the necessity to create a new market for the recyclate, which is, again, you have two products to qualify. That resin first, and then what do you do with the recyclate? And you'll get it in big volumes. Finally, for the polyester pyrolysis, we find it quite promising. It's relatively low cost of ownership, but the yield is still seen as a challenge. The advantage is that you have same as the CTEC type process, you have a large feedstock to deal with between the wind and the marine industry with a lot of polyester application to potentially get investment going in that technology. Okay, I'm slightly over time, so if you have any questions, welcome.
Any questions for Julian?
You don't have to, huh? 3 presentations from the beers. Huh? Okay, I'm available if you have questions afterwards. All right.
Very good. Thank you. So now we'll be hearing from Ryan Beach. He's an NREL researcher for mechanical engineering there in Colorado.
Thank you. And keeping in Julian's format, we are 3 presentations from the beer. My name is Ryan Beach. I'm an engineer with the National Renewable Energy Lab in the United States. And today I'm going to talk about some of the manufacturing trials we've done with these new recyclable by design resin systems that are coming available to the composite market. These systems will do nothing to solve the end-of-life problems we've been discussing so far. What they might do is make the headaches of the future slightly less painful. I'm going to talk primarily on the manufacturing work, but I also want to talk about the structural testing and the recycling efforts we've done. Quick overview. I'm going to give an introduction of NREL. I'll talk about these 2 resin systems I want to discuss. Arkema's Elium system and an in-house resin system we're developing called the Pecan system. Spend the majority of the time talking about manufacturing, then touch on structural testing, recycling, where we go from here, and then hopefully we can have a few minutes for Q&A. NREL is owned by the U.S. Department of Energy. We're run through the Energy Efficiency and Renewable Energy Office. The main campus is located in Golden. I work at the Flatirons campus, which is about 25 miles north near the town of Boulder. We do a lot of grid integration research through our ARES and ICE platforms. We have structural research facilities, dynamometer facilities. We do lots of field testing and a newer composites manufacturing facility. The composite manufacturing facility is called the COMET. COMET stands for Composites Manufacturing Education and Technology Facility. Prior to being repurposed as a manufacturing facility, it was used to prepare large wind turbine blades for testing in the building next door. In 2016, we repurposed it to do manufacturing research. It's about a 900 square meter facility. We do testing from coupon scale up to full scale, and we work with a wide variety of stakeholders. We also have 3 structural test labs on site doing primarily coupon testing and full-scale wind blade testing. We're accredited through ISO 17025 to do wind blade testing to the -23 standard. We've been doing that since the standard was written. We have a lot of hydraulic infrastructure for applying loads to composite structures, and we have just about every data acquisition system you can hope for. Talking about wind blade manufacturing, if you've never been in a wind blade plant, it's quite a thing to see. They're just huge. Wind blades as a whole come out the door as just a one-piece monolithic structure. They're typically made using the vacuum infusion process where you apply all your dry materials to the mold. You cover it with infusion media, put a vacuum bag over everything, pull out the air so you can compress the laminate and allow resin to transfer through all the dry material. The picture in the top left shows two skin halves, high pressure skin, low pressure skin. And then once you have two skins, the molds are clamshell closed, as you see in the bottom left. There's adhesive bonding of the joints. And then after that, it comes out of the mold to the finishing department. There was a running joke, if you ask a wind blade manufacturer what the three most important requirements were for resin, the answers were cost, cost, and cost. That may change, but for this discussion, I'm going to say that the top three requirements are: you need low viscosity. The resin has to flow through the fibers. You need a long open time. There's quite a large surface area to fill, so it takes a while. And you need relatively low temperatures compared to some of the other composites. So generally 100 C or less. The first resin system I want to talk about that we've got a lot of history working with is the Elium system that was just introduced. It's a PMMA-based system. When we started working with them back in 2016, it was through an IACME project. The partners up in the top right who are on this project. IACME stands for the Institute for Advanced Composites Manufacturing and Innovation. It's a consortia of national labs, academic partners, material suppliers, and end users. For this project, we were using the Elium 188 grade resin. It was 98% Elium and then initiated by 2% BPO. If you're a chemist in the room and you hear me use improper chemistry terms, try not to cringe too loud. Since then, I think they moved on to a different resin system that works with MEKP to just more match the industry. But when we were doing it, it was the 188.0. One of the first projects we did was the 9-meter blade demonstration that you can see. Oh, not that. Not that. Pointer. Up here. The goal of that project was just to show that this new resin system works with traditional wind blade manufacturing processes. After we demonstrated that it does work, we did a lot of small-scale coupon research. We did a lot of thermal welding research. We did other proof of concepts, and then the project kind of culminated with us building a 13-meter blade and doing a full-scale structural test on that blade. I'll talk about the structural testing in a bit. But from 2016 to about 2020, we were heavily involved with the IACME project, doing lots of work with Elium. After that project came to an end, we picked up another project through the DOE Water Power Technology Office, where we built 4 tidal turbine blades. 3 of them were deployed in the East River, and we did structural testing on another blade. And then when we brought the turbine out of the river, we did post-deployment testing. It might not be of huge interest to this group, but there's a lot of interest in the marine industry in this resin system because it shows to uptake water less than traditional epoxies, and it tends to retain its mechanical strength better than traditional epoxies. So that was the driving force behind the Tidal project. This is just a time lapse of that 13-meter blade build. We start by laying all the dry materials in the mold. Then we cover everything with infusion layout and a vacuum bag, evacuate all the air. We allow resin to move through the fibers in the core. Once the skin is complete, we take it out of the mold, do a really quick visual inspection, make sure everything wet out the way we like. We make another skin. This structure goes in the middle of the blade. It's called the shear web. Once all the components are built, we do a fit check and bond gap measurement to make sure everything lines up where we want it to. We measure what the bond gaps are so we can estimate the adhesive we need. Then we lay down the adhesive on the blade. For this, since it was relatively low volume, we just used cartridge adhesive out of pneumatic guns. Bond the blade together so it turns into the final part. After it's bonded, we pull it out of the mold. We trim the leading and trailing edge. We apply an overlamination in certain areas. And then we prepare the root. So we cut the root, we drill some holes, we bond in some inserts so that the blade can be attached to something like a rotor or a test stand. So that's fairly typical manufacturing process for a wind blade. The next resin system I want to talk about is an NREL developed resin system. We call it the Kahan system. Pecan stands for polyester covalent adaptable network. I am also not a chemist, so if you have any deep chemistry questions, I will quickly refer you to my colleagues. This project started in 2019 when NREL decided we wanted to build a recyclable resin system that can be fully derived from non-petroleum based monomers, so bio-based resins. The bio-based might not be of huge importance to this group yet. I'm curious to see if that becomes a thing over the coming years, but the recyclable thing certainly is. So we have a partner group down at the main campus in the Bioenergy Sciences and Technologies group who is a group of chemists and polymer scientists. So they really understand the chemistry of these systems. They start out by formulating resins. Once they get to a point where they like it, they hand them off to us. We do manufacturing trials with them to see how they handle. We develop test specimens, we test them, we report back, we iterate on the design until we come up with something that works. Once we settle on a formulation similar to the Ilium project, we scaled it up to a 9-meter blade demonstration. So the blade you see in the bottom left is a pecan blades. That's a bioderivable resin system. And then also similar to the Ilium system, our next step was a water power technology offices project. So these are different tidal turbine blades, but here we're testing a pecan blade next to a kind of a standard baseline epoxy blade. Kind of summarizing some of the manufacturing observations we've had compared to just maybe a baseline wind system. The Arkema system has a nice low viscosity, so it wets out faster. It also has an ambient, I'm going to use air quotes, cure. Really, it's in situ polymerization. What that allows is you don't have to have heated molds, so your capital expenditures are lower, your OPEX is lower because you don't have to pay to heat the mold, and you have a faster cure, so your cycle time goes down, so you can make more blades in a given amount of time. It also has the potential to be thermally welded, although that's quite a ways out. Some of the challenges we observed when we were working with it at NREL is it's fairly susceptible to air. We do have to degas after mixing, which isn't a big deal. That's somewhat common. But the hard one for us was the drop test, 5 millibar in 10 minutes. That's maybe a stricter requirement than a lot of wind blade OEMs are used to seeing. The resin system is also flammable, whereas most wind resins are in the combustible class. And when you move from combustible to flammable, you have some bonding and grounding requirements. You may have some storage limitations, just things your health and safety department need to be aware of. And then we also had some issues on the finishing side. Since it is a thermoplastic, it just handles a little bit differently than a thermoset. Nothing that we weren't able to overcome, just something that we observed. For the pecan system, some of the pros also has very low viscosity with full wet out. If you're used to working with an epoxy system, it's got a very similar cure cycle. And when the formulation we've been working on is 40% bio-based, and that costs about the same as epoxy. We'd like to move to 100% bio-based, but some of the molecules just are very hard to find from biosources. The big challenge we see for our pecan system is it has an issue with latent cure. It does require heat to cure. I don't know if I mentioned earlier, it's an epoxy anhydride system, not an epoxy amine system. So if you don't have heat, the cure time is measured in weeks, not hours. So if you pull a bag, you may still have some liquid resin, which is kind of messy. Moving on to the structural testing, the pyramid on the right just kind of shows typically how we work through structural testing when going through a blade design. We start on the bottom with coupon scale. They're relatively cheap and easy and fast to make. You can test a lot of them for cheap. Then you work your way up to complete blade testing, which can take months and costs hundreds of thousands, if not €500,000. I would say even below this pyramid with the group at the main campus, they do a lot of neat resin testing through DSA, DMA, TGA, those kind of things. And then once we get the resin, we do a lot of run-of-the-mill coupon testing and then also full-scale testing. I'm not going to dwell too much on this page. It just kind of shows typical testing that we do and typical comparisons we make between different resin systems. This was for the Pecan project. So you see in the top, there's a Pecan 15 and a Pecan 35. We had two formulations we were working with. We've since narrowed it down to the Pecan 15. Then we also do full-scale blade testing. The picture on the left, is a 13-meter epoxy blade that we tested. We did a full suite of testing for a separate project. That was a project through the Wind Energy Technology Office. But what it afforded us is a really nice data set for full-scale blade testing of an epoxy baseline. And the owner of that mold set happened to be one of our partners on the IACME project, and they donated the mold to the project so that we could build the 13-meter thermoplastic blade. So we had a really nice epoxy data set. We built a 13-meter blade, did the same testing, and we hope to build a Pecan blade soon. These are just some of the results of the 13-meter blade test results. At a high level, the Elium blade was a little bit lighter. That has to do with the fact that Elium's less dense, and we didn't use the same glass schedule as we did for the epoxy blade. From a modal standpoint, the first three natural frequencies were very close. Of high interest to us and to blade designers is the fact that the thermoplastic had significantly higher structural damping. From a static loading standpoint, strain levels between the two blades were close, displacements were very close. And then when we did the fatigue testing, both blades withstood the same amount of fatigue testing with really no change in properties. So some of the observations we've made on a structural standpoint, the big opportunities for Elium we see are the structural damping. There's currently a WIDO project out right now that's funding structural damping research for wind blade design. Some of the potential challenges, when you think of thermoplastics, you may think of creep. It might be to be seen whether or not that's an issue on a heavily fiber reinforced product. And then while all the mechanical properties were close, I recall the Elium properties being like a few percentage point lower. Nothing that can't be made up for in a blade design. On the NREL Pecan side, we have better creep properties, better weathering, and just very similar results to the epoxy baseline. The challenges, we still haven't done 100% bio yet. Again, not sure if that's of huge interest to this group, and we don't have a comprehensive data set yet. It just takes a lot of testing to go through that. I'm going to touch briefly on the recycling. When we were doing recycling research for IACME, it was really small lab scale. We were using, I believe, chloroform to do recycling, and the results were fairly mediocre. I since reached out to Arkema, and they provided these slides from a presentation they gave this summer. I really can't speak to them other than say I'm really encouraged that they are continuing the research and taking it to full scale. On the Pecan side, we're also doing just lab scale recycling research, mostly methanolysis with chunks of just glass and resin. One of the benefits of this system is it can be recycled at room temperature, or you can heat it up to ramp up the process. During the recycling research, we have seen full recovery of the fibers, and we see about 40 to 60% recovery of the monomers. So we're claiming about 80% recovery. And then we've also done demonstrations through a Vehicles Technology Office carbon fiber project where we saw full retention of properties on a 3x life project. Summarizing some of our observations, again, I really can't comment on the Arkema since we haven't been part of that, other than to say it's encouraging that they're continuing and scaling up. For NREL, the big opportunities are the fact that it's relatively low cost if you can do it at room temperature. It uses I'm told, mild chemical solution compared to some of the other methods. We've gotten multi-life demonstration and shown full recoverable. Some of the challenges we see, and I think this is a challenge for everyone, is fiber orientation. You're never going to get long continuous fibers in a nice weave, and resizing. And then we need to do scale up our demonstrations. I also want to put a plug in. We've got another team that does TEA, LCA work. So they do all that in parallel, but I didn't want to add it to this presentation. So next steps for the pecan, we've got continued carbon fiber work. We want to build and test a 13-meter pecan blade. We're building, like I said, those tidal turbine blades that we're doing lab testing on. We want to deploy one at the University of New Hampshire deployment site. And then we need to scale up our recycling demonstrations. And we always seem to be in contact with different resin suppliers on cure packages. I think I mentioned earlier, we do have the only active Elium work we have right now is through that Wind Energy Technology Office project where we're modeling and measuring structural damping. So we're doing a lot of coupon manufacturing and beam manufacturing for structural damping characteristics. And I think I am a minute and 20 seconds early, so we're that much closer to the beer.
Any questions for Ryan? The microphone's coming. Second.
Thank you so much for your very nice presentation, Annalima, DTU. I have just a question because you mentioned that you have this other team working with LCA. I was wondering if you have quantified how much you save of energy and all of that and materials and so on the different recycling options that you're looking into.
Yeah, if we can, I have some backup slides at the end if we can pull the presentation back up. I have very little knowledge on that, so I will be fumbling through the slides trying to answer that. If those can come back up, I'll maybe take the next question and then revisit.
Well, so, okay. So non-chemist to non-chemist, what recyclate do you get back? Is it the MTHPA from your anhydride system or?
I don't know.
Okay, thank you.
I didn't do any of that work. So.
Okay. Okay, thank you.
I can deflect more questions if anybody has more questions. Let's see. TEA LCA metrics. That looks like a promising slide. And I won't try and fumble through it out loud. So if this doesn't answer your question, I think I have one more slide I can try.
That's okay. Can I take a picture?
Yeah, and this should be public. We did have an article recently published in the journal Science that has all of this outlined, and it does it does have the formulation of the resin system. It is patented by NREL. So if you are interested in using it, I think I'm not a lawyer, not a patent lawyer, but I think NREL's approach to patenting is we patent it so we can license it for very cheap so many people can use it. We're a nonprofit and we wanted to get out there. Curious to see what the other one is.
One more.
Hey, Ryan, thanks for a good talk. Hey, real quick, and you don't have to answer this one if you don't, or you can deflect it if you want. The pecan resin, I'm taking it that you're gonna try to outsource it. I mean, I don't see NREL actually producing.
No,
it
we will
themselves.
never be a blade manufacturer.
So are you gonna do some more testing on it, or what's your?
Yeah.
Okay.
Yeah, well, I mean, we have several projects that are active.
Do you got any commercial interest right now? Can you say yes or no on
I
that?
don't know. I am the lab rat. They almost never let me out of the lab, so the fact that I'm here right now is fantastic. Since other presenters have called out Derek Berry, my colleague, I might have you talk to Derek, or actually, I can put you in contact with the PI.
I'll talk to you.
Okay.
Very good. If there are no more questions, Ryan, thank you very much. Next, we will hear from Heinrich Salstam, CEO of Afterwind.
Good evening. Two more to go. I will try to be brief and not be too provoking, and with that will inspire questions. But my name is Henrik Selstam. I'm based in Gothenburg. I'm a physicist and not a chemist. And I've been involved in recycling and green energy for more than 25 years now. And a lot of startups in methanation of CO2 and plastic recycling, end-of-life tire recycling. It's a live project right now, and also textile recycling. And some of that knowledge and relations we have in those projects has been applied to wind blades. And it's a combination of mechanical and chemical treatment. So we believe the key is to combine these technologies in the best way. Is it forward? Wind energy has an immense problem and no sustainable and scalable answer. 43 million tons of retired wind turbine blades will be generated globally by 2050. That's a lot. So there is plenty for everyone. And here's the provoking thing. Afterwind has developed the only circular, sustainable and recycling solution to recover 75% of the blades into virgin material. I know you have a lot of questions about that, but the reason we're saying this is that we don't downcycle. We try to go back to the virgin states or the different products. So fibers should go back as fibers, as reinforcement, and whatever you can extract from plastics or epoxy should be extracted. I just read an article in a scientific magazine about recycling of epoxy. Through recycling has gone down from $2.1 million per kilo to 1.5. So it's not a viable solution to have an epoxy that you can use again. So what you can do, you can extract precursors to plastics instead. So that's our approach. And this is taken from the investor presentation. So we are seeking 1.5 million to start up the operation. Afterwind exists to preserve natural resources for future generation by reprocessing end-of-life wind turbine blades into traceable virgin grade materials. I will go into the traceability later. As a recycling partner, we utilize best-in-class shipping, shredding, milling, sorting, and reporting solutions to reach our goals. It's a bit hard to read, but there are the 43 million tons of retired blades. And EU wind industry requires to recycle 100% of retired blades by 2025. 100%, that's quite ambitious, and we are just a year from that. And blades contain complex composite that boosts performance, of course, but very challenging to recycle. But you heard that during the day anyhow. So what we do, we combine a mechanical treatment. It's a milling system, very simple. It's a rotating mill with blades, with flanges that crush the shredded blades in that process very fast. It's about 1 ton an hour, and very cheap and very straightforward. And what's good is that the electricity need for this is quite low compared to other processes. So we have defined this as a recycle as a service. That's what Afterwind will do. We will take care of all blades, decommissioned blades, once they're down from the pole and cut it. We take it from there and shred it and mill it and process it. And we partnered up with circular glass fiber and epoxy manufacturers to offtake waste streams. With blades installed up to 2029 and 15 years lifespan, and we used 14 ton per megawatt. So that creates these 43 million tons. It could be more, it could be less, but that's what we're looking at. And there is also a landfill ban in the EU from 2025. So we need to do something with these blades. I will skip a few here. So go into this model. Our business model, we improve the footprint. We are striving for a zero landfill, traceability and regulatory compliance, and taxonomy due to tax benefits. Because if we can show the client that we are taking care of their blades responsibly through the process, so we can track the blade or the parts of the blade all the way through the process to the end user, it's also good for taxonomy reasons and for the EPR auditors. So we collect retired blades from asset owners and manufacturers. Client decide where to cut and shred, so we adapt to the client's need. We use a combination of technologies to recover fibers, long and short, as well as resin. And we guarantee 100% end-to-end traceability. We deliver recovered materials to glass fiber and resin manufacturers. So we combine the mechanical treatment and chemical processes to extract the very most of the material. By taking apart the fibers from the resin, we can treat the resin chemically and get the most out of that. So we can start by cleaning, take away the chlorine from the PVC, and we can take out the easy part of the plastics, and we can use different kinds of solvolysis as well. And to respond to your question earlier today, what happens after the solvolysis? You know, what happens with the black soup that is still there afterwards? We have a dead stop, and if we cannot treat it by chemically, then we can treat it in gasifier. So I don't know if you are familiar with gasification, but we have a working unit using RDF or refused dried fuel as a feed to produce green energy. So we would just blend in this black soup in that process. There's still some energy value in there. Traceability. So we use industry standard machinery, and we have tailored for our customer needs and protected by intellectual property rights. Our process for PETs, for instance, is patented. It's a partner we work together with. We can actually get PET converted into BHET, which is the precursor to PET. So we can have virgin PET coming out of that process. Not many others can do that, and we do that in textiles already, and it's a proven process. So it's TRL9, all of this. And we have operations to be ready to go live at scale very soon. We started the company 1 year ago in Norway. We will move it to Sweden because the market is basically in south of Sweden and Denmark. And we are just about to start up the commercial production. We've done a lot of testing at a test site outside Gothenburg and also in southern Sweden at Malmö. The chemistry has been proven down there. So we are prepared. We will have a small CapEx light installation. It takes 8 to 12 weeks to install. It will be put in 4 containers, and that could be placed nearby the market. And that includes everything from shredding to having separate products like the fibers and the resin that will be shipped to south of Sweden for centralized treatment. Whatever comes out of that treatment will be shipped to the gasifier, and that's placed in Slovakia for the moment. And the traceability is a very crucial thing here because you have to make sure that you keep track of all blades coming in. We mark everything in batches with a QR code and everything in the database. And whatever we know about the blade, because the blades, they come in all sorts and shapes, and we cannot assume anything. It's old blades, 20 years old, and it's glass fiber mainly, 99%. Whatever is carbon fiber will be cut out manually, and the glass fiber will be treated in this process. And we keep track of that batch all the way through the process. And here we go to the popular LCA discussion. This is highly hypothetical, of course, because we don't have a plan yet, so we cannot actually calculate transportation costs and such. But this is a comparison between the base case, which is co-incineration, co-production with incineration ending up in concrete. And the best case is when we use our technology with the mechanical treatment, solvolysis, and also gasification. So about 600 kilo per ton reduction of CO2. That's what we ended up with. And if you're interested in this LCA, I will refer to my colleague, PhD student in London. And we cooperate with a lot of students in south of Sweden. We cooperate with Lund University. And the professor there, he's actually the owner of the company that we partner up with, Hulteberg. And if you look closely at this slide, you see that it's 1 ton looks a bit bigger. And that's because some of the parts of the content goes twice through the process. And here's our team. I started out as CTO and founder, but waiting for a CEO to step in. I will take that role until end of the year. And we have Italian, Norwegian, Swedish, and a lot of people here. Down in the left, you have a mechanical recycling expert that's been doing this for many years. And we have the professor, Christian Hulteberg. He's also involved in the textile recycling, Rewin. And here's some advisors and partners. And the 3 in the bottom there are students at London Business School. And they have done a job for us and competing in the Turner Mint competition to take different projects and look at them from top down, how we should introduce this into the market and how we are cooperating, what kind of ideas we have, prospect of developing quickly. And they won the contests. So we have that school, Turner Mint, is one of the shareholders in the company now. And this is the opportunity, also from the investor presentation. Oops, 35 times the money, if you're interested. Thank you.
Thank you, Henrik. Any questions? One of the things that, go ahead.
From McKean. Working with the glass fiber manufacturers, we learned that for remelting, the fibers had to be very clean, very clean. What do the glass fiber manufacturers do with the powder that you provide?
We can deliver fibers since we are shaking them apart mechanically by using the resonance. So we get the fibers quite clean from the resin, but they get shorter, of course, because we have to shred it first. So the fibers get up to maybe 30 millimeters. So we're looking for off-takers in the market, 5 to 10 millimeters, 10 to 30 millimeters. And there are quite a few using this as a reinforcement for molding, for instance. Could be used in the wind power for the dog houses or the nacelle cover. So of course, we want to go from blade to blade. It's a far stretch. So we also have off-takers that are willing to melt it and create new filaments.
Okay, I misunderstood. I thought it went back to the manufacturing for glass fiber. So yes.
Yeah, and it has to be very clean, of course.
Yes.
The regulations are quite strict, and I think that will loosen up because sometimes you have to give some to get some. So I think that will change. We saw that in the end of life tire when we started that 5 years ago. The manufacturers didn't want to talk about recycled carbon because it's low value, and now they are actually paying more for that. because of the sustainability premium. So I think that will change in the market. I hope so.
Henrik, you say, I'm over here, sorry.
Yeah.
You say that you're ready for commercial scale up. What type of volume would that look like when you do? And then secondly, have you accomplished any proof of concepts with different companies on applying this glass, recovered glass into next life cycle materials?
Yeah, we still haven't managed to get the glass into new products yet, but we have delivered test materials, and we have been approved for certain kind of applications. The plastic part of it, that is proven in similar process for other clients. So, but the capacity, the first half year, 2 kiloton a year, and then we will ramp up to 10 kiloton a year quite quickly. It's not that capex intensive, this setup. It's just the mill and the sorting and sifting. So it's very quick to set up.
Anyone else?
There's one more to go.
Question on your business case, the numbers that you showed. You showed a relatively high gate fee of 500 to 1,000 euros.
Yeah.
Well, from my question, I think that's rather high. What happens to your business case if that drops down, goes to zero?
We have quite a lot of resistance in the model, but it's actually in that range. We have several clients willing to pay that because it's a responsible way to get rid of their waste. And on the offtake side, that's also ambitious, 1,500 to 2,000, but it's actually from a live case. So if we can do this responsibly, it's like you have a stamp saying that this has been taken care of sustainably. So it's actual live data. I think the break even should be something like 1,600 on the offtake. Yeah.
All right, very good. Thank you very much, Henrik.
Thank you.
So now we will hear from Joachim Krachhauser. He's chairman of Wingbeam, and they're in Sweden. Thank you.
Thank you very much for the introduction. Thank you for having me, and I'm highly aware of the timing here. Joachim Krachhauser is my name. I represent the Norwegian company Wingbeam. We want to convert used turbine blades directly to building materials to the extent possible. I'll take you through some background. We can hop over it, but mainly the challenges we have in the form of decommissioning, production, finding the right markets, and financing. And I'll show you the way forward. Before I do so, I have started a number of companies. I'm no longer 40. Why should I do all this? Let's think about CO2, which we emit daily. The blue balloons, this is a heap of carbon dioxide balloons over New York City. You see Manhattan. This is only one day. This is the dimension of the environmental issue we're facing. Not all American presidential candidates know that CO2 is contributing to global warming. Secondly, despite the phenomenal successes of Vestas and the like, we've heard about their hundreds of gigawatts supplied already, the world is running on oil. This is from a BP annual report. You see that coal, oil, and gas supply the world with primary energy. Renewables, you can hardly see them on the slide. So we need much more wind and solar, for that matter, in order to accomplish the transition, or energy saving, or a combination of all that. Now, to our theme, we've talked. All presenters had the different solutions on the table here, but of course we want to use materials responsibly here. I picked this slide from our friends at RISE in Gothenburg, a very competent composite institute. Now, to our business idea, we want to reuse the fantastic quality of the composite materials as it is. So basically, we want to cut rods and produce architecture from it. The Eiffel Tower already exists, but there are many more buildings or architectural units to be built. So that is what we want to do. In Sweden, we're also like Henrik. We're moving from Norway to the south of Sweden, where we'll have lots of blades available. Thereafter, the north of Sweden will be highly relevant. And there are enough blades for everyone, like we said a couple of times, is just figures for the Nordic countries. And we envision we have just a few percentages of the market, which will still mean that we will have 1,000 ton or more per year to convert in our unit. These are future numbers. It can be whatever. It could be much more, but supply is not the problem. Now, we want to develop industrial solutions. I love these articles, and I think tomorrow Albert will present some Dutch examples. Fantastic, I love it, but it's difficult to scale it. It's difficult to industrialize these type of solutions, as nice as they are. Our challenges in developing these industrial solutions relate in the first place to a proper decommissioning method. What we want decommissioning partners to do is a sort of smart decommissioning. We want them to take the blades down responsibly, don't destroy the composite qualities, cut them into right fractions and transport them to our factory. And it would mean cutting that into 6 to 18 meter segments, which can be transported on timber trucks. Often in Sweden, it's natural parks. We would need to have covers to collect the water from cutting these sections. We want to supply the main sections, spar caps, and the good areas to our factory. The rest, we need partners for all these technologies to handle the rest, the tips, leading edge, other parts which we can't convert to useful products. So that has to be organized. That metals and other stuff is separated, goes without saying here. One should be aware that all these processes are highly regulated. As an example, this waste has to be transported in covered trucks in Germany. Similar regulations will probably develop in Scandinavian countries. So decommissioning and transport is highly regulated. Factories as well, if you handle special materials. When we go to product development, it's even more complicated. The building regulations, specifications, long-term testing for all the products we develop. So we're fully aware of that this will take a lot of time. The second challenge for us is the production of our rods. They can be produced in different dimensions. We have tested water cutting. We settle for a diamond source for speed of all this, but this has to be the right quality. It has to be quality managed. If there are mistakes or defects in the composites, it has to be discovered in our factory. It has to be highly automated to save costs, tolerances, quality. All that has to be managed properly. By now, you see in the middle picture, we have some 2 or 3 kilometers of rods in different dimensions and produce prototype materials from 2 45-meter Vestas blades, which we got very cheaply. We're all aware that there's a multitude of materials used in the blades and also differing from manufacturer to manufacturer. So we have a selection procedure even there. And again, we want to extract the high modulus components from spar caps and shear webs. They go into different applications, and you will see a couple of examples. We
we call that an industrial solution. We find that rods and things you cut out from the shear webs are almost like Lego parts. They can be used by many industries, and they can do their own thing. Our focus will be on the production, maybe product development, but we don't want to enter upstream or downstream too much. The whole value chain is already complicated enough in our factory where we are. We call the decommissioning and the preparation blade circle. In our factory, we have separation of materials, we have sawing. Then if we combine it with molds, I'll show you examples. We may produce them ourselves depending on customer requests, but we do storage, surface finishing, and then we'll send this to our customers. But we're fully aware that 50% of the materials will be residuals, which hopefully enter one of the promising processes: pyrolysis, solvolysis, shredding, production of panels, and the like. So we are really dependent on this ecosystem of industries here. On the left side, you see a picture of a rods glued into a wood plastic composite profile. The original is 6 meters long. You'll see a picture of that as well. It should be a beam or a pillar or a column for storage holes, where we cooperate with the Norwegian FBS group. They are about to build a storage hall of reasonable dimensions, and they want to test different embodiments or different designs of these beams. We think in terms of strength and stiffness. Of course, we will match the steel specifications, but our stuff should be lower costs and actually lower weight. We've done a number of full-scale testing of 6-meter beams in terms of modulus, tensile strength, what have you, fatigue, bending tests, also immersion in water. The supplier of these wood plastic composites said, you have a problem with water ingress. No, this kept the same properties after immersion for more than half a year. We will continue this testing, which of course also the effectiveness of the glue binding the wood plastic composite to the composite fiber rods. So all that looks good. In terms of applications, we look, for example, at storage holes, as mentioned, but a greenhouse is a very similar construction. The market for that is spectacular in Sweden compared to Holland. In Holland, you have 100 square kilometers of greenhouses. In Sweden, only one. So there's a real market niche in this type of architecture. And we want to address the low-hanging fruits to start with. Here you see flooring. This is a summer house in Sweden. It had a pressure-impregnated wood on the terrace. This is a horrible material environmentally and also practical. It degrades, you get splinters, you have to oil it, polish it and oil it once a year. This is 7 years old, no service, no nothing, nice to walk on, extremely stable, nice to work with. This is a material containing 75% wood powder, and 25% can be recycled plastic. The supplier, Megawood, says, if you don't like it, send it back to me. I'll make new terraces. And the new thing will be a similar flooring system, but incorporating up to 25% powder from blades. So it can replace the wood powder or wood fibers elegantly. This is where we see a market. It's the company Novotec. They produce some 80,000 tons of these wood plastic composites at this time, so they can easily absorb a whole lot in flooring. And I think the market has enormous potential to grow. I think in the US, the market is like 300,000 tons. So in Europe, it should grow as well. They are a partner for us. They said we can accommodate your materials, but they work according to cradle. So they say you can supply anything, but no PVC, no heavy metals, no nothing. So it's not easy to separate the nasties from them. And by the way, they're also in this sort of €1,000 per ton gate fee. Flooring can also be supported by these rods, so you have a combination of both. As one other product, there are lots of things possible to develop from furniture or reinforcing wood laminate or whatever products you can imagine in the building sector. Railway sleepers is one particular area. There we use the heavy elements from the shear webs, screw them to long rods, and in railway sleepers it's extremely important that you have this dimensional stability at different temperatures from -40 to +40. So these things have really proven in pilot experiments to be very promising. To summarize the product development, we've developed on a prototype scale a number of solutions for pillars, beams, roof girders, these type of things, railway sleepers. We've looked at and written a number of patents, for instance, on truss systems, like the Eiffel Tower construction, and asking currently potential customers for specifications. What would you like? What were we competing at or with? What type of material properties do you need? How important is afterlife, considering recycling after the application? So we're on the prototype stage. Thinking commercially, what we believe you can do the production process for around €2 to €4 a kilo. Gate fees, I have been very skeptical. The company, very interesting company, Continuum in Denmark, say, well, we can live with €250 per ton. We hear different figures. I think it's not settled. It'll settle in the next couple of years. I would hope, of course, for €1,000 or €1 per kilo in gate fee. That's a nice contribution. But on the other hand, we are competing with virgin composite materials, which are not cheap. They can be in the range €8 to €15 per kilo. So when you look at fish farm construction or the like, then you have, with these production costs, you're about to be competitive. Steel, wood laminate, these can be cheaper products. Then in the end, a PR effect or carbon footprint may decide on the use of these materials. But definitely gate fees, policy guidelines, like Irene also said, this is extremely important in this emerging field. If you want to attract financing folks to the area, you need to provide certain ground rules and long-term certainty. The team, I always joke, on a diversity scale from 0 to 10, we don't even fit on this scale. It's all retired, gray-haired people, but highly experienced. Paul Hansen and Stein Dietrichson developed actually PET foam for the wind power industry. We've been working on wind power de-icing. Paul has developed carbon fiber composites for the military, for the naval field. Lars Brynildsen is a building engineer. I come more from the energy and patenting side, so it's almost. This is my wife. She said, "Right, 5th challenge, your age." So I didn't want to write it, but okay. Never mind. We are situated in Fredrikstad, near the Swedish border, in an old sawmill. So we have place to receive a couple of blades. That's where we converted the 2 Vestas blades. But we are inquiring or searching for a good place in the southern part of Sweden to build the first factory, and that should be at least a few hundred tons. But the 2,000-ton factory should actually be profitable. Summarizing, we want to convert to blades directly to long rods, suitable building materials to the extent possible. We definitely need a partner. Got a good IP. a factory we calculate should be profitable from the start. So we're also looking for intelligent money. But the important message here is really the uncertainties in the policies should be regulated. And I appreciate the work being done in this agency Task Force 45 work. I think we should be engaged there. Needless to mention, everybody in this industry is looking for money, but we're looking also for smart money and for cooperation in this ecosystem. And as you've seen the picture of our founders, we need especially a young CEO and a young production head. So welcome to us. Thank you for your attention. Broke a record 2 minutes early.
You get the first drink.
Get an extra beer.
That's right. Joachim, thank you very much. Do we have any questions?
Okay, it's working. I have a question because actually we also cooperate or have a loose cooperation with Megawood. So they are, you know, when I mentioned cradle to cradle, they can only take very, very specific parts, super picky. So because they don't want to contaminate their products, because their products are like cradle to cradle designed so that they can continuously just, you know, recycle all the terraces, yeah, like forever, basically. So they have found a interesting patent, an old patent about replastification. That is basically how they do it. So, but then the question is what to do with the rest of the blades. So I understand, okay, partially you can give some of the parts to Megawood, great. We do the same, or we could do the same. So, and then you have your beams, but then how much leftovers do you have? Like there's obviously some parts that cannot be recycled by you, but then do you have a partner, let's say, who takes a skeleton, or how should I describe that? I don't know.
You know, Novotec is definitely our partner number one, and we're discussing with them how we can separate nasty materials. I mean, you can't have 0 ppm on everything, so it's a discussion. But I know their level, their cradle to cradle level is extremely high. They have a certification for that, so I appreciate that. Maybe I'm painted by my 10 years background in the oil industry that you know, I would tolerate a certain amount of nasties in long-lived encapsulated products. But, you know, it's a discussion. But I think that there are now so many processes being developed by many of you that we will find a home for these products. And your question about the percentage, I would figure 30 to 50% has to go into some sort of granulation and other process.
Okay, you can ship it to us.
Mm-hmm.
Yeah, hello. I have a question regarding you are cutting out beams from already fatigued laminate. How do you ensure that when you use these beams for something like a building, that they can last the full lifetime since they are already fatigued? I guess it's a statistical event when they will fail.
Good question. We do a quality control after sawing. So obviously blades which have been mishandled during decommissioning or the like, those can't be converted. But we take the good stuff and we do quality measurements. So automated afterwards, a bending test, and this type of inspection to make sure that it meets specification.
Okay, thank you.
Mm-hmm.
Great, I go first, Francesco. I really like, we had a discussion at lunch with a couple of people on the repurposing, and well done for doing something of those spark caps and repurposing them. There's a company in China who does pallets with the rods, and they use it as support for the pallets, and then they have a fleet of pallets that they lease, and they make money of moving the pallets around, which are made from recyclates of blade. With regard to the construction beam, we work across sectors, and I'm not too concerned about the structural integrity. So you don't lose modulus so much. You might lose a bit of strength, but civil structures are stiffness driven more than strength driven. So I can see the workout. But one big requirement in construction is fire. And those resin systems that are used for blades have no ATH additives for FST, fire, smoke, and toxicity. So how do you pass the regulations, or is it something you've looked at? Because anything construction related for a building, you have very stringent FST, fire, smoke, and toxicity requirements to comply to.
Totally correct. You named toxicity, in particular flame behavior and these type of thing. It's FBS Group who are building the new storage hall. They're looking at that. So you know, the composite as such is not flammable, but if you take well, not immediately flammable. Like, you know, we tested a combination. We laminated it in wood. Then the wood is the outer shell, and we have seven-story wood houses in Sweden. So actually, their fire behavior is almost better than a concrete building. So then the composite doesn't really matter in that structure. If it's directly outside, like in the beams I showed you this with an opening, then it's a different story. So FBS is looking at that. We're focusing on the production of the rods, but it's a valid theme.
No, but you gave a very good answer. You put a charring layer by having some wood encapsulation, for example. Wood is great, it burns slow. Composites burn quick. You know,
yeah.
Thank you.
Yeah, I had curiosity more or less in the same direction, but more on the mechanical performance of these beams. Because if I understood correctly, you extract or you generate these beams in the longitudinal direction of the blade. So you are constrained somehow by the direction of the fibers.
That's correct.
That are applied on the blade, right?
Yeah.
So you may resist well in loads in certain directions, but not that well in load in transversal direction. Or, I mean, how much is this constraining your application range? That's my question.
It's a very good question, and also I'm not surprised that you're a professor it's totally right. You have bidirectional or multi-directional glass fibers. So, and I'm very afraid that we will have different qualities in the warehouse for different applications, but I think we will end up like this. I think we have to work backwards from a customer setting a specification. We need this strength, we need this elongation at break, or we need this compression strength. Get me the rod of a proper dimension which meets those specifications.
Interesting. Thank you.
Thank you for the question.
Any last ones? Joachim, thank you very much for your presentation. So that concludes our first day. I just want to say that I'm immensely encouraged by kind of the creativity and the ingenuity of our colleagues here in this room. Necessity is a mother of invention, of course, and we absolutely have to figure out circular economies and polymer composites. And a lot of these colleagues that we have here today are doing that. So one of the things I really want to encourage all of us to think through as we go and partake in adult beverages or whatever we end up doing the rest of the night and into tomorrow is think about impactful conversations. So when you're speaking to different colleagues and you're thinking about your own projects, think, how can I advance the conversation in each of these points so that tomorrow we're in a different spot in advancing the conversation? Because obviously last year when this group was meeting, the conversation has advanced since then. And next year, when we come back and reconvene, the conversation will advance even after that. But there's one thing that really needs to take place for that to really occur. So it reminds me of an opportunity that I had with Carbon Rivers doing automotive polymer composite type of research with the OEMs and the tier suppliers. And I realized at one particular point in that meeting that if the sustainability officer and the engineering officer and the procurement officer and the financial and the business development were not all in the same room speaking with each other, then the conversation would not move forward. So we do have a really nice opportunity here that we have universities represented, OEMs represented, wind developers, academic institutions, nonprofits, things like that. So make sure that in the conversation you're having that you're extending and advancing the conversation, because we do have a great opportunity right now to solve some significant global problems. So thank you very much for your time today, and I hope you enjoy the rest of the evening.
Good evening, ladies and gentlemen. Just few last words from my side. First of all, I would like to thank all our speakers for their commitment and interesting presentations, all our participants for coming and joining the discussions and posing very interesting questions. As I have mentioned in the beginning, the presentations will be available for sharing, usually within 2 or 3 weeks time. Also, I would like to thank our chairman, Mr. David Morgan, for his guidance through the conference. As mentioned, now we will gather for the drinks. Tomorrow we are starting 8:30, same as today. There will be a slight change in the agenda. Please check your inboxes later on. I will be sharing the latest version. Before everyone now goes for the evening reception, I would like to ask everyone to come on a stage for a final photo. And of course, please don't forget to evaluate us in the evaluation form. Thank you. And now please, everyone on the stage, enjoy your evening at the bar. Thank you.
Direction, so.
No one dares to stand here. So, why not? Mevrouw moet staan. Ja.